had given several courses at B.Sc level at this platform, some in Hindi, some in English, and this particular course on classical mechanics will be in English. The course will start 26th of January 2021, and roughly the duration will be about 8 weeks, 2 months, and the course will be in the Newtonian framework of mechanics, and we will be talking about dynamics of a single particle, a group of particles, and rigid body. And in the course, we will be developing notions of several parameters, the linear momentum, the angular momentum, the kinetic energy, the potential energy, and various conservation laws. I will be talking a little bit about non-inertial frames, especially rotating frames. Our Earth presents a very natural non-inertial frame, rotating frame. So the kind of Pseudo forces we need in rotating frames, little bit of that I will be talking. Central force motion I will be talking. Our planetary motion is a central force motion, very natural motion that we know, and many other forces. We will be talking of collisions of bodies in center of mass frame and all those things. But the main focus will be on rigid body dynamics. So at school level we had been studying all these things, the rotation of a rigid body, but basically that was confined to a simple case of rotation about a fixed axis of rotation, and there also we were more concerned about parameters which are along the axis of rotation. So we do components of angular momentum and torque and everything in that direction, and develop relations like L is equal to I omega or K is equal to half I omega square and so on. But here we will be talking in more general terms, and moment of inertia tensor, 9 components of moment of inertia, all those things will be involved.
So welcome to this new course on classical mechanics, and when you say mechanics, we have varieties of mechanics. Some of them I can write here. You have classical mechanics, then you have quantum mechanics, then you have statistical mechanics, so varieties of things are there. Classical mechanics, which is the topics from classical mechanics that we will be doing. So classical mechanics is the one from which we will be doing this course, some of the topics. This is basically, it talks of particles and systems which are not very small, not in angstrom level or nanometer levels. So quantum mechanics is the branch where we talk of small particles. Small particles. Not that here we will not be talking of small particles. We will, many times we will take examples where electron is going and proton is there and so on. But basically, if you want to understand the dynamics, the behavior of particles, then you have to go to quantum mechanics if the particles are very small means in the nanometer angstrom regions. But if you have micrometer type dust particle, starting from dust particle let us say, and then planets, okay, so all that that range is governed by this. So not too small, not too small particles. And you have yet another thing which is called relativistic mechanics. Relativistic mechanics. So the varieties of mechanics. This is the one where we talk of high speeds, and not always high speeds. Many times the speeds are not very high, still you need this relativistic mechanics. For example, when you have fission or fusion of particles, nuclear particles, the speeds are not very high. A neutron with a very small velocity enters uranium-238, makes it uranium-239, and then splits. That doesn't come under classical mechanics. These rules will not be able to explain all that phenomena. So you do need their relativistic mechanics and quantum mechanics. Okay, relativistic mechanics, that gives me how much energy will be generated, how much mass will be decreased, whether mass is converted into energy, those things will be here. Then quantum mechanics will be there because we are talking of nucleus which is femtometer size, not even angstrom, femtometer size. So combinations are needed. Alright, so this is it, and this statistical mechanics is when you have large number of particles, very large number of particles, and each particle has a different behavior. Here also we will talk very large number of particles, because we will be talking of rigid bodies, for example. So rigid body will have a large number of particles, but then here you have like gas molecules in a gas jar. So you have large number of molecules, each molecule is going in a different fashion. So that is done under this statistical mechanics. Now coming to classical mechanics, which talks of particles, system of particles, rigid bodies, like that. Here also you have three formulations. One is mechanics, classical mechanics, formulated by Sir Isaac Newton. This was sometimes in the 17th century, sometimes in the year, let us say, around 1687. Perhaps this was the year when Newton published the mechanics book Principia. So this is the roughly 17th century, later half. This is the period when Newton formulated this. We call it Newtonian mechanics, where the central thing is force and motion, force related to motion. This is the central idea. This is a central area. We talk of forces acting on particles, exerted by other particles. So forces are there, forces are causing motion, and from there this entire mechanics is developed. We will talk of various parameters like momentum, angular momentum, energy, all those things will be there, but basic central theme is force and motion. Then about 100 years from here, you have another formulation of classical mechanics, which is called Lagrangian mechanics. So the scientist was Lagrange, and this was around 100 years down the line, somewhere around say 1780s or so. So here he was a mathematician basically, and he developed a total branch of calculus where some small variations are the key elements, and then some kind of least square or action principle, and so on and so forth. So that was the kind of mechanics which is equivalent to this Newtonian mechanics as such, because you can always go from here to here, but then the entire formulation is very, very different. And something around 50 years from here, you have another one which is Hamilton. This scientist is Hamilton, and the mechanics which he developed is Hamiltonian mechanics. So these are all equivalent, but then the formulations are very, very different, and you have advantages for this one, you have advantages in this one, you have some advantages in this one. The biggest advantage of this Hamilton, this is basically the central thing is energy. Kinetic energy, potential energy, some total mechanical energy, that's the central idea. Here the central idea is yet another function called Lagrangian function, again based on potential energy and kinetic energy, but totally different combinations. So this was let's say 50 years from here, somewhere in that era, okay, in that era. So this is how the very important thing and very interesting thing is that this formulation of classical mechanics can be used to very easily make this transition to quantum mechanics. Okay, so although the classical mechanics and quantum mechanics, the rule are very, very different, but from this particular formulation, the structure is such that you can, if you have mastered this, then the mathematics of this quantum mechanics is very, very at least is related, connected. So you can go from here to here. So these are the kind of things that we do in the name of mechanics, and then in the name of classical mechanics. In this particular course, we will be talking of this Newtonian mechanics, right? So we will be talking of a single particle system, and then the forces acting on a single particle system, and then how it moves. And you all know that it is governed by three laws of Newton: first law, second law, and third law. And then there are very well structured equations. F is equal to ma. You solve them to get the future of that particle. Once you know the initial, the present of the particle and the forces acting on them for each instant to come, you can predict the whole trajectory of that particle. So single particle system. Then we will have a multi-particle system, several particles moving with respect to each other. And then once again, how these forces will govern that. You will have forces between the particles by one another. You will have forces from some other particles which are not part of your system, so how that behaves, then we will have all that rigid body and all that. So this is the kind of thing, the syllabus is given, or the topics which we will be covering here are given at the website in the opening page. Okay, so that is our focus, and let me start talking of Newton's first law, second law and third law. So you all know, you had been studying this from high school time. Newton's first law is, if there is no force on a particle, the particle stays at rest or it moves with a constant velocity. So in varieties of ways you can state the same thing, but essentially that is the first law, that if the force on a particle is 0, if the force on a particle is 0, then the acceleration is 0. Then the acceleration of the particle is 0. Essentially is this in a nutshell, because if it is at rest and remains at rest, that means acceleration is 0, or it moves with a constant velocity in the same direction, same speed, that also means acceleration 0. So if you are talking of a particle, if the total force on the particle is 0, then the acceleration should be 0, and vice versa also. This, if acceleration is 0, right, if acceleration of a particle is 0, then according to Newton's first law, you can always say that the net force acting on the particle is 0. So both ways, both ways. So that is Newton's first law. Let's first talk of this, Newton's first law. No force, no acceleration. That's Newton's first law. But that is not always true. That is not always true. If I am in a rotating frame, or let's say I am in a car, accelerating car. So if I am in an accelerating car, right, it is accelerating, and I am sitting here, somewhere here on the seat, okay. So I am sitting here, and then from the car's body some pendulum is hanging, right, some pendulum is hanging. What I see that the pendulum, the string does not stay vertical, it makes some angle theta with the vertical, all right. Now if I think of this particle, this bob of the simple pendulum, what are the forces? The forces are its weight mg and then the tension T. These are the two forces, because force is always exerted by some object, right. Force is by some object on some other object. That is how the force is conceived. So the earth, which is attracting everything, so it's also attracting the bob, and that force is mg in the vertically downward direction. And then other than the earth, the only thing in contact is this string, and string always exerts force along its length. String always pulls, and therefore the force on this bob by the string is in this particular direction, along the string. There is no other object which exerts force on this, and these two forces are not equal and opposite, and they will not add to 0. So you have a net force. Force is not 0. But what I see, I see that it is at rest and it remains at rest. Okay, so the acceleration is 0. For this observer here, if he puts the origin here, x, y, z axis, no coordinate is changing with time. X coordinate doesn't change in time, y coordinate doesn't change in time, z coordinate does not change in time. So it is at rest, it remains at rest, acceleration is 0. So force is not 0, but acceleration is 0. So that means this rule that if force is 0, then the acceleration is 0, and if the force is not 0, then the acceleration is not 0, that rule doesn't hold here. And if you have a resultant of these two, and if you want to make force 0 and apply a force here, you apply a force here, you pull it, you hold the bob and pull it. Why? I want to make the force 0. This tension here, this mg here is giving me some resultant, and I apply a force to make this force, total force 0. What will happen? What will happen? This bob will be accelerated towards me. If I pull it, the bob will be accelerated towards me. So F is 0, but A is not 0. Newton's first law is not valid in this frame. Or if I am in some kind of a rotating frame, I am on some disk, and there on the disk I have put my x, y, z axis, then also this does not hold. So Newton's first law is not a universal law as such, because we are always free to choose our frames of reference. Whatever is suitable for me, I will use that frame of reference. So for some frames of reference it holds, for some frames of reference it does not. So essentially what this Newton's first law is doing, it is defining or it is classifying that okay, there are at least some frames in which this holds, and we call them inertial frames of reference. We generally live on the earth. Whatever we do, our activities generally because the technology is advancing very fast and we are going to in spacecrafts to other places, the moon and Mars and all those things, but most of the time we are on the earth, and therefore a very suitable frame of reference is earth, and that is not inertial. That is not inertial. Now no one can compel me that no, don't use the lab frame, do not put your x, y, z axis in the lab, and you have to go for an inertial frame, first search it, put your x, y, z axis there, and then do all the physics, all the mechanics, all the dynamics. That is not the way science goes. So I am always free to choose my frame of reference, and if it suits me, I can use this frame or some other frame, whatever I like. So this Newton's first law is essentially, it defines. Fortunately, the Earth's frame of reference is close to inertial, although it is non-inertial, but it is very close to inertial. If you think of this condition that if f is 0, what will happen? The acceleration will be very small, exceedingly small. So we can take it as inertial frame of reference. And if the acceleration of some object is 0, how much is the force? In the frame of Earth, if I am there, how much is the force? How much the force needed to make the acceleration 0? That force is exceedingly small, and therefore we generally take Earth as an inertial frame of reference. But whenever we want to do some physics where the accuracy is important, and our instruments are sensitive enough to detect small changes in the motion, or we can measure very small forces, then yes, we do take care of the fact that Earth is not inertial. So this first law actually defines inertial frames of reference. And once the inertial frame of reference is defined from here, then we go to the second law. In an inertial frame, force on a particle, net force on a particle is equal to mass of the particle into acceleration of the particle. So many times people say that, okay, why first law? From the second law, put A equal to 0 here, F will be 0, and that is the first law. So first law can be derived from the second law. That's not very true, because this is also valid in an inertial frame. But what is inertial frame? That comes from the first law. So first law has its own independent significance, and once the inertial frame is taken from here, then we say that okay, in that inertial frame this will happen, and that is our Newton's second law. And then we have Newton's third law, which is very different from all this. It's called laws of motion. First law, second law, third law, these are called Newton's laws of motions. But the third law doesn't involve motion as such. So if I talk of third law, okay, and that says that force by particle 1 on particle 2 and force by particle 2 on particle 1 at any instant are equal in magnitude and opposite in direction. I have written a long statement of Newton's third law. Force by particle 1 on particle 2 and force by particle 2 on particle 1 at any instant are equal in magnitude and opposite in direction. Whereas the most popular version of Newton's third law is that action and reaction are equal in and opposite But that short, crisp, very simple, beautiful statement of Newton's third law, every action has an equal and opposite reaction, has caused a lot of confusion in the interpretation of Newton's third law, lot of confusions. So basically the content of Newton's third law is, if you have two objects and they are exerting forces on each other, remember, for any force you can ask these questions: which object has exerted this force? On which object this force is exerted? Okay, what is the magnitude, what is the direction? But basically from where the force is coming, so which object is exerting the force and on which object it is being exerted. So that's very, very important. So if you have two objects, one is exerting force on the other is also exerting force on the first one. So that is it, force by particle 1 on particle 2 and force by particle 2 on particle at any instant. This is also very, very important. In the action reaction statement, it appears that first some force was exerted, which is action, and then reaction also occurred. So it's in reaction to the first force, the second force is exerted. It's not that. It's at any instant, at one single instant, this is exerting force on that, at the same instant this is exerting force on this one. So which one is action and which one is reaction has no significance, absolutely no significance, because at any instant, at one particular instant, this object is exerting force on this and this object is exerting force on that, and the two are equal in magnitude and opposite in direction. So that is Newton's third law. The motion is not involved as such here, but how the forces are related. Here also there is yet another thing which we can add here in the Newton's third law, that and are these forces along the line joining the particles. This also you can add. If you have a particle here A, if you have a particle here B, the force by A on B and force by B on A at any given instant are equal in magnitude, opposite in direction, but that could have been this way. That could have been this way. The directions are opposite. The magnitudes are equal. So this statement is satisfied. But the other part which you can add is that no, the force is along, these forces are along the line joining these two particles. Okay. Now if that does not happen, maybe in some cases if it does not happen, then this part will not be valid. Now if you stop here, what is Newton's law? Force by particle 1 on particle 2 and force by particle 2 on particle 1 at any instant are equal in magnitude and opposite in direction. This, if you stop here, this is sometimes called weak form of Newton's third law, right? This is sometimes called weak form of Newton's third law. And when you add this also, that the two forces are along the line joining the particles, this is sometimes called strong form of Newton's third law. Okay, so we will stop here and we will talk further on forces in the next lecture. So last time we talked about Newton's first law, second law, third law, which forms the basis of what we call Newtonian mechanics, and I stated Newton's first law and talked about it in the sense that it defines a class of frames of references which we call inertial frames of reference. So first law is basically related to identification of inertial frames of reference. If you have a reference frame, you have XYZ axis given, you have clock given to measure time, and then you do dynamics of the particle here and there and look at the forces and look at the motion of the particle, you will find, if you have chosen inertial frame, then you will find that yes, if I don't apply any force or the net resultant force on a particle is 0, then the particle remains unaccelerated. If it is at rest, it remains at rest. If it is moving, it keeps moving with uniform velocity. So, these things we know from our schools, but the proper interpretation of Newton's law in this particular fashion, it is sometimes not done at a lower level. And once the inertial frame is defined, then comes Newton's second law, that in such frames, if you do apply a force, what happens? And that tells that yes, an acceleration will be produced. This is up to say first law, but then it is proportional to the acceleration, or it is product of mass and acceleration, or it is proportional to mass into acceleration, and the proportionality constant is taken as 1. We define units of force in that particular fashion. So, those things come after we have defined that inertial frame from the first law. And then the third law is that action reaction, which is really very difficult to practice, but then if you think in terms of forces, not force, forces, because you have two objects, one applies force on the second and the second also applies force on the first. They are equal and opposite, that is the weak form of Newton's third law, and then they are also along the line joining, that we call strong form of the Newton's third law. So, first let me talk of particle dynamics. That means I have just one particle, and then there are forces on it. Externally we are applying forces. So, dynamics of a particle. When I call particle, which particle or how big is the particle? We do not, generally we will not talk in terms of atomic or subatomic particles. Generally we will be talking of bigger particles, say at least micrometer type or millimeter type or centimeter type or meter type or kilometer type planets. So, those things we can do, but the particles means that now I am not interested in the inner structure of that particle. For me it is just one point, right. So, that is how we define our particle. It may be an extended body, but if all parts of the extended body move with the same velocity at particular instant, as time passes the velocity can change, the whole thing can be treated as a particle. So, it is not only just size, it is basically this, that if I am not interested in the internal structure, parts, how parts are moving or what parts are doing, I am not interested in that, then the whole thing can be treated as a particle. But you conceive this idea, you have a small particle, and then we are doing dynamics of that. So, the basic equation is very simple, a force is equal to ma, and the stated problem of dynamics is that at a certain time you know the position of the particle, you know the velocity of the particle, and then as time passes you know at each instant what is the force on the particle, and then you have to predict that at a given later time where the particle will be and what will be its velocity. So, that is the problem. So, what is the problem? What is known at certain time, which we call t equal to 0. Remember, time has been flowing from time immortal and will keep flowing. So, if you say t equal to 0, you have chosen some instant and you are calling it t equal to 0. So, it is our definition of t equal to 0, right. So, in some questions if you get to negative value of t, that does not mean that it is unacceptable, it is unphysical. It is before that instant which you call t equal to 0. Before that also the motion was there, the particle was there, the forces were there, and everything was there. So, if you are getting in some question, you solve it and you get t as negative, that does not mean that it is unphysical. It only tells that you have taken a particular instant as t equal to 0, and this result pertains to time before that. Okay. Nevertheless, at some instant which we call t equal to 0, position and velocity of the particle is known. That is one thing, and then the force acting on the particle is also known. The force may be same at all later instants, or force may depend on where the particle is. If the particle has reached from here to there, the force is different. If it has gone somewhere else, the force is different. The force may be depending on the position of the particle, force may be depending on the velocity of the particle. If you throw something with high speed in air, the force by the air on that object, we generally call it a resistance, air resistance, depends on the velocity. Or the magnetic force, you know, depends on the velocity. Force may depend on the velocity, force may depend on time. So whatever, but it is known. It is known. So in that entire duration, it is known. So this is known, and what we wish to find, the position and velocity at all later times to find, and this is known. So that's basically the task of mechanics, at least when we do this particle dynamics. And the thing is very, very simple. You have F is equal to mass times acceleration. Remember, mass times acceleration is not the force. It is product of two quantities, mass of the particle and acceleration of the particle. This is equal to the force applied. F is equal to ma. So this is force, this is not force. It has units of force, it has dimensions of force, but this is not force. This is product of mass and acceleration. Okay, so you can, and this is known. This is known. So you have acceleration is F by m. Mass of the particle is supposedly known. So you write this as second derivative of position vector d2r dt square, that is equal to F by m. If you write in the component forms, Cartesian component forms, you have three equations. d2x dt square is equal to fx by m. Then d2y dt square is fy by m, and d2z dt square is equal to fz by m. You can also use other types of coordinate system other than Cartesian, then the equations will be different, but you will have three equations. So this vector equation is a combination of three equations, and each of this fx, fy, fz can be function of space point or function of time or both. So this may be some function of xyz, some function of xyz, some function of xyz, can also be time, but we will first deal with the forces which depend on the position of the particle. Just like if you have a pendulum, then whatever time, if the pendulum is here, you have a particular force. If the pendulum is here, you have a particular force. Pendulum is here, you have particular force. So it depends on the space position and position of the particle, and therefore it can be a function of xyz, it can be a function of xyz, this can be a function of xyz. If it so happens that it does not depend on xyz or t, it is constant, or during the entire motion of the particle we are interested in, this force is constant, then the life is very, very simple. d2x dt square is equal to a known function fx by m. This is constant, right? We start with constant force. So this fx by m is constant. So that is this. And then you can always integrate it. dx dt is equal to, this is one integration, so f into t and plus some constant c1, and then again integrated, x is equal to half ft square and plus c1t and plus c2. And this is the acceleration, which is constant, which is known because it is f divided by m. So if you write it as ax, this fx by m, if you write it ax, your x is equal to half at square plus c1t plus c2, and these two constants are not known as such with this much of information. So what you need is at t equal to 0, that means at some instant I know the position and I know the velocity, and I am calling that as t equal to 0. So what is known as x at time t equal to 0, that is known. I can call this position as x equal to 0. Okay, so that is a standard way. If you say that this position I have chosen to be the origin, so here x is equal to 0, y equal to 0 and z is equal to 0. Just as you can choose a particular instant as t equal to 0, you can choose a particular space point as the origin, x equal to 0, y equal to 0, z is equal to 0. So if you have chosen this particular position at t equal to 0 to be 0, you can put it here. What do you get? 0 is equal to, t is equal to 0. So this is 0, this is 0, c2. So c2 is 0. So you have x is equal to half at square and plus c1t. So you get the value of one constant, but one constant still remains and one information still remains, because not only position, I also know the velocity, and velocity is here, velocity is here, dx dt. So at t equal to 0, if the velocity is known and if I call that velocity as u, small u, then what I get? If I use this, this is my Vx. So if I use this information that at t equal to 0, at t equal to 0, the velocity or the x component of velocity at t equal to 0 is known, and I call it ux. Then I can use this equation, ux is equal to, and put t equal to 0, ux is equal to c1. So if I put it here, this gives me ux is equal to c1. So the c1 is that x component of the velocity at t equal to 0, and you put it here and you get your very well known equation, x is uxt plus half axt square, and same is the story for y and z components. So uit plus half ayt square, and z is equal to uzt and plus half azt square. So if you know the force, and force happens to be same at all positions at all time, so this is constant, this is ax, this is ay, and this is az, and they are all known, then you can immediately write what is x, y, z at a later time t, and from here you can write what is the, so Vx is equal to c1 is ux, and this is ax. So all those equations that you learned in the first chapter of your high school book in mechanics, so all those things can be found from here. So in principle the task is over, right, if it is constant. If it is not constant, then there are techniques. If you have this kind of equation, but then this depends on x, or it depends on y, it depends on z, or it depends on time, then you have techniques of integrations, and from there you will rederive the corresponding equations which will depend on how this fx, fy, fz are depending on x, y, z or time. So those methods can be applied. Finally you can get x, y, z, finally you can get vx, vy, vz. So vx is this, vy is this, and vz is this, right? But we will be talking more about some parameters which are associated, like linear momentum, angular momentum, energy, which will be useful for our system of particles, which will be useful for rigid bodies, and which will also be useful in many cases for a single particle. So let me talk about those quantities, or those physical quantities. So one very important parameter in Newtonian mechanics is linear momentum of the system you are studying. It may be a single particle or a system of particles, rigid body, whatever. Linear momentum. Linear momentum. To start with, I will be talking of a particle, single particle. I am talking of single particle system. So linear momentum, and we define linear momentum as p is equal to mass times velocity. No fantasy, nothing special. This quantity is defined as linear momentum. It's by definition. This is the definition. This quantity is called linear momentum. Mass of the particle into velocity of the particle is called linear momentum of the particle. And then Newton's law, force on the particle is equal to mass of the particle into acceleration. So this we can recast in terms of this. If I take dp dt, or from here also I can go, let's go from here. This is m into dv dt. Rate of change of velocity is acceleration, again by definition, right? There is no physics involved here. We define this rate of change of velocity as acceleration. So it is this. If mass is constant, I can take it inside. So it is d dt of mv, and mv is p, so it is dp dt. So force on a particle is equal to rate of change of momentum of the particle. Actually Newton described second law in terms of rate of change of momentum only. The words used were in Principia were very different, but essentially the force and this rate of change of momentum, they are proportional. That is how Newton's started, and then from here we go to this F equal to ma. So this is about force and P, and if this force is 0, force on the particle is 0, dp dt is 0, right? dp dt is 0, and that means P is constant, linear momentum is constant. Obvious, nothing to be derived mathematically. Obvious, if force is 0, there is no acceleration. If there is no acceleration, there is no change in velocity, and if there is no change in velocity, and mass is anyway in Newtonian mechanics we take the mass of the particle as constant, no change in p. So, p is constant. So, if a force is 0, then linear momentum is constant, and we will see that when we talk about system of particles or extended bodies which can rotate and other things, we will see that this translates to a very important law of physics which is called conservation of linear momentum. If the total external force on a system is 0, then the linear momentum of the entire system that remains constant. It's different from this. So far I am not talking of external internal forces. It is one particle and I am absolutely not interested in what is going inside. So any force on this is external. Okay. So that's why I am not talking of that word external force so far. But once you go to a system of particles where different parts of the system can exert forces on each other, then those forces are called internal forces, and any force which is coming from something other than this system, that will be external force. And conservation of linear momentum is essentially, if the external force on a system is 0, the total momentum of that system is constant. And if your system is just one particle and everything is external, all forces are external anyway if you call it a particle, then of course that same principle tells that if f is 0, then p is constant. So that is about linear momentum, and we will be using this conservation of linear momentum extensively when we talk of system of particles, collision of two particles, and all those things. Okay. The other concept is related to the force itself. Okay. If you have a force which depends on a space point x, y, z, force is a function of x, y, z. So you have f, and that f is a function of space point. I am using Cartesian coordinates. If convenient, we can also use, depending on what problem is at hand, other coordinate systems, but let us describe our theory in terms of Cartesian coordinates. So if a force depends on a space point, then you think of this quantity. I have a point x, y, z. I have some frame of reference, some origin, some axis, some y axis, some z axis, and with reference to that I have a point x, y, z. Then nearby I take another point, nearby, and this is x plus dx, y plus dy, z plus dz, and this vector I call dr vector or dl vector. Okay, we call it dl. People also call it dr vector. I can also take dr vector, and then this is a small line segment. So we assume that the variation of x within this is infinitesimally small. That is how calculus works. Okay, if it is infinitesimal lengths, if this displacement is infinitesimal, if this dx, dy, dz are infinitesimals, then I need not worry whether force at this point, this point, this point, they vary. I am not worried about that because it is so small. So whatever is the force here, I can take that as f, and this is dl. You construct this quantity f dot dl, and you can take a curve. You can take some curve. Let me take the curve somewhere here, and here is a point which is, we will call it r1. This vector is r1, and another point we call this vector as r2. So now I am going from here to here, big distance, not infinitesimal, big distance. I am going from here to here. I can add all these quantities, f dl here, f dl here, f dl here, f dl here. This quantity I can add, take infinitesimal lengths and then construct this and add all that, and that will be f dot dl. From r1 to r2 along that path given, along the path given, because this dl, 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 I have to take this dl, then 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 this dl, this dl. If I take another path here from the same point r1 to r2, then I will be taking this dl, then this dl, then this dl, then this dl, then this dl, and so on. So it is different, right? It is different. So f dot dl along this path may or may not be equal to f dot dl along this path. Okay, and this plays a very important role. Whether this integral depends only on these two positions, or it also depends on the particular path I have taken. that distinguishes forces into categories. One we call conservative forces, other we call non-conservative forces. So we will start from here next time. So we talked about a single particle on which a force acts and the particle moves in certain path, and we defined a quantity f dot dl. So if the particle is here at a certain time and then it moves to a nearby point which we call dl vector, this is the displacement in this small time, and during this the force acting on the particle is some f. So you can ask what is f dot dl, and you know essentially this is called work done by the force during this displacement, f dot dl. If the force acting on the particle is f and the displacement of the particle is dl, small displacement, infinitesimal displacement, so that we don't have to worry about variation of this f during this displacement and change in direction of the particle during this displacement. So we do not have to worry about those things. This quantity is also called work done by the force during this displacement. Now the important point was that if I take a finite displacement, if I take a finite time in which this particle goes from here to say somewhere here, and this is b, and I can ask what is the total value of sum of this f dot dl on this path, on this path, on this path, on this path, on this path. I mean, I go along with the particle, I take each small infinitesimal part here, calculate this f dot dl and do it for the entire path from a to b, and then sum all these things. This we call integration. But we will not write a here and b here from a to b, because this particular path is also important. I can also go along some other path and still reach here, and I can ask what is f dot dl here, 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 and so on. An entire path you do this f dot dl and reach L, and these may or may not be equal. So we say that it is on path 1, certain path is to be specified on which path I have to calculate all these things. So this is path 1, let us say this is path 1, this is path 2. There may be infinite such paths connecting A and B. Now there are two possible situations. One is same for all paths connecting A and B. The end points must be same. We start at A and we finally stop our this integration or this addition at B. So if it is same for all paths, such forces are called conservative forces. Force is conservative. And remember, even if there is no particle going on the path, but I know that if a particle is here, this will be the force on it. If a particle is here, this will be the force on it. If the particle is here, the force will be this. If the particle is here, the force is this. Even then I can calculate this quantity f dot dl. dl need not be the actual displacement of the particle. I can just draw a path and then construct, okay, here this is the dl, this is dl, here this is dl. I can construct all these dl's along the path, and I know that if the particle is here, this will be the force. If the particle is here, this will be the force. I can calculate this f dot dl. So whether the force is conservative or not, for that I need not have the physical particle. The force by itself, I can say that it is conservative or it is non-conservative, and if it is not, then it is non-conservative, right? If it is not same for all paths, remember all, it may be same for 10 different paths, it may be same for 10 different paths, but for 11th part if it is different, then this condition will apply, this condition will not. So this is called non-conservative. We say that force is non-conservative. Okay. Now if the force is conservative, and then you take a closed loop, that means I start from a point A and go round somewhere on some path and reach once again A. That means A and B are the same. You start at A, do this f dot dl here, do this f dot dl here, do this f dot dl here and here and here and here and here and here and here. Stop adding here. It's a closed loop. What we can do? We can take some point B somewhere on this path, and then this f dot dl, this let's call it path 1 and this is path 2. So this f dot dl on path 1, and now the path is, path 1 means you are going from A and stopping at B, and path 2 means you start at A and stop at B. So connecting the same points A and B. So this should be equal to f dot dl on path 2, conservative force. We assume that we are talking of a conservative force. In that case, these two paths are same. Now if I invert the arrows of this path 2 everywhere, what will happen? Each f dot dl will become negative of itself, right? Because here, what is the force? That is fixed, that you don't have any control on that. If the particle is here, this will be the force. But dl, it's up to you. You can take this as dl or you can take this as dl. So if you invert all these arrows here and make it like this, make it like this, what will happen? What will happen? Now it is the other side, is the other way. This is f dot dl, and let me call it path 3. Remember, now path 3 starts at B and ends at A, because these are the kind of dl we are taking. So this is path 3, which is different. Starts at B and then it goes this way, this way, this way, this way, this way, and reaches here. And path 2 is, starts from here on that same geometrical line, it goes this way, 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 and reaches here. Every dl becomes minus dl, and therefore these two are negative of each other. Now bring this thing here. So you have f dot dl on path 1 plus f dot dl on path 3 equal to 0. And what is this? Path 1 and then path 3, and you are adding. Path 1 means you are going from A to B along this line and reaching here, and then path 3 means you are going from B to A along this line and reaching here. So you are going on a closed loop. You start at A and you again reach at A after going through this closed loop. So this whole thing is f dot dl on a closed loop, and for that we put a circle here to tell that it is a closed loop, and this is 0. Valid for all closed loops. So this can be taken as another identifying equation whether the force is conservative or not. If this f dot dl integration, line integration, is 0 on all possible closed loops, the force is conservative. And if there is some closed loop on which it is not 0, then it is non-conservative. And this is also equivalent to, this equation is also equivalent to, some mathematics is needed. What do you say? Point by point, curl of the force is equal to 0. The symbol is read as curl of f. What is that? What is that curl of? Essentially, if I am using Cartesian coordinates, your f is a function of x, y, z, and that means fx is a function of x, y, z, fy is a function of x, y, z, and fz is a function of x, y, z. And now you construct this quantity. It is determinant. I am writing I cap here, j cap here, k cap here, then del del x here, del del y here, and del del z here, and fx here, and fy here, and fz here. You know determinant, how to open up a determinant. So you write this this element here, I cap, and then in algebra, this multiplied by this minus this multiplied by this. Here it will be del del y of fz minus del del z of fy. So you will write del fz del y and minus del del z of fy. And then similarly you do for j cap part and you do for k cap part. Just as in algebra, you open up this determinant and write the expression. What is this? Fz. Fz is a function of x, y, z. Now differentiate with respect to y and treat any x and z coming in this expression as constant during this differentiation. This is called partial differentiation, partial derivative. Similarly here, fy is a function of x, y, z and differentiate with respect to z. So in this expression, differentiate with respect to z and treat any x and y coming in the expression as constant. Similarly, you will have two partial derivatives here and two partial derivatives here. This quantity is called, it's a vector quantity, remember. So you have I cap here, j cap here, k cap here. So this is a vector quantity, and that vector quantity is called curl of f. So if all these are 0, this is 0, this is 0, this is 0, then your force will be conservative. If curl of f is 0, the force is conservative. In this definition, how many closed paths you will check? It may be 0 on 10 different closed paths, but then on 11th it may not be 0. How many closed paths you can check, or how many different paths between the same 2 points you can check? But here it's very foolproof. If you know the force, expression of force in terms of x, y, z, do this operation, and if that turns out to be 0, there is no path and closed or open or this point and that point. If for every x, y, z this is 0, and the expression itself will tell whether it is 0 or not, the force is conservative or non-conservative, you can decide from here. So this is another way of telling that a force is conservative. For a conservative force, curl of f is 0 at all points. For a conservative force, this integral f dot dl on a closed path is 0 for all paths, all closed paths, or between the same 2 points, this integration is same for all paths. So these are the ways in which you can identify whether the force is conservative or not. Why do we say that the force is conservative? If something of this kind happens, why is the name, what is conserved, why it is called conservative? So that is on the next board. Now if the force is conservative, I take the first definition. You have 2 points A and B, and you say that this integration f dot dl on this path is independent of the path and only depends on the endpoints A and B. If this is the case, it is always possible to define a scalar function. Remember, this is a scalar, this is a dot product, and then you are adding. So it's always possible to define a scalar function which we will call v xyz. So for each point I have defined a particular v. At different points you can have different values of this v. So you can, it is always possible. So it is always possible to define a scalar function v such that, right, such that this integration f dot dl, now that it is independent of path, I can write a here and b here. I have to go from a to b, whatever path. So I can write a and b, a to b, f dot dl, whatever path you want to choose, you can choose, it doesn't matter. So this quantity is equal to v at b and minus v at a, and for some reasons I write it with a minus sign. Okay, so once you ensure me that this f dot dl integration between two given points a and b is independent of path, I can always come up with certain functional form of a scalar function v x y z, so that this integration will be equal to the value of this v at this point b and value of this b at this point a. It's always possible to do that. Okay, and then if this is the case, so this is va and minus vb. Now let me do a separate algebra and come out with a different result. What is that? Now I am bringing a particle of mass m. I am bringing a particle of mass m on which this force is acting, and this is the only force acting on the particle. Okay, so this is the resultant force. So F is the resultant force on a particle of mass m, let us say. What is this f dot dr? F dot dl. What is this f dot dl? This f dot dl you can write as mass times dv dt, mass times acceleration, because this is the resultant force, so I can use Newton's second law. F is equal to m times a, m dv dt, and then dot dl, and this dt can go here, and this you can write as m dv, and then dot dl dt, and dl dt is v. Okay, in time dt, if the displacement is dl, then the velocity at that point is just this v, and this is half d, or let me write half also inside, d of half m speed square v square. How do I write that? Go in the reverse way. What is half mv square? Half mv square, this is a scalar quantity here, this is also scalar quantity, but in terms of two vector quantities, v vector and dv vector. So how do I come to this speed square here from this vector thing? So this you can write as half m v dot v, and then you differentiate d of this, this will be half m, and then d of this. How do I do d of this? Product of two functions, keep one function and differentiate the other one, so v dot dv, then keep the second function fixed and differentiate the first one, so this is dv and then dot v. Okay, so just that differentiation of products of two functions, keep one, differentiate other, then keep the second one and differentiate the first one. So I am keeping this and differentiating this, here I am keeping that and differentiating this, so this is this. So it is 2 times v dv dot v, and that 2 cancels with here, and you have m and v dot dv or dv dot v. So that is here, m dv dot v is equal to d of half mv square. Now integrate f dot dl, on that path a to b, this is equal to integration d of half mv square, a to b, and integration of dx is just x, integration of d theta is just theta, so integration of this will be just half mv square, so it is half mv square, and then you put the limits, the lower limit here, the upper limit here, so it is half m v square at b and minus half mv square at a, and that is kinetic energy at b and minus kinetic energy at a. So if you have a particle on which this conservative force F is acting, then this F dot dl integration from A to B is equal to change in kinetic energy at B and minus kinetic energy of at A. But the same integration, I said that I can find certainly I can find a function V which satisfies this equation. So F dot dl integration A to B is VA minus VB. If the force is conservative, I can do that. This depends only on A and B, not on the path. This depends only on A and B, not on the path. So since the same integration is written in two fashions, one is here, other is here, they should be equal. So VA minus VB should be equal to KB minus KA. VA minus VB should be equal to KB and minus KA, and that means VA plus KA is equal to VB and plus KB. Now this we name as potential energy of the particle when it is at A, and this is potential energy of the particle when it is B. This V function at x, y, z is named as potential energy of the particle when it is at that x, y, z. And this potential energy plus kinetic energy is called mechanical energy. And if I denote it by some other symbol u, which is once again function of x, y, z, which may be a function of x, y, z, then you have this u at A is equal to u at B. So you go from here to here. your kinetic energy is changing. But if you term this as a potential energy and add to that, the total mechanical energy does not depend on x, y, z. It is same at this point and at that point. So this is known as conservation of energy. In mechanics, this is known as conservation, principle of conservation of energy. And that is why the name conservative force. Only conservative forces will allow you to define a potential energy, and only then the total mechanical energy will be constant. Now, let me take some examples and then some more questions and discussions on that. Let us take an example of spring force. You have all studied simple harmonic motion, and if you have a particle connected to a spring and one end of the spring is fixed and the equilibrium position where the spring is relaxed, we take that x equal to 0 and then we pull it, release, and it oscillates, and we say that the force is minus k times x, which you also write as minus m omega square times x, and omega is written for square root of k by m. I am not going into great details because you have all studied this motion, very important and very interesting also. But let us go to the energy. Do I have something like Vx? The entire motion is on x axis. So do we have some function like this? Yes, we do have. It is half kx square or half m omega square x square. This is a function, and the energy of this particle with this kind of force is kinetic energy, which is half mv square and then plus half m omega square x square. And if the particle is at its extreme position, you know, the particle oscillates. If this is the kind of system, and then you pull it and then release it from here, it oscillates, and at extreme points the velocity is 0. That is why it is extreme, and therefore at extreme point at say x is equal to capital A, which is the amplitude, this E is equal to velocity is 0. So this part is 0, and you have half m omega square and capital A square. X is capital A, and if you write it here, equal to half m omega square A square, you can write what is V. So this half goes, half goes, half goes, m goes, and m goes. So you can write what is this V square. This V square is equal to this omega square is here, omega square is here, and then you have A square and minus x square. So take square root, dx dt is equal to omega square root A square minus x square, and now it is very simple. Dx by this, dx divided by square root A square minus x square is equal to dx divided by this is equal to omega dt, and you can integrate it very easily, right? You can integrate it very easily. What is that? This is sine inverse of x by A is equal to omega t plus some integration constant, and that tells you x is equal to capital A sine omega t plus epsilon. So this conservation of energy principle is a quite useful principle. You can see how easily I can get that displacement as a function of time, speed as a function of time, everything, v as a function of x, all those things we get from here. If we start from here and write this as m times d2x dt square, we have to do a greater algebra to reach this point. So there are many other applications of this conservation principle and the concept of potential energy. So we will talk more about the concept of potential energy in the next lecture. So we talked about potential energy. If the force acting on the particle is conservative, the resultant force, the only force, then we can define this potential energy function V, and then V plus kinetic energy, this is constant. We call it law of or principle of conservation of energy. And how we define this V? Remember that F dot dl, integration from a point A to B. Now I can talk in terms of point A to B, because this is conservative force and path is not important, only the end points are important. This we define as V1 or VA minus VB. So if you have just a small displacement dl, you can say this F dot dl is small change in the potential energy, and that is here minus dV, because it is initial minus final, not final minus initial. So it is minus of a small change in potential energy, and this is it. Now this gives me another beautiful equation. If I write in component form, this will be Fx and dl is dx. So dl you can write as dx I cap plus dy j cap plus dz k cap, and f you can write as fx I cap plus fy j cap plus fz k cap, and if you take the dot product, it is fx dx plus fy dy plus fz dz. So this is fx dx plus fy dy plus fz dz, this is dv. Now if you take this y and z as constant which do not change, only x changes, then you have fx dx is equal to dv. That means fx is minus dv by dx minus, this is this minus here. Fx is minus dv dx provided dy is 0, provided dz is 0, y is constant, z is constant, and that is the partial derivative of v with respect to x. So fx from this equation is minus del v del x, and similarly fy is minus del v del y, and fz is minus del v del z. So if the potential energy function is known as a function of x, y, z, I can get the force components, and if the force is known as a function of x, y, z, then I can construct this potential energy function. Since only the difference is defined, so it will be arbitrary to the addition of some constant energy. So with that much of uncertainty which you have to choose, where you take potential energy to be 0, you get this V from F and F from V. So these are the things. You can take some more examples. Say U is equal to half kx square, not U, V. V is equal to half kx square, one dimensional motion. Entire motion is on the x axis. So one dimensional motion, and if this is the case, then you know when it occurs. It occurs in your simple harmonic oscillations. Just in the previous lecture we talked about that. F is equal to minus kx. Okay, so if you plot this V as a function of x, x can be positive, x can be negative. So if you plot this V as a function of x, it will be a parabola. It will be a parabolic function, half kx square. So from this diagram you can work out, if you take the particle is here at this point, at this x, this is the origin. So if the particle is here, then the corresponding potential energy is here. This is the point on the curve. This is the point on the curve. And here if you draw a tangent, the slope of this is del v del x, which in this case is dv dx, and therefore your force is all one dimension, so fx is same as f, so that is minus of this dv dx, and that is minus of this tan theta. So from this diagram also it comes out that if the particle is here on the positive side of the origin, then the slope is positive, this angle is less than 90 degree acute angle, slope is positive, tan theta is positive, and force is negative, so force is towards the origin. Whereas if the particle is here and if you draw the tangent, then the tangent is like this angle is more than 90 degree obtuse angle, and the value of tan theta will be negative, and therefore the value of x will be positive. So if the particle is somewhere here, then the force is positive, tan theta is negative, force is positive, so force is in this direction. So qualitatively many of the features come from this diagram, so the particle has to oscillate and all those. Then if you have a particular energy which is fixed, the total mechanical energy is fixed, and since this is in energy units, potential energy, so I can find on this line what is the total mechanical energy of the motion I am interested in. And if this is that point, if this is that total energy, u, this is that total energy u, then if I draw a line here, the total energy will always remain u, and if the particle is somewhere here, suppose the particle is somewhere here, then this is the potential energy, this much is the potential energy, this much is the potential energy, because this is the potential energy curve. So, as a function of x I am plotting potential energy. So, at this value of x, this is the potential energy and this is the total energy. So, this is kinetic energy, this much is kinetic energy, and kinetic energy plus potential energy is the total mechanical energy. So, now you can see if the particle is moving away from the origin, the potential energy is increasing, the kinetic energy is decreasing, the totals remains u. And if the particle reaches this point, this particular point here, call it x equal to a, what happens? This is the potential energy and this is also equal to the total energy, mechanical energy, and therefore the kinetic energy is 0. So, the particle comes to rest at this position, the kinetic energy is decreasing, here this much was kinetic energy, then as it moved to the right, kinetic energy decreased, further decreased, and finally it became 0. So, the particle is going away, slowing down, and then it comes to rest, and then it turns back because the force is there. So, this is the turning point, this is turning point. From here the particle has to turn, and once it turns, it comes towards the origin, kinetic energy keeps on increasing. Here the kinetic energy is same as the potential energy, so the same as the total mechanical energy, and so the potential energy is 0. But then since it has kinetic energy, it is moving towards left, it keeps moving towards left, it reaches somewhere here, then somewhere here, then somewhere here, and finally at this place which is minus a, when it reaches here, once again the kinetic energy is 0. So, this is also turning point. So, these kind of analysis you can do once you know the shape of this potential energy curve. Many of the qualitative features of the motion you can derive from this. Let me take one more example. Suppose you have a proton, and you have another proton, and suppose this proton is somehow fixed, this proton is fixed and this can move, and suppose this is moving, this distance is large and it's moving towards this first proton like that. It has some velocity v here, v naught here, and this distance is quite large, As a function of distance, what is the potential energy? You know that, right? If you have two charges q1, q2, the corresponding potential energy is q1, q2 divided by 4 pi epsilon naught r. So, v is equal to, let me say this is all x axis, the entire motion is on x axis. So, it is right heading towards this proton, and this I am taking as x axis. So, it will be proton q1, q2 by 4 pi epsilon naught and then x plus positive, both are protons. This is the potential energy as a function of x. If you plot, what happens? If you plot, it will be a hyperbolic curve. And then initially it is at a large distance, and then the speed is v naught. So, initially whatever you call t equal to 0 or so, initially r is or x is large, very large, and the kinetic energy k is half m v naught square, and this is also the total energy, because for large x this potential energy is tending towards 0. So, this is the total energy known, suppose it is known, and that total energy is somewhere here, let us say this is that total energy, and initially x is very large, that means the particle is somewhere here at a large x, but the total energy is this much. If the particle is here, the potential energy is almost 0 and kinetic energy is, so this much is the kinetic energy and also total mechanical energy. Now, the particle is coming towards this proton, so x is decreasing. So, x is decreasing, particle comes here, suppose it has come here. When the particle is here, then this is the potential energy, that's the curve I have drawn, potential energy versus x. So, this is potential energy, total energy is fixed, and therefore kinetic energy is this much is the kinetic energy, decreased, right, because it is repelling. So the speed will decrease, kinetic energy will decrease, kinetic energy is decreasing, 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 and the particle comes here, some x naught, and then you are on the curve, you are reaching this point. So the entire energy is potential energy, the kinetic energy is 0. This is turning point. The proton turns from here. So it comes, and at some x naught it turns. And once it turns, that's it. There is only one turning point. It will not turn again. It will go to infinity. Now this description is relevant for fusion in sun. Fusion in sun. You can set up your coordinate system with origin here and then do some algebra. It's almost the same problem. In this particular frame, it is moving only in x direction. This is at rest, so almost similar. Mass you have to, if you want to do real quantitative analysis, then you have to do something else, because it is a non-inertial frame, remember, if you put your origin here. So we will take care of that, but essentially this is the case. The separation between the proton will be having a value x naught, which will depend on the initial kinetic energy. Now in sun the temperature is some 10 to the power 7 Kelvin or so, of that order, and you can assume that all the protons are moving with some thermal energies, and that also you know the random motion 3 kT by m square root, that is the square root RMS value of the speed, and if you calculate this you get some value, and with that value you can calculate how much should be the x naught. Different protons are of course moving with different velocities. But this is the average kind of thing, some kind of root mean square. So if you take this as the velocity, calculate the kinetic energy, and find this x naught here, that x naught turns out to be some few hundred femtometers, say 300 femtometers. Okay, the story is that this is not a complete picture, because protons also exert nuclear forces which come into play once the separation is of the order of femtometers. So on this scale, I don't know where will be the femtometer. Suppose this is femtometer, 2-3 femtometers. So if you are inside this, if the separation is in femtometer range, then on top of this Coulomb potential energy, you also have potential energy corresponding to that attraction, nuclear attraction, and that's very, very strong in femtometer region. So this curve actually goes like this. Okay, so this is the nuclear attraction range where the potential energy has sharply gone down. The Coulomb potential energy is increasing, but it is sharply going down, and it overtakes this Coulomb energy, and final potential energy is of this type. So if proton and proton are to fuse, fusion reaction is to take place in the core of the sun. The first thing is that two protons should fuse, and after that more protons will add to make a helium nucleus. But the first stage where proton and proton have to fuse, it must come closer to this separation. Okay, so it must reach somewhere here. But then x naught is 300 femtometer, and this is 1 or 2 or 3 femtometers. So this is 300 femtometers. Okay, so even if you say that you have some protons which are of higher than this, having speed higher than this RMS, which we calculate from here, even then you don't have enough protons to reach here, fuse, and give that wonderful energy that we receive from the sun. So then there are some other phenomena, barrier tunneling and all those things, quantum mechanical phenomena, which finally gives us required number of protons actually reaching here and then fusing and creating that energy of the sun. Okay, so these are the things that you can do with potential energy. We will come across such things again and again. And now I want to introduce another parameter. So we talked of linear momentum, we talked of potential energy, and then from there this total mechanical energy, kinetic energy. Another parameter which is important in mechanics, and that is angular momentum. So when we say angular momentum, generally what comes to your mind is something is rotating, and angular momentum should be some moment of inertia times angular velocity. So it should be a rigid body or an extended body. But even for a single particle, this angular momentum concept is very useful. Let's see how. Angular momentum is basically angular momentum is defined for a particle only. And if you have extended bodies, then you add angular momentum of all those particles to get the total angular momentum. But the basic definition is for a particle. And what is that? The first thing is this angular momentum of a particle about a given point, which I will call origin. So the angular momentum of a particle is also associated with which point you are talking of. Particle may be somewhere else, but this point is you have to choose somewhere. Okay. So for linear momentum, it doesn't matter where you have taken your origin or what. It is mass of the particle, velocity of the particle, local phenomena. But angular momentum, particle is needed. The parameters of particles are needed, we will just see, and then the origin or the point about which this angular momentum is to be calculated. So definition includes this point, and that is given by, we write it L with a vector sign. This is a vector quantity, and this is r vector cross p vector. What is r vector? It is the position vector of the particle from the chosen origin, this point, this given point, from that given point. And P is the linear momentum of the particle. So if you have an origin, if this is that point, and then at certain instant you have a particle of mass m and is moving in some direction, say this direction, this particle of mass m is moving in this direction with a speed v, the angular momentum of this particle at this instant about this point, always whenever there is an angular momentum, which point, about which point, so that should be known, and that is from this origin you join that particle, okay, call that vector as vector r, construct this mass times velocity here, and then take cross product of these two. In this diagram, if this is x axis, this is y axis, then this r cross p, p will be in this direction, will be going into the board minus z direction. So angular momentum is a vector quantity, it has a magnitude, it has a direction, and the direction is perpendicular to this r vector and perpendicular to this linear momentum vector. So that is angular momentum defined about that particular point. Okay. Correspondingly, and the magnitude of course is mass times velocity, and this distance r, m, v, r, and then the angle sine of the angle between two. So this is r vector, this is that p vector, this angle is theta, so sine of theta, r, magnitude of this r vector, magnitude of this momentum, linear momentum vector, and then multiplied by sine theta, that is the magnitude. Correspondingly, there is a similar quantity or similar looking quantity that also we define, torque of a force. Once again about a given point. Which we will take as the origin. And that is written as tau vector, we read it tau, T-A-U, Greek letter, tau, and then the vector sign is equal to r cross f. And once again, F is the force, you want torque of a force, so where is that force? It is here. And about a given point, so you have a given point. And from that given point to the point of application of force, force is acting on some particle, so position vector of that particle or position vector of application of this force, so that is known as torque. Once again the similar story, it will be perpendicular to this r vector, it will be perpendicular to this f vector, and along that perpendicular, this side or that side will be decided by the rules of a cross product. You know how to get the direction of this cross product, and the magnitude will be once again r into f into sine theta, similar picture here. So that we define as torque. And very interestingly, if you use this L is equal to r cross p and differentiate with respect to time, dl dt, that will be r cross dp dt and plus dr dt cross p. Now dr dt is velocity vector and this p is mass times velocity vector, cross product is 0, and this is dp dt is f, so it is r cross f. That means torque is equal to dl dt. For a single particle we get this equation, very simple equation, torque is dl dt. If you have a single particle, some force F is acting on it, you have chosen an origin, and from that origin you are calculating angular momentum as a function of time. The particle is moving here, there, so the position vector is changing, speed is changing, direction of the velocity may be changing. Calculate how much is this dl dt, that must be equal to that r cross f, which is torque. So we will take from here. So I had introduced the concept of angular momentum, and even for a single particle this is a useful concept. Together with linear momentum and energy, angular momentum is another physical quantity which is very useful in dynamics. How do we define that? We define angular momentum L of a particle and about an origin. These things are important. About a chosen point which we call origin, and the definition is this L is equal to r cross p. What does that mean? You have an axis system, you have an origin, you have the particle somewhere here, and then the particle may be moving in some direction, its mass is m. At that instant, what is the position of the particle as seen from this origin, from this frame of reference? That is known as r vector, r, this r vector, and p is the linear momentum, the mass of the particle times this velocity. So that is it. And then similarly we define torque. This also on a particle. So these adjectives are important. Of a force, we call torque of a force, and force is acting on some particle, and once again about the origin. So this is important, and then we say that torque is r cross f. This r is same as this r. This is the position vector of the particle on which this force is acting, and this position vector is taken from the same origin, and then we call this torque about that point. And then you have a very simple relation that torque is equal to dl dt. dl dt, simple. L you know, so dl dt if you do, it will be differentiation of the first function cross the second function as such, and then first function as such, and differentiation of this second vector. Now it's important that the order is not changed. R first, P next, R first, P next, R first, P next. This order should not change. And then one sees that this is 0. This is 0. Why? This is parallel to velocity. This is velocity itself. So this is 0, and this is force. This is force, resultant force dp dt, and therefore this is equal to tau. Simple. Now let me take a very common example, simple example. A particle freely falling under gravity. So it is dropped. A particle is dropped, and then it falls. So it falls on a vertical line, and then it reaches ground. It reaches ground. So it is dropped from here, and we can take the origin right here, and then x-axis, y-axis, and z-axis. And if this time is t equal to 0, at certain time t, it will be here. So this is at time t, and this distance is half gt square. So if I ask what is the angular momentum of this particle at time t, so L at time t, this is r cross p. Now what is r vector? Here is the origin. So this is our r vector, this is our position vector of the particle at time t. And what is the linear momentum? It is mass times velocity, mass times velocity, and the two are in the same direction. R vector and this p vector are in the same direction, and therefore this is 0. Angular momentum remains 0, it moves on this straight line. And torque at time t, r cross f, that also you can work out. What is the force? The force is mg. The force is F is mg. Which direction? Vertically downward. So once again r and F are parallel to each other, and therefore it is 0. So obviously torque is dl dt. L is 0 all the time, torque is 0 all the time, so torque is dl dt is obviously correct. If you take your origin here, same story, same story. This is r vector, this is r vector then, and this is F vector, and this is p vector, so same story. What if I take the origin somewhere here? Let us say this is a point O, and this is point A, and this is point P, and my origin is here. Now what is the angular momentum? Is it 0? The angular momentum L is r cross P, and r vector is from the origin to the particle. So this is r vector. So this is r vector, OP, cross product with p vector, mass times velocity. What is velocity? Gt. If I call this let us say this x axis, this is y axis, then it is velocity is gt in minus k cap direction, minus j cap direction, right? Velocity is g into t, v equal to u plus dt, u is 0, and therefore it is mgt, mass times velocity, and then the direction of the velocity is in minus j cap direction. And if I work it out, this OP vector is OA vector plus AP vector. So it is OA vector and plus AP vector, and cross mgt and then minus j cap. OA, this is x direction. So let's take origin here, and this is our x direction, this is our y direction, and the z direction is here. So this was earlier. Alright, so this is origin, this is the OP vector, and which I am writing OA plus AP. OA is this distance is some distance, OA. So this is OA times and I cap plus AP. So it is AP and times this what? J vector, and cross mgt minus j cap. So j cap cross j cap is 0. But I cap cross j cap is not 0, it is k cap. So this is OA multiplied by mgt and then minus, and I cap cross j cap is k cap. Alright, OA is fixed. The particle falls like this. So all the time OA is fixed. So OA has a magnitude, depends where you have chosen the origin, and then mgt in minus k cap direction, and k cap, remember, is now perpendicular to the blackboard. So the particle is falling along this parallel to this y axis. This particle is falling parallel to the y axis, but its angular momentum is in z direction, negative z direction. If this is x, this is y, z is coming towards us, and minus k cap means it is going into the board. So that is L. What is torque? Torque is r cross f, and r is OP vector. So OP cross f, f is mg in the downward direction. So mg times minus j cap. So minus j cap. Look at this expression for L and this expression for torque. So what is the difference? OP cross mgt minus j cap. OP cross mg minus j cap. Only this t is not there, otherwise everything is there. So now if you do this dl dt, here is dl, here is L, this is L, and I am doing dl dt. Differentiate this with respect to time. OP is a fixed vector. No, OP is not fixed vector. OA plus AP, you can write it like that. So your BL dt, if you take from here, OA is fixed, correct? OA is fixed. So this is OA, and then mg is fixed and differentiate with respect to time. So it is 1. So it is minus k cap. So OA into mg, and then differentiated here minus k cap. And what is this? This also you can work out. This is OA plus AP, and then cross mg and minus j cap. And once again, AP is parallel to this y axis, so this part will go away, and what you will have is this OA, and then mg here, m into g here, OA here, and this OA is in x direction, so x I cap and j cap is k cap, so minus k cap. Simple. Same as this. Torque is same as this dl dt. So even for a particle which is falling vertically under gravity, if the origin is chosen in a certain way, you do have angular momentum, you do have torque, and then the rate of change of angular momentum is equal to torque. That equation is valid. So my next example is from central forces, and we will be talking at length about the central forces here to introduce this idea of angular momentum and its use. So we call it central force because you have a force center. So you have a point and the particle is can be anywhere, and then the force on the particle is always along the line joining the particle from this fixed point. That we call force center or center of force. So you have a fixed point, the particle can go anywhere in the whole space, but wherever it is, you join the origin with that position of the particle, the force on the particle will be along that line, either towards the center or away from the center. And then the magnitude of the force depends only on this distance from this fixed point. If that happens, we call that force as a central force. So I can write for central force F at r is equal to some function of r without vector. Okay, here r is with vector, here r is without vector, and then r cap. What is r cap? Just tell. First, let's see what is this r vector and what is this r. R vector is, as usual, position vector of the particle at time t. So at time t, the particle is somewhere, and I join the origin and the particle, and that vector is this r vector. Force on the particle when it is at that position. That is our left hand side. Okay, force on the particle when the particle is at this position, So that is the left hand side. And what is right hand side? It is the distance of the particle at that instant from the origin. Here is the particle, here is the origin, and this is the distance, and the distance is r. And this direction is the direction of the force. Okay, it need not be in general, it need not be in this direction, but for a central force, it has to be in this direction. This r cap vector is along this line and in the increasing r direction, unit vector along the direction of this position vector. This is known as r cap. So this Fr, if it is positive, then the force is away from the center of force. If this Fr is negative, then the force is towards the center, attractive or repulsive. So we have enough examples for such central forces, at least approximately. Our planetary system, sun and the planets. So sun attracts the particle, the planet, wherever it is. So the force is in the direction of that sun, that means opposite to the position vector. And the magnitude depends only on the distance between the sun and the planet, right? The sun is given, the planet is given, so m1, m2 is there, capital G is there, so it's only by r square. It depends only on r, not on the direction, not on the direction. So, or let's say Bohr's model of atom. You have a proton and you have an electron, and then in that model, the electron is supposed to go in some circular path. So all the time the force on the electron is towards that proton, which is taken as the origin, and the force depends on the distance only, q1 q2 by 4 pi epsilon naught r square. So you have so many examples. Okay, so let's try to study this. Now, suppose this particle is acted upon by this central force, and we ask what is the angular momentum of the particle. How do I write the angular momentum of the particle? So, first let us take some axes, and in this process I will be telling you more about another coordinate system in 2 dimensions, which is known as plane polar coordinates. So, I have x axis and y axis, and then the particle is somewhere, and if I join the position of particle from the origin, this vector is the position vector r, and the unit vector along this position vector is known as r cap, and then this angle I can call theta, and if you do not increase the distance but turn it so that this theta increases. So, in the direction in which r is not changing but theta is increasing, that means perpendicular to this. This direction is known as theta cap direction. So, if I take the particle in this direction, this theta will increase. If I take it to infinitesimally small distance here, this theta will become theta plus d theta, but r will remain the same. Same means if it is infinitesimal small, okay, there is no component of that displacement in the r direction, and therefore, for that infinitesimally small displacement we will take that r is constant, only theta is changing. This is r cap, this is theta cap. And if I draw a perpendicular here, this is x and this is y. To get the position, I can write what is x and what is y. I can also write what is r and what is theta. If someone says that all right, it is at a distance of r from the origin, and this line makes angle theta with the x axis, that also tells me that okay, the particle is here, provided the particle remains in this xy plane. If it is in the xy plane, yes, give me r, give me theta, I know that it is in this plane and I know where the particle is. If I know that it is in xy plane, give me x, gives me y, I know that it is in this plane, and here is x, here is y, and this should be the particle. But if it is leaving this xy plane and it moves in a space, 3-dimensional space, z is also there, then neither this is sufficient nor that is sufficient. Let us come back to our angular momentum. So, angular momentum of this particle at time t is given by L equal to r vector and cross p vector, that is mass times r and cross v, and torque. Torque is tau, which is dl dt of course, and which is r cross f. Now, here is the crucial point, r cross f, this is vector r, and the force is also along that direction, r cap. The force is either towards the center or away from the center, but it is on the same line, and therefore, when you do this r cross f, this is 0 for central force. And if torque is 0, that tells me that this L is constant, and remember, it is d dt of L vector. So, if that is 0, that means L vector is constant, and L vector is constant means what? This is constant, this is constant. L vector is equal to mass times r cross v, and this is constant in magnitude as well as in direction, and this is a constant vector, remember, and this v is perpendicular to, this v is perpendicular to L. That is how the cross product is defined. The cross product of two vectors is perpendicular to each of these two vectors. So, L is perpendicular to r, L is perpendicular to v. I am interested in the second part. L is perpendicular to v, so v is perpendicular to L, and L is a fixed vector. So, particle does not have any component of velocity along this direction, this L direction. If I call this L direction, as z axis, v is always perpendicular to L, that means v is in xy plane, that means vz is 0, no component in z direction. So, if initially there is no component in z direction, and then you cannot pick up any magnitude of that, it has to remain in xy plane. So the way you start, how you start in this direction or that direction or that direction, that will decide finally the plane of motion, and the particle must move in a plane. Okay, so does not matter what this function is, 1 by r square, 1 by r, 1 by r cube, whatever. All right, the motion of the particle is in a plane. All central force motion is coplanar, in one single plane it remains, and therefore we can use this. Right, therefore we can use this, and let me go a little ahead of this. What is this r cap in terms of I cap and j cap? Remember, this r cap and theta cap, they depend on where this point is. If the point is here, r cap is in this direction, theta cap is in that direction. These are not constant vectors. They depend on the position of the particle. I cap, j cap are constant. X axis is fixed, y axis is fixed, particle is moving. I cap, j cap are constant vectors. So I can write this r cap as cos theta I cap and plus sin theta j cap. Verify. This angle is theta, this angle is theta, and so this is unit vector, cos theta this component and sin theta that component. And theta cap if you write, so it has one component this side, one component that side, so minus sin theta I cap and plus cos theta j cap, that is theta cap. Now very interesting, what is dr cap dt? And first, what does this mean, dr cap dt? The particle is here, you have a r cap direction, this is r cap. Then in a time dt, the particle goes from here to somewhere else, let us say here, of course, in time dt. So it is infinitesimal displacement. And now r cap is this. So how much is the change in r cap? This vector and minus that vector. That is change in r cap, and therefore I divide by dt and I get this dr dt. Okay, so here is r. These are fixed vectors, I cap, j cap. Theta can vary. Theta is variable. Theta can change as the particle moves. So this is minus sin theta and then d theta dt and plus cos theta and then d theta dt. Here is j cap, here is I cap. And this is minus sin theta I cap plus cos theta j cap and theta dot. Right? When I write dot, it is ddt, ddt of theta. And this is theta cap. This is theta cap, theta dot. It is theta dot theta cap. So dr cap dt is theta dot and then theta cap. Right? So once again, let us write this L vector. You can write what is V vector. What is first R vector? R vector is R cap. Can you see this? Can you see this? R vector is R, that's the magnitude, and the direction is r cap. So r vector is this magnitude r cap. So what is dr dt? Dr dt, this is the velocity of the particle. This is the velocity of the particle, dr dt, r vector here. So differentiate this, keep this as constant, then keep this as constant, differentiate this. And that is equal to r dot r cap, then plus r times dr dt. Dr dt is right here. So it is r and then theta dot and then theta cap. So the r component is r dot and the theta component is r theta dot. You can write it like this. And you can write an expression for this L, which is m times r vector cross v vector, and r vector is r cap, and then cross v vector is here, r dot r cap plus r theta dot theta cap. R cap cross r cap is 0, so it is m into this r and then theta dot r cap cross theta cap. Come back here. Here is r cap and here is theta cap. So what is r cap cross theta cap? This is a unit vector in this perpendicular direction, and that is z direction. So this is k vector, unit vector k cap. So this is k cap. Okay, so we have already shown that the whole motion is in xy plane, and angular momentum is taken in the z direction. So that comes out in z direction. Very good, very nice. And it is fixed, direction is fixed. Magnitude is also fixed. L vector is a constant vector, and here is the magnitude. So L is equal to m into r square into theta dot. and this is constant, means r square into theta dot is constant. The particle may go somewhere in this plane, r is changing, theta is changing, theta dot is changing, but r square theta dot must remain constant. So we will take it from here. We will talk much more about central forces. So we were discussing central force motion, motion of a particle under a central force, and I defined a central force by saying that there is a particle which is moving under a force, and then there is a point, so that all the time the force is along the line joining that point and the particle, and the magnitude only depends on the distance from that particle. So if you have a xyz axis, x axis, y axis, z axis, and then you have a particle here, and at some time t it is here, this is the radial line OP, and suppose it has a velocity in some direction, it has a velocity in this direction, right? The choice of xy axis can be made after I know the velocity of this particle. At this particular instant it will have some velocity, so there will be a velocity vector, and then you have this OP. So you choose your xy axis in the plane of this OP and this V, so that you have at least initially the particle is moving in this plane, and then the z axis is perpendicular. And if the force on the resultant force on this particle is like V Fr r cap, force is equal to Fr r cap, r is this distance and r cap is unit vector in this direction, this is r cap. Okay, it can be away from O or it can be towards O, that will depend on this function. This function can be negative, this function can be positive, so the force can be away, force can be towards. So those things will be taken care of by this scalar function small fr, but the direction is along OP, and the magnitude of the force depends only on this distance, then it is called a central force. And then we saw that the torque is 0, torque on the particle is 0, because at any time, what is torque? Torque is r cross f, and since f is in this radial direction, r vector is in the radial direction, so this is 0. And torque 0 means the L vector is constant, because your torque is dl dp, right? And if L vector is constant, and then L vector is m times r cross v, and L is perpendicular to this r vector and also perpendicular to this v vector, and initially, at least initially, r is here, v is here, so r cross v is in z direction, so this is some L naught times k cap. So initially there is no velocity component in z direction, and velocity has to remain perpendicular to the z direction, and therefore you cannot have the particle out of this xy plane. And so from here itself we can say that the path of the particle under a central force is in one single plane, whatever be that plane. It's a two-dimensional motion, it's not three-dimensional motion, although it's free to go anywhere as such, no boundary is there. It's not constrained somewhere by putting some sheet or something that you cannot go away from this, but still it will go in one particular plane, and the plane will be decided by how the motion is started, right? So if you have the center of force, the force is away from this center or towards that center, and then you have velocity, that decides the plane, and once it is in that plane, it will always remain in that plane, coplanar. Then the other thing we found is that the magnitude of L is mr square theta dot. Okay, this angle is known as theta, and this distance is known as r. So r square and theta dot means d theta dt, mr square d theta dt. This is the magnitude, and since L is constant, right? Since L is constant, this magnitude is also constant. And from this fact that the magnitude is constant, we can derive another nice property of this central force motion. The path is in one single plane, and now we are going to derive yet another beautiful property under central force motion, and that is, if the particle at time t is somewhere here, this is x axis, this is y axis, this is r, this is theta, and in dt time, this is at time t, and in dt time it reaches somewhere here, and this time the velocity is v, so this distance is v dt, and this angle is theta. This distance from here to the new position is r plus dr, and the new angle is theta plus d theta, so this angle is d theta. So let us first calculate what is the area of this triangle. What is the area of this triangle? Remember, we are talking of infinitesimal time dt, and therefore this dr is infinitesimally small, this d theta is infinitesimally small, and this whole area is infinitesimally small. What is that area? Let us calculate. So if I drop a perpendicular from here and call this as h, remember this v dt is this line is v dt. Area of this triangle is half into base into height, half into base into height, and that is half into base is this is the base, one side on which you drop the perpendicular from the third vertex. So this is base, so this r, base is r, and height is this one, and this height you can write from this right angle triangle, this height will be r plus dr sine of d theta, r plus dr sine of d theta, right? This is height, and we have dropped perpendicular to get that height, and then this is a right angle triangle, this is hypotenuse, r plus dr is the hypotenuse, and this is the side h opposite to angle d theta, so sine d theta will be this h divided by r plus dr, and h will be r plus dr into sine d theta. But since the angle is infinitesimally small, sine d theta is same as d theta in the limit, so this will be half into r and into this r plus dr and then d theta, and that is half r into d theta is r square d theta, and then plus r into dr into d theta. And since we have first order infinitesimally small quantity present here, and this is that second order infinitesimally small quantity, there are two infinitesimal quantities, dr and d theta is product of that. So this can always be dropped in presence of this. This is not an approximation. This is not an approximation because we are going to take limits. We always talk in terms of the limits. Final results in calculus are the limits, and there it is exactly the same. So this can be dropped out, and this area dA is equal to half r square and then d theta. That is the area, and this is the area swept by this radius vector in time dt. This was the radius vector. And then this radius vector is, suppose this going, this whole radius vector, actually the particle is going, but you draw this radius vector from each point of this path. So as if this is sweeping this area, this radial line is sweeping this area in time dt. So the rate at which this area is being swept, this radius vector is sweeping the area, will be dA dt, and that dA dt will be half r square d theta dt, that is half r square theta dot, and that is L divided by 2m. Constant, independent of time. The magnitude of angular momentum does not change with time. L is a constant. L by 2m is a constant. So whatever be the form of central force, whatever be the functional form of that f small f r, this function here, for all central motions this is true. The radius vector sweeps equal area in equal time, because the rate at which this area is swept is constant. Radius vector What is radius vector? I don't know where is the radius. There is no circle out. Okay. It can be a circle, but in general it can be anything else. So the radius vector, origin to the particle, that vector is known, the position vector is known as, also known as radius vector. The radius vector of the particle sweeps equal area in equal time. Familiar statement? It may be sounding very familiar, somewhere you have heard it. Yes, you have heard it when you are studying Kepler's laws. This is the second Kepler's law, second law of Kepler. And from in what context these laws were given? Planetary motion, motion of planets around the sun. So there are some 8 planets or 9 planets at the time of Kepler, perhaps there were 9 planets. So different planets are going in different elliptical orbits around the sun, with sun at one of the foci. So that is Kepler's first law. The second law is the radius vector from the sun to the planet sweeps equal area in equal time. And the third law is about the time period. Square of the time period is proportional to the cube of the semi-major axis of the ellipse. The second law of Kepler is valid for all varieties of central force motion, whatever is Fr. Now specifically if you talk of that sun planet type system, you know the force is given by G m by r square, magnitude, and then the direction. So we can write minus and r cap here. So this is taking sun as the origin and planet as the particle. So if this is the origin, then this distance is r, this is r cap vector, it is attractive force, so it is this. What we are doing is very idealized case. Here the sun will also get attracted towards the planet, and therefore sun will also have some kind of central force motion like that. So in our case the origin is fixed, the center of the force is fixed, although sun is very heavy as compared to the planet, so the mistake is not large. But then you can reformulate this sun planet system, neglecting the effect of other planets, of course, asteroids and so many moons and all those things are there. Forget that. If you have just one center here sun, another center say earth, then although the sun is also moving, the earth is also moving under mutual attraction, but that problem can be reformulated to match with this description. So essentially what we have is our Fr here, this Fr, this f of small r is of this type. Fr is minus some constant divided by r square, minus some constant divided by r square. This is known as inverse square law. So if Fr is of this variety, you are considering a particle on which this central force is acting, and the magnitude of central force is given by this 1 by r square type, and it is always directed towards that origin, then it will very close to our planetary system, or very close to the Bohr's model hydrogen atom, where proton is sitting at the center, electron is going around it, and very close to that Rutherford scattering, where you have a nucleus, alpha particle is sent, and because of that force, of course repulsive force, or if you send beta particles, then it is attractive force. Very close to this situation, the force is 1 by r square type, inverse square type. Now if this is the case, we can do something more using energy diagrams. Okay, so let me do that. So energy diagrams I had talked when I was talking of particle moving in one straight line. I took an example of spring force Vx is equal to half kx square, and if I plot this Vx as a function of x, it's a parabola, and from the shape itself I can tell many things. If this is given and if the total energy is known, then I know what are the turning points, what are the amplitudes, and then as a function of x, how much is the potential energy, how much is the kinetic energy at each time. Many things I can derive from these kind of diagrams. But if the motion is not confined to one straight line, but it can go in a plane in different directions, then how do I plot this? So it so happens that in this kind of central force motion, we can have a similar thing, energy diagram, but not exactly of this kind that I am just plotting this potential energy as a function of time, because here if this is force, force is equal to minus k by r square r cap, then this potential v of r will be minus k by r, right. So I just plot this v by r versus r, it will be a hyperbola, and it will also give you some results, but not very useful. So we do some mathematical manipulations. Let us see what. First is, we write this total energy U, which is half mv square and plus potential energy, which is minus k by r, right. Kinetic energy plus potential energy is the total mechanical energy. This is what I want to use in this diagram, and this v I write as r dot r cap and plus r theta cap, r theta dot and then theta cap. This is velocity vector. I had derived it in the previous lecture. If you look at it, the velocity vector v is given by this, and it's the magnitude of this whole square, that is here v square. So this is v and then square and minus k by r. Okay, we derived this. We said that r vector is r cap, and therefore the velocity vector is ddt of r vector, and from there we said it is ddt of r cap, and then we opened it, right, this r ddt of r, which is r dot and then r cap plus r and then ddt of this this quantity, and we saw that this quantity turned out to be theta dot and theta cap. So r theta dot theta cap, we derived that. Okay. Now what is that magnitude square? This magnitude square is half m, this component square plus this component square. They are components in perpendicular directions. R cap direction and theta cap direction are perpendicular directions, unit vectors in perpendicular directions, and therefore you have broken the velocity vector into perpendicular components, one along r cap, another along theta cap, and so the magnitude square is the square of the two components, sum of the squares of the two components. So this will be r dot square and plus r square and theta dot square. So this will be the magnitude and minus k by r. And you also know that m r square theta dot is L. So theta dot is L by m r square. Okay, theta dot is L divided by m r square. Put it here. So you have half m r dot square, that's first term, and then you have half and m here, r square here, and then theta dot square. So L square here and m square and r4 here, and minus k by r. So this is half m r dot square and plus 1 m cancels with this power. This r square will make it r square in the denominator. So you have L square divided by 2m r square, 2m r square, and then minus k by r. This is it. This is it. So the total energy U is equal to half m r dot square and then plus L square by 2 m r square and minus k by r. This you can do with any central force, not necessarily inverse square, only this term will be different. If you change the force law, if it is not inverse square attractive force, is something else, then this will be something else, and only change will come here. This part will still remain the same. Now it resembles, now I have only one variable r, not x and y. So it resembles that motion in one straight line. There we had for motion in one straight line, we had u is equal to half m x dot square dx dt, and then Vr plus potential Vxyz. This is a function of x. No, it's a one straight line motion, so the position is just V at x. So you have half mx dot square and then a function of x, and then we said that okay, we plot this vx as a function of x and then we derive information from here. Now this equation is somewhat of this type, half mx dot square, half mr dot square, and the same x is appearing here, it's some function of x, and this is some function of r dot here and some function of r here, x dot here and some function of x here, right? So you can draw a diagram where this quantity is plotted, right? Here we plotted this vx, here we plotted this vx and derived the equations. Here we plot this quantity which we call v effective as a function of r, and from this we can derive several information about the inverse square, attractive inverse square motion of a particle. Okay, so how do I plot this? The actual plot will depend the actual value of this L, M and K, but we can still have some information about the shape. Say there are two terms here, one is proportional to 1 by r square, another is proportional to 1 by r. If r is very small, much smaller than 1, then what will happen? 1 by r tends towards infinity, 1 by r becomes very large, and if 1 by r becomes very large, 1 by r into 1 by r will again be very large. So this 1 by r square will dominate over this 1 by r term. Here you have 1 by r, here you have 1 by r square. So L square, M, K, they are all fixed. So if you go sufficiently towards that smaller values, if r is sufficiently small, you can always make this much larger than this. So for very small values of r, this term will dominate, the positive term will dominate, the negative term will be much smaller in magnitude as compared to this. So for very small r, this value will be somewhere here, and then it will come down, and at some value, which value? L square by 2 mr square is equal to k by r. So r is equal to L square by 2 mk. At this value, this whole quantity is 0, so it will cross this r axis somewhere here, it will cross at this position, it will cross. Now this will start dominating. These two terms are now equal, and after that 1 by r is becoming smaller. As r is going bigger, 1 by r is becoming smaller. And if 1 by r is small, 1 by r into 1 by r is still small, much smaller, and therefore this will keep dominating. And how is this minus 1 by r? So if you see minus 1 by r is something like this, and this will dominate. 1 by L square by 2 mr square, if I plot, it will be of this type. It will be of this type, going to 0. Ultimately both of the terms are going to 0. Minus k by r will be of this type. So here they are equal. It will be going like this. This will be falling much faster. This will be falling much faster. Okay, and here they are equal, and therefore it will come like this. After this, this will dominate, and this will become smaller and smaller. So it will be of this type. This will be of this type. So this whole quantity, if you plot, this will be of this type, right? So now I can remove these dotted ones. I can remove these ones. This is my v effective. This is my v effective, and from this diagram, from this shape, we can derive certain information about this inverse square attractive central force motion that we will do next time. So we talked about energy diagrams for a particle with a central force acting on it, and for that we have to write the expression of energy. U is half mv square, and then potential energy function, but this v can be written as r dot r cap and plus r theta dot theta cap. So when we use these plane polar coordinates, x axis, y axis, the position is denoted by this r and this theta, and this is r cap vector, and perpendicular to this in increasing theta direction is theta cap direction, unit vector theta cap, and in terms of these unit vectors, velocity is given by these. You can also find expression for acceleration from here. If we differentiate this, you get the acceleration of the particle, the component in r cap direction and component in theta cap direction. If you use this, the acceleration will be r double dot r cap and then plus r dot d r cap dt. Double dot means the second differentiation with respect to time. So, when you differentiate r dot with respect to time, d2 r by dt square is written as r double dot r cap, then keep this r dot here and differentiate this. Here you have three quantities, r, theta cap and theta dot. So, differentiate this r dot and keep the rest there, right, and then differentiate this one. So, plus r theta double dot and then theta cap. Now differentiate this one. So, plus r theta dot and d theta cap theta dt, theta dot. Okay. So, r kept as it is, theta dot kept as it is, and this is differentiated. So, you write this way, and then you know how to write this, you know how to write this. This r cap is cos theta and I cap plus sin theta j cap, because this is x axis. So, this is x direction, this is y direction, this angle is theta. So, this r cap you can decompose in cos theta sin theta, theta cap you can decompose as minus sin theta I cap and plus cos theta j cap, and from here you can write what is this dr cap dot dr cap dt. We had done that, dr cap dt, you differentiate this. So, it is minus sin theta I cap plus cos theta j cap. So, this is how it goes, and then theta dot, of course, because you have to differentiate with respect to time. So, this is theta dot and then theta cap. Similarly, you can do this d theta cap dt. If you differentiate this, it is minus cos theta theta dot I cap, and then this will be minus sin theta theta dot j cap. So, this will be minus and theta dot and then r cap, because you have minus cos theta and minus sin theta, and then that minus is taken common, you have cos theta I cap plus sin theta j cap, which is r cap. So, it is this. So, you can put it here, and your expression for acceleration is now, acceleration is r double dot r cap plus r dot and then dr cap dt is theta dot theta cap, theta dot theta cap, then plus r dot theta dot theta cap here, then from here it is plus r theta double dot theta cap, and then you have r theta dot and d theta cap by dt is minus theta cap. So, this is minus theta dot. So, it is minus theta dot square and then this r cap. So, if we collect r cap at one place, you have r double dot from here and minus r theta dot square from here. So, that is the radial direction, acceleration in radial direction. So, if the particle is here, is moving in some way with some velocity on some path, and you ask what is the acceleration of the particle. So, you can decompose in two components, in r cap direction and in theta cap direction. So, that r cap component will be this, and theta cap component will be from here r theta dot, r dot theta dot, then from here again r dot theta dot, and from here r theta double dot. So, that is the expression. Your radial acceleration is r double dot minus r theta dot square, and the theta component will be 2 r dot theta dot and plus r theta dot. So, you can do your dynamics, two dimensional dynamics in a plane using these plane polar coordinates like this. But at the moment we are concerned with the energy of a particle which is acted upon by a central force. So, you have a center of force, and then the particle is here, a mass, and the direction of the force is along this line, radial line, this r cap line, and that is the kind of situation. And for that we are writing our, this is the origin, x axis, y axis, r theta. You can write, if the particle is here, this is r, this is theta. So, energy is half mv square, half m. And for v square we write from here r dot square and plus r square and theta dot square. That is the mv square, and plus what is the potential energy? V of r. Then we use angular momentum expression to write this r theta dot square, you know, m r square theta dot is L, and from there we wrote this as half m r dot square plus L square by 2 m r square and plus V of r. This whole thing we write as effective potential energy. It is a function of r only, that is half m r dot square and plus V effective, which is a function of r. And it is this V effective r that we plot. So it is this V effective r that we plot. And this side is r, remember, and r will not be negative, so everything will be on this side. And what is this V effective r? Here, L square by 2 m r square plus V r. So if you talk of inverse square attractive force, okay, which occurs at so many places, you know, Coulomb's force is inverse square. If the charges are of unequal type, it is attractive. You can put your origin at one of the particles and the other particle will be doing this kind of central force motion. You have planetary systems, Sun, Earth, Sun, Jupiter and all those things, which can be fairly well approximated by this inverse square attractive force. You can have a nucleus and then bombard electrons and see how that electron beam is deflected by this positive nucleus. All those things can be fairly well understood using all this analysis. So if this Vr is minus kr, minus k by r, and this V effective is L square by 2 m r square and minus k by r, then we saw the shape of this will be of this type. For small values of r, this dominates, it is increasing and positive, and for large values of r, this will dominate over this. So ultimately this will fall faster and the total will be negative, and finally when r is very large, everything is approaching 0. Now the total energy U, this total energy U, I can write on this scale. So suppose this is the total energy, this is that line, total energy is here. So you have this particle, and this particle has got some velocity at this time. Let us say this is the velocity. In this direction it has some magnitude, there is some r here, and at that time it will have some angular momentum L, and the total energy depending on this kinetic energy plus minus k by r. So initial conditions will tell me how much is the angular momentum L and how much is the total energy U. So once L is known, then I can draw this, I can have this thing, and so I can draw this line, and once energy is known, total energy is known, what is the kinetic energy here, what is the potential energy here, that total energy, then I can draw this line. So this is the situation. What will happen to this particle further? So at this time there is some value of r. So some value of r, suppose this is that value of r, this, remember this is r axis. So this is that value, initial condition. So that means on this diagram, if I draw a line, this is the potential energy, this is the potential energy, okay, and this is the total energy, this is the total energy, this is the total energy, total mechanical energy, okay. So how much is, this is not potential energy, this is effective potential energy, okay, this is effective potential energy, this much. Value of this is given by this point, this much is the effective potential energy. So one more E, effective potential energy, V effective. V effective is this much. So if you subtract this effective potential energy from this total energy, so this is the total energy, from this you subtract this energy. So that means this whole thing from here to here, from here to here, this whole thing is half m r dot square. What remains? Half m r dot square. This is not kinetic energy. Okay, this is not kinetic energy. Kinetic energy is this plus this, but half m r dot square is that full length. Now what is happening? If this is the diagram, if the particle is going in this direction, the value of r is decreasing. If it is going on that side, the value of r will increasing. So for this diagram, if I go by this diagram, if I say that no, this is very nicely drawn diagram, it does represent the correct direction of velocity, r is decreasing, that means this point here as time passes will shift here, the r is decreasing. Particle is here, remember this is a graph, this is the particle is going in this direction. So this length, the separation from origin is decreasing. In this diagram the particle original r is here and the r is decreasing, means it is going this way. If it is going this way, what is happening? Your effective potential energy is now this much, the magnitude is decreasing, and then the total energy is here to here, this is total energy, and what is from here to here? This is once again, this is half mr dot square. So value of half mr dot square, which was this much, has decreased to this much. Okay, so this way things will go, and then somewhere it will go. So what happens on this diagram? Let us see what happens on this diagram. On this diagram, as r decreases, you are going this side, this side, this side, this side, this side, and finally at some stage r will decrease. At some stage r will decrease, and you will reach here. You will reach here. Suppose r is decreased to this value. And what is this value? If I draw a vertical line here, it just crosses this. Okay, so at this point, what is the effective potential energy? Here is the curve. So at this point, this is the effective potential energy. And how much is the total energy? That is always fixed. This is the total energy. How much is half mr dot square? 0. Okay, so when the particle reaches this point, let me call it r1, and the point, corresponding point on this curve is here, then you have mr dot square equal to 0. So here for this r1, half mr dot square is 0, so r dot is 0. What does that mean? What does that mean? That means your r is minimum there, dr dt is 0, dr dt is 0, r is a function of time, and dr dt 0 means it can be a maximum or it can be a minimum or point of inflection. So what is the physical picture here? R is decreasing, 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 decreasing. So somewhere it has to reach a minimum and then it will increase. So this particle will go something like this. So there is a minimum r, this is that minimum r. Okay, r is decreasing, 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 and after that it is increasing, increasing, increasing. So after this point, when this point is reached, the motion will continue and r will start increasing. So we started from somewhere here. So on this u diagram, if I point, it is somewhere here, and on this line let me move. R is going this way, that means this point is moving this way, this way, this way, this way, this way, and then this point reaches here, and it cannot go in this side. If it goes this side, then that half mr dot square should be negative, which it is not. So this is forbidden. This is turning point, not exactly turning point, but in some sense yes, r is decreasing, decreasing, and then start increasing, increasing. So it's something similar to that turning point. This is the minimum r1, and after that r will start increasing. Your point will go in this side, this side, this side. There is no other turning point. R dot is never 0. R dot is never 0. You go this way, this way, this way, this way, never you will be intersecting this point. So r dot is never 0, so the r dot will keep increasing. So that kind of path will be there. Similar will be the characteristics if u is 0. If u is not this much, if u is this much, same story. U is this much, same story. U is this much, same story, in the sense that yes, it never reaches here. Okay, if this is u, u is equal to 0, and then your particle goes this side, you have a turning point, so called, and then r is minimum there, and if initially this particle is not going this way, if it is going this way, r is increasing, then it will keep increasing, right? It will keep increasing, no turning point on this side. But if u is less than 0, if u is less than 0, suppose this is u, then this is the point where r dot is 0, and this is the point where r dot is 0. The total energy and the effective potential energy are same. Here is total energy and here is effective potential energy. So at the points of intersection, the total energy and the effective potential energy is same, and that means r dot is 0. So this corresponds to minimum and this corresponds to maximum. If the particle is going towards right on this diagram, That means r is initially increasing. It will increase, but after here it will reach a maximum distance from the origin, and then r will start decreasing. That means on this diagram the representative point will be moving this way, and once it reaches here, again r dot is 0. This time r has reached a minimum, and after that r will start increasing. So physically, if this is the origin, and if this is the circle of radius r1, and if this is the circle of radius r2, the particle cannot go inside this circle and cannot go outside this circle. The particle is bound. If u is positive or if u is 0, the path is unbound. It goes to infinity. And in this case where u is less than 0, the particle is bound. It cannot go much away from the center of force. So for bound paths, total energy should be negative. What kind of path it is? With this much information only, the path can be anything between these two. It can be like this. It's confined in that place, but it can be anything. But if it is potential energy is minus k by r, inverse square attractive, then the things are more definite. We have to do more algebra and equations, but then we can come out with the result. I will just tell you the steps. That the path is an ellipse. Remember, circle is a special case of ellipse. The path, if u is less than 0, the path of the particle under inverse square attractive force is an ellipse. So it will be something like this. It could be something like this. Minimum separation is r1, and maximum separation is r2. Something like this. Some kind of ellipse between these two circles. So that is the path. Kepler's first law states that all planets move around the sun in elliptical paths with sun at one of the foci. So it is here. Of course, second law we have already discussed. Third law will also come if you consider this attractive inverse square law. Now, how to get this orbit? How to get the equation of this orbit? How do I know that it is an ellipse and nothing else? If it is bound, it has to be an ellipse, and if it is unbound, what kind of curve? Okay, so that also we can. I can just tell you the steps the algebra one has to do, or see the textbook and convince yourself that the path is elliptical if the total energy is negative. So write your energy expression. U is equal to half mr dot square plus L square by 2 mr square and then minus k by r. This is the energy expression, and U and L are known from the initial conditions. Once you know initially where the particle is, you know what is k by r. Once you know what is the initial velocity in which direction and how much is the speed, then you know this quantity, this quantity. So U and L are defined from the initial conditions, all right, and therefore you can write this as half mr dot square is equal to U and minus L square by 2 mr square and minus k by r. Multiply by 2 by m, so r dot square is equal to 2 by m and then U minus L square by 2 mr square and minus k by r, and take a square root on both sides. So r dot is equal to square root of this. And what is r dot? R dot is dr dt. So dr divided by square root of 2 by m U minus L square by 2 mr square and minus k by r is equal to dt. So as a physics person, I have done my job. This is now a mathematics. This is a function of r, and here you have dr. So apply the rules of integrations, this that, to get this expression here. Okay, so you get this thing r as a function of time. From here you get r as a function of time. some function of time. When you integrate this, you get that. And once you get r as a function of time, you can use this expression that L is equal to mr square theta dot. So, theta dot is equal to L by mr square, and this is d theta dt. So, d theta is equal to L by mr square and then dt, and r you know as a function of time. R you know as a function of time. Once again, it is a matter of integration. You have dt here, you have a function of time. A function of time to be integrated with respect to time, it is a calculus matter. So, do it. Once you do it, you get theta as a function of time. Alright. So, this is a ft, let us call it gt. So, now you have r as a function of time, you have theta as a function of time. You do have initial values of r and theta, you can put t equal to 0 and those values to get any integration constant, and therefore, you know the path point by point. At this time the particle will be here, at this time the particle will be here, at this time the particle will be here, and so on. And if you eliminate time from here and here, you have two equations. R is blah 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 as a function of time, theta is blah 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 another function of time. If you eliminate time from these two equations, what do you get? You will get r as a function of theta. That is path. That is the equation of the path. R is a function of theta. So, this is the way one can calculate and come out with the exact equation that if u is positive, it is a hyperbola. It is a hyperbola. If u is equal to 0, it is a parabola, and if u is less than 0, it is an ellipse. Finish. Remember, circle is a special case of ellipse, and we can work out when it will be circle, but maybe next time. So, under attractive inverse square law, that kind of force, the path of particle has to be either ellipse or parabola or hyperbola, nothing else. And then what exactly it is, that is decided by the total energy, and that is decided by how you start the motion. So, in the previous lecture we discussed how to get the path of this orbit if a particle is there under a central force, inverse square central attractive force, and these are the steps. In fact, you can start with total energy, and angular momentum are known from the initial conditions. You write mr dot square from here, and from there r dot, and that becomes function of r only, and therefore, in principle you can bring this side, it is a function of r, and that can be integrated with respect to r, and this side is t. So, you get t as a function of r, and then algebraically you manipulate and write r as a function of t, and once r as a function of t is obtained, then you can come to this equation, and from here you can write theta dot, which is L by mr square. Now, this whole thing is a function of time, and therefore, r is a function of time, and therefore, you can integrate this out and write theta as a function of time, and then you can eliminate time from this equation and this equation. That gives you relation between r and theta, and that is the equation of the path in plane polar coordinates. So, you know what is the orbit, and if you work out the conditions that we have already discussed with energy diagram qualitatively, that if this u is greater than 0, it turns out to be a hyperbola. If this u is equal to 0, it turns out to be parabola. If this u is less than 0, then it turns out to be an ellipse. We will be more interested in this elliptical orbits where the initial conditions are such that the total energy is negative. The potential energy minus k by r has a much larger magnitude than the kinetic energy half mv square. So, the total energy is negative, and then the orbit is ellipse, and the equation of that orbit, if you work out, that will be r equal to some constant r naught divided by 1 minus e cos theta, where r naught is L square by mk, and this small e is square root of 1 plus 2 times total energy times L square and divided by mk square. Now, this quantity is known as eccentricity of the ellipse. This quantity here is the eccentricity. It gives you equation of an ellipse if this E is between 0 and 1. Okay, so this is the equation. If you want to see how this can be an ellipse, you can take some values and convince yourself that it looks, at least it looks like a ellipse, and that will also give you some feeling of this E here. So let us take this example. Let us say E is 0.1. What happens? R is equal to R naught divided by 1 minus 0.1 times cos theta. Suppose this distance is R naught, this distance is R naught, and I have put this point, it will be at on the ellipse, because here theta is 90 degree, and if you put theta is equal to 90 degrees, this is 0 and R is equal to R naught. So you will have a point here on the ellipse, and what happens if theta is 0 degree, then cos theta is 1, it's 1 minus 0.1, so 0.9 R naught divided by 0.9, little more than R naught, little more than R naught. So you have a point somewhere here, little more than R naught. If theta is pi, cos theta is minus 1, then it is 1.1, R naught divided by 1.1, a little less than R naught. So a little less than R naught somewhere, let us say here. So it's of this type, it is of this type. So you have an ellipse you can draw it to the scale. You can use an Excel file and put the values of theta, get the values of R, and then you can make tables and you can plot and you can see how it looks like. On the other side, if you take E is equal to say 0.9, what happens? R is equal to R naught divided by 1 minus 0.9 times cos theta. So now if you have the same R naught here, because at theta equal to 90 degrees, this will be 0 and R will be R naught, so this point remains the same. But the point on the x axis, theta equal to 0, if theta is 0, cos theta is 1 minus 0.9 is 0.1 only, so this is R naught divided by 0.1, 10 times R naught, 10 times R naught. So you have a point at a very large distance here. And on the other side, if theta is pi, this will be 1 plus 0.9, very close to R naught by 2. So another point is here. So now you can see, you can write this as so as the eccentricity increases, this ellipse becomes more and more elliptical. If it is close to 0, it's close to circle, and if it is close to 1, there's a very elongated cigar type ellipse. What happens if E is equal to 0? If E is equal to 0, if E is equal to 0, where? Here, if this E is equal to 0, R is equal to R naught. R is equal to R naught for all theta. So that's a perfect circle, right? And if E is equal to 1, if this is 1, then it is 1 minus cos theta, and at somewhere it will blow, or more than 1, somewhere it will blow, go to infinity. So if E is equal to 1, then it is a parabola. If E is greater than 1, then it is a hyperbola. If E is less than 1, between 0 and 1, then you have ellipse. So that is how. And you can also get this idea of how elongated it is from this R minimum and R maximum. So what is R minimum here? R minimum is R naught divided by 1 plus E. R naught divided by 1 plus E. And R maximum is R naught divided by 1 minus E. Okay, so this is your maximum, and this is the minimum, and here this is the relation. If you see the ratio, R max by R min, that is 1 plus E divided by 1 minus E. That also will give you a fairly good idea that how much is this. And then eccentricity, you also have a relation that if I take the center of the ellipse, then this is called semi-major axis and this is called semi-minor axis. Okay, from the center of this minimum point and maximum point, theta equal to 0 and theta equal to pi, from the center if you draw a perpendicular line, then half of this whole distance, this is known as semi-major axis, this point to this point is known as major axis, and this perpendicular, this point to this point is known as minor axis, and this is semi-minor axis. And the relation between these two is b is equal to a square root 1 minus e square. So b by a is equal to, or a by b, okay, b by a is equal to square root 1 minus e square, and a by b will be reverse of this, 1 divided by square root of 1 minus e square. So from here you can also see, if e is close to 1, then this quantity is very small and this quantity is very large. The major axis is much larger than the minor axis, and that is what I mean by that elongated ellipse. Whereas if this e is close to 0 and this whole thing is close to 1, then a is close to 1, a is close to b, and then the minor axis and major axis are roughly equal, and that is nearly a circular orbit. So this eccentricity decides the shape of the ellipse that it is there, and physically the eccentricity depends on these quantities: total energy, the angular momentum, which are constants, and then of course mass of the particle, and force. This constant k is coming from force, remember it's k by r square, force is k by r square, that k. So these things will finally decide what is the energy, and remember this u is negative, so this e is less than 1, and therefore it is an ellipse. Okay, let me also write how much is that major axis, okay, and you will see a very interesting result. So if you write that major axis 2a, that is r min and plus r max, this is the major axis, and this is r naught divided by 1 minus e plus r naught divided by 1 plus e, and that is r naught. Here you have 1 minus e square, and then you have sum of these two, which is 2. So 2 times r naught divided by 1 minus e square. How much is this? This is 2 times r naught. R naught is r naught, where is r naught? R naught is L square by mk. So this is 2 times L square by mk, and then 1 minus e square. What is 1 minus e square? E square is equal to 1 plus 2u L square divided by mk square. So 1 minus e square is equal to minus 2u L square by mk square. So right here 1 minus e square is equal to 2u L square and then mk square. How much is this? L cancels out, not u, L cancels out, 2 cancels out, m cancels out, and this is just 1 minus e square, minus of this, right? So minus of this. So it is minus here, and then k here, 1k cancels out, and divided by u here. This is it. So u is equal to minus k divided by 2a. The total energy decides the major axis, or if you know the major axis, you know the total energy. It doesn't depend anything on anything else. So this is one beautiful result that one can remember. Okay. Another thing what you can do is to calculate the time period. If the particle is going on this ellipse, how much is the time taken? And for that you already know that the area, rate of area swept by this radius vector. So at some instant the particle is here, and then the particle reaches here. So this is the area, this is that area covered, and dA dt is constant. So this area is increasing at a constant rate, and the total area of ellipse is known. dA dt is what? L by 2m, right? mr square theta dot, mr square theta dot, this is L, and this is 2 times m times half r square and then d theta dt. Okay. And this is that area dA, this is that dA. So, L is equal to 2m and dA dt, and therefore, dA dt is L by 2m, dA dt is L by 2m, correct. The total area of this whole ellipse is, which the radius vector has to sweep in one full revolution, that is pi ab. So, the time period will be pi ab, this is the total area, and divided by this dA dt, which is L by 2m, divided by dA dt. This is the area swept per unit time, and total area to be swept in one revolution is this, and therefore, when you divide you get the time. So, this is pi into A, and B is A square root 1 minus E square, and divided by dA dt is L by 2m. So, L here and 2m here. So, it is 2m pi A square by L, 2m pi A square by L, square root of 1 minus E square. 1 minus E square we had written, this is 1 minus E square, this is divided by mk square. Once again we can do it from here, 1 minus E square will be equal to minus 2 u L square by mk square, and square root of that, square root of this. So, it is square root of minus 2 u L square and by mk square. What cancels? This L cancels with L square. Okay, then all right. So, this is it. So, this is equal to 2m pi A square divided by this m I can take inside the square root. So, this will be square root of m here, right, m here and square root of m here. When you cancel, square root of m goes in the numerator, that we are writing here. 2 pi A square we have written, and therefore, we only have to write the rest of it. So, minus 2 times, oh, okay, let us write 2 times minus u. What is minus u? Minus u is k by 2a, minus u is k by 2a. So, this is 2 and minus u is k by 2a. So, it is k by 2a, right, k by 2a, minus u is k by 2a. We have written this divided by k square. So, k I can write here. All right. So, yeah, there is a root k here and k here. Okay. So, let me write k square and then I will cancel it. This is equal to 2 pi A square and then square root m by k, right, m here and k here, 2 cancels, a is in the denominator. So, divided by square root of a. So, this is 2 pi square root m by k and then a to the power 3 by 2, or t square, capital T square is 4 pi square and then m by k and then a to the power 3. So, if you have a gravitational attractive inverse square law, sun and different planets, what is this k? In that case, k is capital G m m. The force is k by r square and the force is g m m by r square. So, k is g m m. What is m by k? M by k is 1 by capital G m. Small m divided by k is equal to, small m divided by k is equal to 1 by capital G m. So, this is 4 pi square divided by capital G capital M a power 3 by 2. The mass of the particle has gone. If this is the case, if this k is proportional to the mass of the particle, which is the case in the gravitational attraction at least, if k is proportional to m, m by k is independent of the mass of the particle. So, in the sun planet system, you consider any planet, Earth, Mars, Jupiter, whatever, any planet, no reference there, and it is only the semi-major axis which is deciding this time period. Square of the time period is proportional to the cube of the semi-major axis. Okay, square of the time period is proportional to cube of the semi-major axis. This is Kepler's second law. Kepler described all these laws on the basis of observation of positions of planets at different times around the year. These observations were taken by Tycho Brahe, and Kepler analyzed those data, and from there he formulated these rules. The first law, all planets go in elliptical orbits with Sun at one of the foci, and that we understand now using all that algebra. We know that yes, this is the equation. This is the equation of the ellipse, and therefore the particle or the planet has to go on the ellipse and the Sun will be at the focus. Then the second law is here. Oh, this is the third law in fact. The second law, popularly known as second law, is that radius vector sweeps equal area in equal time. So that we have already seen. That is valid for any central force, not only inverse square attractive. Okay, so Kepler observed it very rightly from the data that it sweeps equal area in equal time. And then the third law, that square of the time period is cube of this semi-major axis. So that also comes from this analysis. So today we will be doing some problems, and most of the problems that I will be doing in this course will be based on the book by Kleppner and Kolenko. This is that book, Introduction to Mechanics, by Daniel Kleppner and Robert Kolenko. So most of our problems will be from this book, but not for quiz, okay, for doing in the class. So the first problem I am taking is based on example 1.17, and it says that a particle moves with a, so first problem is a particle moves in a plane. The problems that I am taking today will be using plane polar coordinates. So it's a practice of using plane polar coordinates. The particle moves in a plane with standard notations. R dot is equal to 4 meter per second, and you know what is r and what is theta. This is x axis, this is y axis, this is the position of the particle, then this distance is r and this angle is theta. These are the plane polar coordinates. So r dot means ddt. ddt of r is 4 meter per second, and theta dot is 2 radian per second. Theta dot is 2 radian per second. So this is the data given, and you are asked to find the velocity and acceleration of this particle. Find velocity and acceleration of this point, of this particle. Okay, so as you know, what is velocity? Velocity has two components, radial components and transverse component. I call this theta cap direction as transverse direction, and r cap direction is the radial direction. So this is r cap and this is theta cap, although this book calls it tangential acceleration, but tangential would mean tangent to the path, not perpendicular to this radial. So v is equal to r dot r cap and plus r theta dot theta cap. So that is the expression for velocity, and r dot is given here 4 meter per second, and r cap and then r, and theta cap is given 2 radian per second. When r is 3 meter, when r is 3 meters. So that's also in the question. Find the velocity and acceleration of this particle when r is 3 meters. So you can put this 3 here. So 4, this is, finally it will be in meter per second. So remember that I am using only the numerical values here, but the velocity will come out to be in meter per second because we are feeding all SI data. So this is 4 times r cap, and plus 3 into 2 is 6. So theta cap. So that is the velocity, meter per second. This is the velocity. So this is, in this direction the component is 4 units, and in this direction the component is 6 units. If you want speed, it is just a square root of this 4 square and plus 6 square. So 16 plus 36, that is square root of 52 meter per second, that is the speed. And if you want the angle, you can always get what is this angle. Tan theta is equal to this radial component divided by the transverse component. So this is about velocity. Then acceleration is acceleration is, the radial component of acceleration is r double dot minus r theta dot square. Right? We must have derived this, otherwise you can derive it, r cap, and the transverse component is r theta double dot plus 2 times r dot theta dot. We had done dr cap by d theta and d theta cap by d theta, we had done this, and then if you are differentiating with respect to time, you also have to finally differentiate with respect to time here. So, theta dot, that will, those things will be used here, and then you can get this relation. So, if I put the values here, r dot is fixed, okay. So, r double dot, which is d dt of r dot, is 0. So, that is 1, and then theta dot is 2. So, theta dot is 2, and therefore, theta double dot is d theta dot by dt, that is also 0. So, this is 0 and this is 0. So, what you are left with, r theta dot square. So, A is equal to minus r theta dot square. So, minus r theta dot square, and this is in r cap direction, and in theta cap direction, it is 2 r dot theta dot, so plus 2 r dot theta dot. In theta cap direction, you put the value 3 here, then theta dot square, that is 4 here, and this much r cap plus 2 times r dot into theta dot 4 into 2, so 4 into 2 theta cap. So, that is the acceleration, 12 r cap plus 16 theta cap meter per second square. Okay, so that is how you can get this acceleration. Next problem, problem number 2, and this is based on 1.18 of the book, and the problem is, a particle is moving on a circle with a uniform speed v. A particle is moving on a circle with a uniform speed v, circle of radius r. Find the rate at which the acceleration changes. Find the rate with which the acceleration changes. Okay. So, a particle moves on a circle of radius capital R and with a constant speed v, uniform circular motion. You have done it in standard 11, and you know what is the acceleration. The acceleration is towards the center and is minus v square by r. You can also write from here, the acceleration is r double dot minus r theta dot square in r cap direction, and r theta double dot plus 2 times r dot theta dot in theta cap direction. Since r is constant, the distance of the particle from the origin is constant. You can take x axis, you can take y axis. This is r, this is theta. R dot is 0, r double dot is 0, so this term goes away, and r dot is 0, so this term goes away. Then you have theta double dot, and theta dot, the angular velocity theta dot d theta dt, okay, d theta dt is v by r, because if this is d theta and then this is v times dt, so d theta by dt will be v by r. So theta dot is v by r, v is constant, r is constant, so theta double dot is 0. So theta double dot is 0. So you do not have any theta cap component of the acceleration, we know it. If the speed is not changing, the tangential acceleration is 0, and here the tangential acceleration is same as the theta component of the acceleration, because here this theta direction is actually tangent to the path. So this is gone, and then you have minus r theta dot square, and theta dot is your v by r, this r is capital R, and this is v square by r square r cap, and that is minus v square by r cap. So this result you anyway know. Now comes rate of change of acceleration dA dt, that is minus v square by r is constant, right, minus v square by r is constant, r cap. So this is d r cap dt, which is d r cap d theta, and then d theta dt, which is minus v square by r. And what is dr cap d theta? Dr cap d theta is theta cap. Okay, we must have done it. So this is theta cap, this is theta cap, and d theta dt is this one, v by r. So this is v by r, and then this theta cap. So this rate of change of acceleration is minus v cube by r square, and then theta cap. This is our question number 2. Next question 3, and this is based on example 1.17, and it says that a particle moves with theta dot is equal to omega, which is constant, and r is equal to r naught e to the power omega t. So this is the information given. Theta dot is omega and r is r naught e to the power omega t. The first part is sketch the path. Sketch the path. So when you want to get the path, time is not important. We want a relation between the coordinates on which path it moves. So here it is r is given as r naught e power omega t, and theta from here will be omega t. So I can eliminate t and write r as r naught e to the power theta. So that is the equation of the path. And how does it look like? Sketching. So if you have say x axis and y axis, and at theta is equal to 0, if you take theta equal to 0, e to the power 0 is 1 and r is equal to r naught, and theta equal to 0 means along the x axis. So in this direction, this is theta equal to 0 direction, and r is equal to r naught. So from here you have to go a distance r naught. So this is r naught, this small thing is r naught. So particle is here. When theta is 0, particle is there. Now when theta is, let us say, pi by 2, as theta increases from 0, e to the power theta will increase. You know what is e theta? E to the power theta, 1 plus theta square by 2 and so on. So theta increases, e theta increases. At theta equal to pi by 2, this e to the power theta is e to the power, say, 1.57, and that value is around 4.8. So that means r will be r naught into 4.8. So if this is r naught here, theta equal to pi by 2, that means you are here, and the 4.8 times of this. So I cannot draw it to the scale. So this is, say, 4.8 times r naught, and it's continuously increasing here. It's continuously increasing here. It's going like this. It's going like this. Then when theta is pi, e to the power theta will be square of this, and that is around 23. That is around 23. Okay. So this is r naught. When it reaches here, it is 23 times of this. So I cannot draw on the scale. I can only tell that it will keep on increasing, and it will be like this. And then when theta is 3 pi by 2, then this is 110. This is e power theta is 110. So it ever increases, and this is 110 times this r naught. Theta is 2 pi, e to the power theta will be very high. It is 534 square of this. So it will go like this, and so on. So this kind of spiral will be there. You can draw a much better work and look at the angles, which we will be doing in the other sections anyway. So this is part A. Part B is find the speed as a function of theta. So part B is find the speed as a function of theta. So write velocity. Velocity is r dot r cap and plus r theta dot theta cap. Should be tuned to it and write it quickly. This is velocity. So and what we need? Speed. So r dot. What is r dot? r is equal to r naught e to the power omega t, and or you can also say this is e to the power theta. So r dot is r naught and then e to the power theta into theta dot, right. What we have done, differentiate with respect to time. This is to be differentiated with respect to time. First differentiate with respect to theta because it is written as a function of theta. So differentiate with respect to theta and then differentiate theta with respect to time. So that is how it comes, and theta dot is known, theta dot is fixed, omega. So this is r naught times omega times e to the power theta. This is r dot. And what is r theta dot? R theta dot is r naught e to the power theta. This is r and then theta dot, and theta dot is omega. So this is r theta dot. What you see is r dot is same as r theta dot. See, r dot is same as r theta dot. That means Vr, r component of the velocity, is same as theta component of the velocity. This thing and this thing are same. The component of this velocity in r cap direction, it's same as the component of velocity in r theta cap, theta dot, in theta cap direction. So if I am somewhere here on this path, and if this is the r cap direction and the perpendicular to it is theta cap direction, this is r cap, this is theta cap, the velocity has equal components in the two directions, and therefore the velocity should be in this direction, 45 degree to it, 45 degree to it. Our diagram is bad, our diagram is very bad. Okay, the velocity should be 45 degree to the radial direction, the velocity should be 45 degree to the tangential direction. So it should go like this, it should go like this. Here this is radial direction r cap, this is tangential direction theta cap, and then it should go like this, equal angle from r cap direction and theta cap, everywhere. This is r cap direction and this is theta cap direction, and the actual velocity should be in between. So it should go like this. Okay, so just don't go by the sketch of the diagram, and you can draw a much better diagram. But the thing is, it will keep on increasing, r will keep on increasing all the time. This equation will be followed. So speed will be this Vr square plus V theta square. So this is root 2 times omega r naught e to the power theta. So that's the speed. Okay, then this is part B. Part C is find the angle made by the velocity vector with the radial and transverse. We have done that, so no need. Next part is find the radial, transverse and tangential acceleration. So write it as C. Find the radial, transverse and tangential acceleration. Okay. So what is this radial acceleration? Radial acceleration AR is r double dot and minus r theta dot square. This is the radial direction, acceleration in radial direction. What is r double dot? What is r double dot? This is r. So r double dot is omega times r naught e power omega t. So we are differentiating with respect to time, and r is given by this. So with respect to time we differentiate, this omega comes here. So omega r naught e to the power omega t, that is r dot, and therefore r double dot is once again differentiate with respect to time. So omega square into r naught and then e power omega t. So that's the radial, that's the r double dot, that is r double dot. And what is r theta dot square? R theta dot square means e to the r naught into e to the power omega t, that is r. Theta dot is omega, so theta dot square is omega square. So omega square r naught e to the power omega t. Again you see omega square r naught and omega t. So what is this? What is this? What is this? This is 0. Interesting. Radial component of the acceleration is 0. Okay. So AR is equal to 0. AR is equal to r double dot minus r theta dot square is equal to 0. R is increasing in a great fashion. R is going away from this origin, and it's exponentially it is going away. You can see this is 4.8, this is 23, and so on. This is 500. R dot, if you see R dot, here is R dot is also increasing. So the rate at which this distance is increasing, that rate is also increasing, but still the acceleration in that radial direction is 0. So you can have motion in which R increases, R dot also increases, but then the radial acceleration is 0. Transverse acceleration, that means acceleration in theta direction, and that is R theta double dot and minus plus 2 R dot and theta dot. So go in the same fashion, theta double dot, theta dot is fixed, theta dot is fixed, theta dot is d theta dt, and that is fixed, that is omega. Okay, this theta dot is omega, so theta double dot is 0. 2 times R dot and theta dot, theta dot is omega, and R dot is this omega R naught, so omega here, R naught here, and e power omega t. So that is the acceleration in theta direction, transverse direction, in this direction. This is that theta direction. So this direction there is no acceleration, this direction you do have acceleration, and it is this much, and therefore the acceleration is in this direction. Since there is no radial acceleration, this theta cap direction, that is the direction of the acceleration. So the entire acceleration is in this direction, and this is the magnitude. And tangential acceleration, AT you can write, tangential acceleration. What is that? Acceleration in along this tangent. If this is the path, then this is the tangential direction, and in that tangential direction what is the acceleration? So in theta cap direction you have acceleration, full acceleration is in theta cap direction. So if you need a tangential component, you just multiply by cos of that angle. Okay, and since we have seen that cos of this angle is 45 degree, this angle is 45 degree, cos of 45 degree is 1 by root 2, and therefore this is a theta times 1 by root 2. This also, this a theta is also a full acceleration. So this is root 2 times omega square R naught, and then e power omega t, or e power theta if you so wish. So that gives you the tangential acceleration. Then the next part is show that this tangential acceleration is dv dt is equal to dv dt, rate of change of speed. Okay, in circular motion you must have studied the radial acceleration is v square by r towards the center, and the tangential acceleration is dv dt, rate of change of speed. So that we generally do for circular motion, but here if I do this dv dt, what is speed? Here is the speed, this is the speed. So v is equal to square root of 2 omega and then r naught and e to the power theta, which is omega t. So dv dt is equal to rate of change of speed, square root here, omega here, and 1 omega will come from the differentiation, so omega square here, r naught here, and e power omega t here, and you match. So in this case also, even if the path is not circular, the tangential acceleration, component of acceleration towards the tangent, is given by this dv dt, rate of change of speed. So we close the session here, and you can do more practice with the book Kleppner if you can get, that is the base book which I am following at least for this problems solving. So you can do more practice yourself. So today is the session for solving problem, and maybe next session also will be on problem solving, and maybe next to next section will also be on problem solving. So I start with a problem which is based on this book by Kleppner and Kolonkov, and this particular problem is based on question number 4.13 of Kleppner, and it says that the potential of a particle of mass m by 2 is given by u equal to epsilon then r naught by r to the power 12 minus 2 r naught by r to the power 6. The questions are: A, sketch the function. The second part is find the equilibrium separation. Find the equilibrium separation of the particle from the origin. And the third part is find the frequency of small oscillations about the equilibrium point. So it is based on, it's not 4.13 of that book, it's based on that. Okay. Essentially it is a one dimensional problem. You are talking of equilibrium position, you are talking of frequency of oscillation about that equilibrium position. So it's essentially a one dimensional problem. And you may be wondering why m by 2, why not m? That will become clear after a few lectures. So sketch the function, sketch this function. So I have to write r and this u. And how do I sketch? The first thing is that are there points where this u is 0? So I want to know whether this curve cuts this r axis or not, and if it cuts, then at which points. So to sketch, let us do all those exercise. If u is equal to 0, if u is equal to 0, that means r naught by r to the power 12 is equal to 2 times r naught by r to the power 6. So if I take the sixth root, it is r naught by r to the power 2 is equal to 2 to the power 1 by 6, and then here r naught by r. Right? I am taking sixth root, the whole thing to the power 1 by 6 here. So that will make it 2, and 1 by 6, this will be 1, and this will be 2 to the power 1 by 6. And that means r naught by r is equal to 2 to the power 1 by 6. So r is equal to r naught divided by 2 to the power 1 by 6. So you get only one value, you get only one value of r where u is 0. And that value is slightly less than r naught, because 2 to the power 1 by 6 will be more than 1. So you are dividing by a quantity which is more than 1, so this will be smaller than this. So on this graph, if I need more space. So suppose this is my r here, this is u here, and this point is r naught, and this r which makes u equal to 0 is somewhat less, so suppose it is here. That's one. It will cross this r axis only at one point. Now what happens if r is very small? If r is very small, so this is u. If r is very small, you have 1 by r which is very large to the power 12, and here you have 1 by r to the power 6. This is also very large, but this thing is the square of this. 1 by r to the power 6 is also very large, but then square it, it will become very much larger, and this will be this factor. That means for very small r, this will be much larger than this, and so this whole quantity is positive, right, and going to infinity. For very small r, this will go to infinity, this is also going to infinity, this is also going to infinity, but this is a much bigger infinity, and the whole thing is positive and going to infinity. That means for very small r, it is coming from here. That's one. Then you have what happens if r is very large? If r going to very large values, this is going to 0, this is also going to 0. So ultimately it has to go to 0. So that is another information. And then what you have is that where are maxima and minima. So, we have the information that for small r it is very large, for large r it is going to 0, and then in between what happens? For that, let us look for the maximum minimum. So, du dr, let us look for du dr. Now, du dr, if you differentiate, it will be epsilon here, then 12 times r naught by r to the power 11, okay, 12 times r naught by r to the power 11. That means I have differentiated this term with respect to r naught by r, and so I have to multiply by differentiation of derivative of r naught by r with respect to r, which will be minus r naught by r square. So, it is minus r naught by r square, this. So, the first term we have differentiated. Come to second term, minus 2 into this 6, that is 12. So, 12, and then r naught by r to the power 5, right, 6 is here. So, 6 will come to this side, 2 into 6 will be 12, r naught by r to the power 5, then differentiation of r naught by r with respect to r, which will be once again minus r naught by r square. That is du dr. So, let me write it in a somewhat more manageable fashion. Du dr is equal to epsilon and then square bracket. Now, it is 12 here, 12 you can take out if you so wish. So, 12 I can write somewhere here, let us write it somewhere here. Then it is minus r naught to the power 12. So, minus r naught to the power 12, and then r to the power 13, right, r to the power 13. So, divided by r to the power 13, and then here you have plus, and 12 we have already taken. So, r naught to the power 6, so plus r naught to the power 6 and divided by r naught to the power 8, r naught to the power 6 divided by r to the power 8, divided by r to the power 5 from here, and r to the power 2 from here, so r to the power 7. This is r to the power 7. This is du by dr, right. Now, if this is 0, if this is 0, if du dr is 0, that means r naught by 12 divided by r power 13 should be equal to r naught 6 here and r to the power 7 here, and therefore, r naught to the power 6 divided by r to the power 6 should be equal to 1, r should be equal to r naught. Because I know that in the beginning it is very high, and the end it is 0, going to be 0, and there can be only one maximum or minimum. So, that has to be minimum, that cannot be a maximum. So, it will decrease, it has to go to this point where it crosses this point, it becomes negative there, then it has to be a minimum here if it wants to reach this 0, and that minimum must occur at r equal to r naught, and then it will go and then it will gradually approach 0. So, that is the kind of sketch we have. This is the kind of potential energy function. If the particle is somewhere here, the potential energy is positive. If the particle is here, potential energy is 0. If the particle is here, then the potential is negative. If the particle is here, it is maximum negative, and then gradually the potential energy again increases, right. So, that is A part. B part, find the equilibrium separation of the particle from the origin. So, equilibrium positions mean the force is 0, it stays there, that is the equilibrium position. That happens when this potential energy is minimum, because force is given by negative of du dr. So, if force is 0, du dr is 0, and therefore, the equilibrium position will be at r equal to r naught. So, this is also done, the equilibrium position will be this will be the answer, r equal to r0, this is that equilibrium position. What does that mean? If you put the particle at r equal to r naught, okay, if you put the particle at r equal to r naught, it will stay there in equilibrium, it will not move. So, that is the meaning of this. This is essentially one dimensional motion. If it is two dimensional motion, r equal to r naught means a circle, okay, but here it is this equilibrium position, the force is 0. Then the C part, find the frequency of small oscillation about the equilibrium position. So, if the particle is here and the energy is just this, if this is the energy, if this is the total energy and total energy is equal to the potential energy, total energy is equal to the potential energy, then the kinetic energy is 0 and the particle does not move. But if the energy is more, if the energy is more, then the particle can move, and we have already discussed these are the turning points. These are the turning points. This is, let us say, R1 and this is R2, and the particle with this energy, it will go from here to here, here to here, here to here, here to here. That means from the origin the distance will change and it will stay between R1 and R2. So, these are the turning points. So, this is the kind of motion, but frequency of small oscillations, that means the energy is such that you have you are using only this much. So, your energy is very close to that required for equilibrium. So, somewhere here, so it goes in a oscillation here, and if it is small, then this portion can be approximated to a parabolic curve, and then it will be SHM. And we will see, I have to do some calculations, I can perhaps do it here, that for small oscillations it can be treated as an SHM, and then we can get the frequency from the SHM equations. And how do I do that? I go for this expansion of u around this point R naught. Okay. So, u is equal to, this is called Taylor series. It says that if you have to get u as a function of r and you have a point R naught which is very close to it, you can write it as u at R naught and plus du dr at r equal to R naught and then multiplied by r minus R naught plus then half of second derivative d2v dr square evaluated at r equal to R naught and multiplied by r minus R naught square, and similarly higher order terms coming in there. And if r is very close to R naught, perhaps you would like to neglect this r minus R naught square term in comparison to r minus R naught term here. You do have r minus R naught cube terms and 4th power and 5th power, but if this separation is small, if this quantity is small, then you can neglect higher order terms. Now, in our case du dr at r equal to R naught is 0. This is r equal to R naught and here du dr is 0, and therefore, this term is not there, and so I cannot neglect this in comparison to this, and so I have to evaluate this. We can do that u. So, we can do that, and it's du dr is here. So, let us calculate what is d2u dr square equal to 12 epsilon minus r naught to the power 12, r naught to the power 12, and then you have to differentiate r to the power minus 13. So, minus 13 here and then r to the power minus 14. So, r to the power 14 in the denominator, right. I have written minus, I have written r naught to the power 12 which is constant, and then I have to differentiate. So, I am differentiating r to the power minus 13. So, minus 13 r to the power minus 14, r to the power minus 14 is written as r to the power 14 in the denominator. Now, come here plus r naught to the power 6. So, this is r naught to the power 6, and then I have to differentiate r to the power minus 7. So, minus 7 here and then r to the power 8 here. So, that is the differentiation. So, let me, and it has to be evaluated at r equal to R naught. So, if I write r equal to R naught, so this every r becomes R naught, r equal to R naught. Then what happens? Then it is 12 epsilon, this minus and this minus is plus, r to the power 12 divided by r naught to the power 12 divided by r naught to the power 14. So, it is r naught to the power 2. So, it is 13 divided by r naught square, the first term. The second term is minus here and 7 here and divided by r naught square. So, this is 12 epsilon into 6 divided by r naught square. So, it is 72 epsilon divided by r naught square. Now, look at this term, u r is equal to u r naught and then plus half of this quantity d2u dr square at r equal to r naught. So, that is 72 epsilon divided by r naught square and then r minus r naught square. Compare with u x equal to half k x square. This is our SHM equation. Potential energy of a particle undergoing simple harmonic motion F equal to minus kx. So, that k is here, the potential energy is given by half k x square. There we choose 0 of potential energy at x equal to 0, right. So, around that, and you know potential energy is always arbitrary to an additive constant. So, it does not matter where I take my potential energy to be 0. So, this is just a constant shift, okay. And then this is the equilibrium position, and here this x is also from equilibrium position. So, separation from the equilibrium position is square, same story, and this does not matter. You can take any point and say that okay, my 0 is here, potential energy 0 is here. So, a DC shift can always be done. So, it is identical to this. This will be an SHM. If this is the equation, this is HM. Of course, this is an approximation because we have neglected the third power, fourth power and sixth power, but if r is close to r naught, we can do that. And so, this motion will be approximately SHM. For small change in energy, the motion will be approximately SHM, and what will be the frequency? So, for SHM, you know, angular frequency is square root of k by m. So, the same equation here, in our case omega is equal to square root of k. In place of k, I have the 72 epsilon naught by r naught square. So, 72 epsilon naught by r naught square and divided by m, and mass of the particle here is m by 2. So, we divide by m by 2. So, I put m here and into 2 here. And 72 into 2 is 144, a perfect square, square root is 12. So, this is 12 times epsilon naught divided by m r naught square. Okay. So, epsilon naught is in our habit, when we do electrodynamics, we write epsilon naught so many times. So, this is the angular frequency, and you know the frequency as such is this angular frequency divided by 2 pi. Let me take one more question, and this will be proper two-dimensional central force motion. And the question is based on 9.2 of our Kleppner-Kolonkov book. A particle of mass m moves under an attractive central force F of r is equal to minus k r cube. The angular momentum is L. The angular momentum of the particle and obviously about the origin is L. The maximum distance of the particle, from the origin is double the minimum distance and the question is find this minimum distance. Okay, so force F is F is minus kr cube. So write what is potential energy U. U will be what? You have to integrate. So k into r to the power 4 divided by 4. This will be the potential energy. If you differentiate it with respect to r, you get kr cube, and put a minus sign, you get the force. So this is potential energy. What is V effective? We have used this terminology. V effective, it is L square by 2 mr square, and then the actual potential energy, which is plus kr to the power 4 by 4, kr to the power 4 by 4. This is the effective potential energy. And if you draw the potential energy, how will it look like? If this is r and this is V effective, and if I draw this, if you take very small values of r, this is negligible, very small value, so it's going to 0. Very small values, this is going to infinity, so it comes from infinity. All the time it is positive, r square here, r4 here, all the time it is positive. I don't have to find a point where it crosses this r axis. And of course, I can look at the large r values. For large r values, this will be 0, but this will go to infinity. So it starts from infinity and it goes up to infinity. What happens in between? So look for the maxima minima, V effective, and then differentiation of this with respect to r. So if you differentiate, you have minus L square by mr cube. This term will always occur, so I remember it. And then here, when you differentiate, it will be plus kr cube. If it is 0, if it is going to be 0, then you get L square by mk. L square by mk is equal to r to the power 6, the sixth power of this. This is the place where this will be maximum or minimum, and the only one value, you get only one value of r. So only one maxima or only one minima is possible. This is infinity, this is infinity, it is always positive, it has to be a minimum. So your function will be something of this type, and this will be the minimum. Now it is said that the maximum distance of the particle from the origin is double the minimum distance. So that means the energy is something like this. This could be the total energy, and here are the turning points. This is that minimum distance, let us say r naught, and then this is another turning point, and this will be 2 times r naught. Okay, if this is the total energy, then the particle cannot come this side and cannot go that side. It has to remain in this, so that half m r dot square is always positive, it cannot be negative. Here that r dot is 0, here this r dot is 0. So these are the situations. You have to find the value of r naught. How do I get that? At this point and at this point, the total energy is same as this effective potential energy. That is why that half m r dot is 0. Total energy is half m r dot square and plus L square by 2 m r square and plus u of r, potential energy here, V or u, I don't know what I have written. So this is the kinetic energy and this is the potential energy, but then we combine these two and write this as V effective. So the total energy is your effective potential energy and plus half m r dot square. So here that r dot is 0 and u is same as the V effective. That means V effective here at r naught, and that is L square by 2m r naught square. Okay, at this point, what is the effective potential energy at this point, minimum distance? So r is equal to r naught. So I am writing r naught here, and then plus the potential energy at r naught, which is equal to the effective potential energy at this point. So effective potential energy at this point is L square divided by 2m, 2r naught square, and then plus effective potential energy I am writing at 2r naught, like this. So I have written u here, so I should have written u here, I should have written u here, I should have written u here, and yeah, V effective is fine. Okay, so this is u at r. So this is a situation, I can write L square 2m r naught square plus u at r naught. What is u at r naught? K into r naught to the power 4 divided by 4. So k into r naught to the power 4 divided by 4 is equal to L square divided by 2 into 2 is 4, 4 into 2 is 8. So 8 m r naught square plus this is k by 4 and then 2 r naught power 4. The potential energy at 2 r naughts, it is this. So, this is 16 by 4 is 4 here. So, I have this L square minus 2 m r naught square, this one, and minus this one, minus L square by 8 m r naught square is equal to, this is 16 by 4 is 4 k r naught to the power 4 and minus k r naught to the power 4 by 4. Alright, so easy to calculate, L square by 2 m r naught square, and then you have 1 minus 1 by 2 I have taken, so 1 by 4, correct. 1 by 8 here, 1 by 2 is here, and 1 by 4 is here, and this side k r naught to the power 4, and then you have 4 minus 1 by 4. Alright, so this is 3 by 4, this is 3 by 4, so 3 L square divided by 8 m r naught square, and on that side it is 15 by 4, 15 by 4 times k r naught 4. That gives you, let us take this r naught square on this side, so this will become r naught to the power 6, r naught to the power 6 equal to, and everything rest will be on the other side. So, this I can make it, okay, let me write. So, 3 L square by 8 m, 3 L square by 8 m. From this side I had taken this r naught square there, so it is 3 L square by 8 m, and from that side I have to bring this thing. So, this 15 k will come in the denominator, so 15 k here, and this 4 will go in numerator, so 4 will go here. So, this will be what? 3 and 15, so 5 here, 4 and 8, so 2 here. So, it is L square and divided by 10 km, 10 mk, and therefore, r naught is equal to, minimum distance is equal to 1/6 power of this, that means it is L square by 10 mk to the power 1 by 6, and that is the answer. 1 by 6, that is the answer. L is given to us, mass of the particle is m, and k is given to us, a particle of mass m. So, that is our minimum distance of the particle from the origin. So, this is our question. A particle of mass m moves in a circular orbit under the force Fr equal to minus Kr. You know what kind of force is this? You can have a spring attached to mass and so on. In that Kleppner book, that figure is given where spring is attached with the mass, and this kind of force is applied with a total energy u naught. So, total energy u naught is given. Find the radius, the speed, and the angular momentum of the particle. So, let us go one by one. So, the first part is find the radius, speed, and angular momentum. So, once again we can use our knowledge of circular motion. Force is Kr towards the center, that should be equal to m times v square by r. So, this is one equation. So, m v square is equal to Kr square. We have to get the speed as well as the radius. So, two unknowns are there. But then the total energy is given u. The total energy u naught is equal to half m v square, kinetic energy, and potential energy. If F is minus Kr, you very well know it is half Kr square. Okay, it is half Kr square. If you differentiate and put a minus sign, you will get force. So, plus half Kr square. So, these are the two equations, and you have two unknowns. To get mv square, you can write this, you can use this, u naught is equal to half mv square and plus half Kr square, which is again mv square, so which is m times v square, and therefore v is equal to square root of m u naught divided by m, u naught divided by m. So, that is the speed, and radius you can obtain from anywhere. So, r square is equal to, or here itself for radius we write u naught is equal to half Kr square plus Kr square half. So, this is equal to Kr square, and r is equal to square root of u naught by k. So, that is the radius. And angular momentum, if it is going in a circle, and angular momentum means obviously angular momentum about the center of this circle. So, if this is the circle, if this is the radius, and if this is the velocity, if it is going in circle, the velocity has to be in tangential direction, and therefore L will be just m times v times r, and that will be m square root of u naught by m and into u naught by k, m into v into r. So, this is v, this is r. So, it is this. Okay, this will be square root of m square goes here. So, m here, u naught square here, and by k here. So, that is the first part. Right, mass into speed is square root of u naught by m, and r is square root of u naught by k, and therefore it is under root m u naught square divided by k. Now, a sharp blow is given to the particle in the radial direction so that it achieves a small radial speed v. The particle is going here with this speed v, which is written here, and then it is given a sharp blow in this direction, radial direction. A force is applied for a short time in this direction. What will this force do? It will create a velocity in the radial direction, but this tangential velocity will still remain the same, right? So, and that velocity which is achieved here is capital V, that is given. So, that it achieves a small radial speed v. Find the maximum and minimum distance of the particle from the original center. So, originally the particle was at this distance given by this equation, but now that you have given extra energy, the particle will not go on circle, but it will remain in the vicinity of the circle. So, we have to find the minimum and maximum distance from the origin. How do we do that? We write now the initial total energy is equal to half m v square, and initial total energy, let me write. So, half v square, this v. So, let me call it v naught square, this v, and plus half m this capital V square, and then the potential energy half k r square. Okay, this is the total energy. Kinetic energy, now I am writing for a general r as such. The kinetic energy initially is, okay, let me write initial. So, this is the energy. So, initially the velocity is v in this direction, capital V in this direction, and therefore the kinetic energy will be half m net v square, but that net v square will be this square plus that square. So, that is the kinetic energy, and then the initial potential energy at the time of just before, just after the blow, let us say just after the blow, the kinetic energy is this and potential energy is half k r naught square, where r naught is this is r naught. Alright, so this is it. We can write the values also. Half m v naught square will be half and then v naught square. So, this will be u naught, correct, half m v naught square. So, m v naught square will be u naught. So, it is this, and then plus half m v square, it is given to us, and then half k r naught square will again be this. So, it is again half u naught, and you have just increased the energy by this half m capital V square. So, this is the energy. What is that effective potential now? V effective, it is L square. Now, I am going for a general R in this motion, L square by 2 m r square, and then plus the potential energy is half k r square, right. After the blow, it is going in some path in xy plane, and in that situation this is the actual potential energy, and L square by 2 m r square is that term which is coming, and then this is the effective potential energy. Plot it. How it will look like? All the time positive. There is a one minimum, never crosses 0, all the time positive. There is one minimum, and therefore the shape will be of something like this. And here is that u naught. Here is that u naught. If the energy is u naught, it is going in the circle. So, it has to be this lowest point where you have only one value of r possible, and that is r naught, right. But now the energy is more. So, energy is here. This is the energy, and therefore you have two turning points, r1 and r2. this is R1, which is the minimum distance from the origin, and this is R2, which is the maximum distance from the origin. We are asked to obtain this R1 and R2, and you know that here this U is equal to value of this effective potential energy, that is L square by 2m R1 square and plus half k R1 square. And here the same equation, L square divided by 2m R2 square and plus half k R2 square. So now you have the equation. So essentially what is it? It is U is equal to L square by 2m R square and plus half k R square. It is this equation which will give you two values of R, one will be R1, one will be R2. And now you can write. So it is U naught is original. So now you can write the values also, you are given what is U naught and all that. So it will be U naught plus half m capital V square is equal to L square by 2m R square and plus half k R square. Okay. So multiply by R square if you so wish, you will have half k R to the power 4, this term here, then take this whole thing on that side, it is U naught plus half m capital V square and into R square. So we are multiplying the entire equation by R square and collecting on one side. So this into R square goes to the right, and then you have this term here plus L square by 2m, right, is equal to 0. So everything is there, k is there, k is 3 in SI units, then U naught is there, this is 12 joules, mass is there 2 kg, and this mass is given L square you have already calculated. What is L square? Here is L square, that is also known. And remember, in the radial blow L has not changed, okay. Since the blow was in radial direction, this component, when you write angular momentum R cross P or m times R cross V, this component will not give you any contribution and the angular momentum is still there. So this original angular momentum that we had calculated can be obtained from, can be put there. So it's a quadratic equation. It's a quadratic equation, and you find the two values using your class 9 algebra, and the two values of R square you will obtain, and then take the positive square roots, those will be R min and R max. So if you do it correctly, you should get R min and R max, which are root 8 by 3 and root 6 meters. Okay, so that is how you can get these values. So let us do some more problems on central forces, especially inverse square attractive central force. And the first question is this: an object of mass m is projected from the earth's surface at an angle of 60 degrees from the vertical with a speed v naught equal to square root gm by r, where m is the mass of the earth and r is its radius. So you have earth, and then you are somewhere here, this is vertical, and from the vertical making an angle of 60 degrees, the particle is projected with some speed v naught, which is given here. And then the question is, find the maximum height the object attains. So you must have done such problems in class 11 or maybe even before, but then the speeds were in meters per second, and here the speed is much larger. It is in terms of mass of the earth and the radius of the earth, and the speed is square root of gm by r, which will be in kilometers per second. So that is why the approximation of constant g cannot be taken here. So we know this particle will be attracted by the earth, and the force of attraction will be minus gmm over r square, which is of the type minus k by r square we have studied, with k is equal to gmm. So it is inverse square attractive force under which it is traveling. So it will go in an elliptical path and hit somewhere. So we want to know, maybe it will hit somewhere or may not. This is the maximum distance, this is the maximum height. You know, height is the distance from the center. So I should draw a slightly better diagram. Okay, it won't be better because it's not circle. Fine. So we need this R max from the center of the earth, the farthest distance, that is the height, maximum height that is obtained. In fact, this is the maximum height minus this capital R, but nevertheless we will call this as R max in our terminology. So it is going in ellipse and I want to know what is R max. Okay. So what should be our strategy? We have to get this maximum value of R, and you know, this maximum value of R for inverse square attractive force is given by L square by mk and divided by 1 minus eccentricity. This is R max, and R min is this quantity divided by 1 plus E. And what is this E? Eccentricity. This is the square root of 1 plus 2 U L square divided by mk square. So our plan will be to calculate L and U. L is a constant of motion, U is a constant of motion, and we can get the values of L and U from this initial point. We can calculate L here, we can calculate U here, and those values will remain same as it goes in this elliptical orbit. Okay. So we calculate U and L. Once we calculate U and L, then we can calculate this E. And once we have this E here and L we calculate, then we can calculate this R max. So that is the strategy. So let us calculate L and then U. So what is L? At this point what is L? M into V into R into cos sine whatever sine 60 degrees, right? Because only this component, this tangential component will contribute in L, R cross P. This radial component R cross P, this will give 0. And this component is V naught sine 60 degrees. So mass into this V naught sine 60 degrees into distance capital R, that is our L. So this is M, and V naught is given to us G capital M by R, and then this R here, and then this sine 60 degree root 3 by 2. So let us take everything inside. Let's take everything inside this square bracket. So this is R here, this is R here. So let's take everything inside. This M becomes M square, capital G is there, M is there, this R will come inside as R square, and with this R it will be capital R here, then 3 by 4, so 3 by 4, that is L. And this L is calculated at this point, but this is the L everywhere in the whole of the orbit, whether it hits here or whether it goes in another path or whatever it does. Okay, then U. U is kinetic energy half V naught square, and potential energy, we are talking of this point, minus G M M over R. At this point the distance is R, so it is this, and this is half M. V naught square is G M over R, that is V naught square, and then minus G M M divided by R. If you take this G M M by R common, it is half minus 1, so it is minus G M M over 2R. That's it. Now let us calculate this eccentricity E, and for that you have this equation. So first let us calculate this quantity. 2U L square divided by mk square is equal to 2 into U. U is minus G M M over 2R into L square. L square is 3 small m square, then G M capital R and divided by 4, that is L square. So 2U L square divided by mk square, m, and k is G M M square of that. So G M and then small m and square of that, so G M square and m square. It's like this, k square G M square and m square, so m square G M square, that is our k square, and this m here. And now see what simplification can be done. So you have Gm here, you have Gm here, and you have Gm square here, so they cancel out, right? Then you have m here, you have m square here, that is m cube, and you have m here and m square here, they cancel out, m cube cancel out. you have this r here, you have this r here, you have this r here, that cancels out. So, what is left? Only the numbers, only the numbers. And what are those numbers? This 2 can be cancelled with this 2. So, it is minus here, and then this 2 is already gone, this r is gone, GMM is gone, into 3 by 4. So, into 3 by 4 is here, and that is all, and that is all, everything else has cancelled out. So, this quantity is minus 3 by 4, and therefore, eccentricity is equal to square root of 1 plus this whole quantity, and this whole quantity is minus 3 by 4. So, this is 1 minus 3 by 4, and that is square root of 1 by 4, and that is half. So, the eccentricity of this ellipse, the object is going on an elliptical path, and eccentricity of that is 1 by 2. So, what is R max? R max is here, L square by mk divided by 1 minus E. So, R max is equal to L square is here, L square. So, 3 m square G capital MR divided by 4, that is L square, divided by mk, small m and k is G m m, right, G m m, k is G m m. So, we have written L square, that is L square, then divided by m, and then this k, and so this is L square by mk divided by, the whole thing divided by 1 minus eccentricity, that means 1 minus half. So, once again you have m square, m here, and m square here cancel out, g into m cancel out, and what is left? 3 into r here, and then 4 here, and then half here, that will go up, so that will become into 2, and this is 3r by 2. This is R max. From the center to the highest point is 3r by 2, and therefore, the height, maximum height is 3r by 2 and minus r, and that is r by 2. So, that is the maximum height over the ground. So, our next question is this. You have this diagram and read the question in its reference. A spacecraft is going in a circular orbit of radius 2r around the Earth. So, here is the Earth, and this spacecraft is going in a circular orbit of radius 2 times r, where r is the radius of the Earth. It is to be taken in a circular orbit of radius 4r. So, it is going in this orbit, but then it is to be taken in this circular orbit whose radius is 4r. The first part is, what is the minimum energy to be spent in this operation? So, minimum energy to be spent is same as the increase in energy as it goes from this circular orbit to that circular orbit. That much we have to do if there is no other waste. Okay, so part A, energy in orbit of radius 2r. So, when it is in this circular orbit, what is the energy? So, you can write that energy, you have total energy is equal to kinetic energy plus potential energy, and the kinetic energy you can easily write, if m is the mass of the spacecraft, mv square divided by the radius 2r, this should be the force, and that is g m divided by 2r square. Okay, so this is the force on this spacecraft towards the center, and that force should be equal to mass times acceleration. So, here is the mass and here is the acceleration, v square divided by the radius of the orbit. And so, half m v square is equal to this, r goes on that side, g m by 4r, so that is the kinetic energy, and the potential energy here is minus g m and divided by 2r. So, what is the total energy? The total energy is g m divided by 4r and minus g m divided by 2r, which will be minus g m divided by 4r. has to be negative. For the bound orbit, the total energy must be negative in at least in this inverse square central force, attractive force. Then energy when this goes to this orbit, this circular orbit, in the second orbit. So that energy in the orbit of radius 4r is in a similar fashion. You can write V m times v square divided by 4r is equal to gmm divided by 4r square, and that gives me mv square. Half mv square is equal to 2r will go on that side. So gmm, and here it should have been 16r square, but 2r is here, so 8 times r, right? 8 times r, that is the kinetic energy. And then potential energy, you can write potential energy is minus gmm divided by 4r when it is at the distance 4r. So the total energy is, in this case, is total energy is gmm over 8r and minus gmm over 4r, which is equal to minus gmm over 8r. Very simple. In fact, in place of 2r you have to write 4r, so in place of r you have to write 2r, so it has to be minus gmm by 8r, which is here. So how much is the change in energy between this smaller circular orbit and the larger circular orbit? So the change in energy is equal to this energy minus gmm over 8r and minus the energy in the previous orbit, which is minus gmm by 4r. And how much is this? This is gmm by 4r minus gmm by 8r, so it is plus gmm by 8r. Right, this is positive, this is negative. If this goes to that side, it will add, and then it will be double of this, and that is this. So this much is the increase in energy. That much energy has to be supplied to the spacecraft, and if there are some other form of energy wasted, then that will be more, but minimum this energy is to be spent if you want to take this spacecraft from this orbit to this orbit. So that is part A. So part B, it is to be done in 2 stages. In the first stage, rockets are fired at point A, taking it to an elliptical orbit with the nearest point at a distance 2r and the farthest point at a distance 4r, as shown in the figure. So in the first circular orbit, when it is here, rockets are fired. So what are the rockets going to do? Change the speed, and because of this change in speed, the energy is increased, and it goes in an elliptical orbit. Remember that V effective R graph, it has a minimum. If the radius or the energy is at the bottom of that, it is circular orbit, and if you increase the energy, then you have 2 turning points, R1 and R2. So you have R minimum and R maximum. So that elliptical orbit is here. It is the minimum distance is this much, 2r, and this elliptical orbit, the maximum distance is 4r, and it reaches B. So that is the first stage, to take it from the circular orbit to this elliptical orbit. So this is it, and find the change in the speed at A when the rockets are fired. So this is it. Now, so we are going from the circular orbit of radius 2r to this particular elliptical orbit, and we are asked how much is the change in the speed. So energy when in the circular orbit of radius 2r is, say, E1. We have just calculated it, that was minus gmm over 4r. We calculated kinetic energy, we calculated potential energy, we added to get this energy. There was a simple procedure, and that is, if you remember, the energy is minus k by 2a. For any elliptical orbit under inverse square attractive force, the energy is minus k divided by 2a, and this 2a is the major axis. A is the semi-major axis. So if you have a circular orbit, then this major axis, minor axis are same, and that is here to here, and that is 2 times the radius, and this is radius is 2r, so 2 times the radius is 4r, and k is of course gmm, so it is minus gmm, and divided by this is the radius, so it is 4r. So there is a simpler way of doing it, and I will be using it for the elliptical orbit. Okay. Now for the elliptical orbit, energy when it goes to the elliptical orbit, E2, let us say that E2 will be equal to minus k by 2a, so minus gmm by 2a. What is 2a? This minimum distance here is 2r, and the maximum distance here is 4r, and the major axis is 2r plus 4r, that is 6r. So it is 6r. So this is the energy, it is here. From here you can get the velocity, because half mv square and minus gmm by 2r, that is the energy, kinetic energy and plus potential energy is equal to minus gmm over 4r, and therefore half mv square is equal to, this will go to that side and it will be gmm over 4r. So m cancels out, and therefore v square is equal to 2 goes here, gm by 2r, and so v is equal to square root of gm over 2r. And what happens here? Total energy is given. The total energy is half mv square, that is the kinetic energy, and minus gmm. Remember, I am here, we are talking here, we are going in a circular orbit, and now we are changing to elliptical orbit, and what is the change in the speed that is asked? So the potential energy remains the same, minus gmm by 2r, and this is the total energy. So this is equal to this and this. So what is half mv square? Half mv square is equal to, this comes to this side, gmm over 2r, and then minus gmm over 6r. So 6r here, and this is 3 times, and this is minus 1 times gmm. So this is gmm over 3r, and therefore v square is equal to, m will cancel out from here and here, and this 2 will go there, so 2 times g capital M by 3r, and so v is equal to square root of 2 gm over 3r. So when the rockets are fired and it goes in the elliptical orbit, the energy is increased, and the new energy is given by this quantity, and that is sum of kinetic energy and potential energy, and from there you can calculate that the new speed should be this, old speed was here, and therefore the change in speed is equal to this energy, final energy, square root of 2 gm over 3r, and then minus square root of gm over 2r. That is it. So if you take this square root of gm by r common, what you are left with, square root of gm by r common. So this is a square root of 2 by 3, this is square root of 2 by 3, and then minus square root of 1 by 2. So square root of 1 by 2, and check that this is positive. It must be positive. We have given energy, we have increased the speed. The total energy is more in elliptical orbit. So this is 2 by 3, that is 0.67 or so. This is 1 by 2, 0.5. So this is positive. So this much of increase in speed is occurring at this point A. All right. So that is part B. Part C. In the second stage, rockets are fired when the spacecraft is at B. Here, the rockets are fired here in its elliptical path. This takes the spacecraft to the final circular orbit, that means to this final circular orbit of radius 4r, and again you have to find the change in the speed in this operation. So exactly similar procedure. You know how much is the total energy when it was in elliptical orbit before firing the rockets, and that is here, energy when it goes to this. So this is the total energy in this elliptical orbit, And when it goes to the circular orbit, what is the energy now? So you know that the radius is 4r, so it will be minus k by 2a. You can use that and you get the change in the speed. So let us do some more problems on central forces, and the first problem is here. A particle is subjected to a central force Fr r cap. This is the definition of a central force. Define u equal to 1 by r and find the differential equation of the path of the particle in terms of u and its derivative. So we had obtained path of the particle, especially for the attractive inverse square force, and that was r as a function of theta. So when you give the relation between the coordinates, you get the path. Here you are asked to work not in r but in u, which is 1 by r, and then find the differential equation of the path. Means u as a function of theta will give me the path, but what we need here is differential equation in terms of u, du d theta, d2u d theta square, and so on. So let us start with it. We know that the radial acceleration is ar, which is r double dot and minus r theta dot square, that is this, and this is the force divided by mass. Force is equal to mass into acceleration. It is a central force, so the entire force is in the radial direction, and therefore radial acceleration is just force divided by mass. Now we start from here. What is this r double dot, what is this theta dot, and so on. And you know that for central motion a constant of motion is angular momentum, which is mass, and then of course the mass of the particle is m. So m r square theta dot, and from here you can write what is theta dot. Theta dot is L by m r square, and that is L by m u square in the numerator, because 1 by r is u. So this theta dot we will write from here, r double dot. Okay. So r is equal to 1 by u. So r dot dr dt, r dot will be minus 1 by u square, that is differentiation with respect to u, and then du d theta, because u is a function of theta, so du d theta, and then differentiation of theta with respect to time. Ultimately this is dr dt, so you have to differentiate in terms of time, with respect to time. So it is this and then theta dot, and that you can write minus 1 by u square du d theta, and theta dot is L u square by m, so L u square by m, and this u square cancels with this u square, and you have minus L by m du d theta. So that's the advantage of working in u. You get simpler things like this cancel out and so on. It will be clear further. And then r double dot, we need r double dot. So r double dot means we have to differentiate this thing with respect to time, and that will be minus L by m d2u d theta square, and then theta dot, differentiation with respect to theta, and then differentiation of theta with respect to time. That gives me the time derivative of this r dot, which is r double dot. So let us put these things in this equation here. So r double dot is minus L by m d2u d theta square, and then theta dot. In fact, I can write this theta dot from here itself. This is equal to minus L by m d2u d theta square, and theta dot is L u square. So this is L here, u square here, and divided by m, so m here, and that same thing comes here, L u square by m. This is what I am writing this equation ar. R double dot, only this part is here. R double dot is minus L by m d2u d theta square L u square by m. Then minus r, this r is 1 by u, and then theta dot square. Theta dot square is L square u4, so L square u4, and divided by m square, and that is equal to force, this function r, function of r, f at r, this is the force. We will write it as f of u. This will be f in terms of u divided by mass. Okay. Now this functional form is somewhat different if you write in terms of r, if you write in terms of u. For example, if fr is 1 by r square, then fu that I am writing there is u square. So I am writing this r as 1 by u and it becomes u square. So in principle this is a different function and this is a different function. This is a square and this is 1 by square. So in principle I should have written some other symbol here, but I will continue with this and you understand what I mean. This functional form which is given in terms of r, so that has to be just converted into u and that I will be writing there. Okay. So let us see what it is. So you have this u and here fourth power becomes third power, and this thing I want to separate out. So first let me do some simplification. This is d2u d theta square, and let me put plus sign here and minus sign here. Okay. Then it is L square, so L square, and then I have u square, so u square divided by m square, so m square here, plus L square and divided by m square here, and u to the power 3, so u to the power 3, and this is minus f u divided by m. So divide by this quantity, and this quantity is common here and here except for this u here. Here you have u square, here you have u cube. So if I take that as common, L square u square by m square, and then bracket d2u d theta square and plus u from here, and that is equal to minus f of u divided by m. And take this quantity on the right hand side. So you have d2u d theta square plus u is equal to this quantity goes to the right hand side, m square divided by in fact 1 m I can cancel out from here itself, this power m square, so it's just 1 m, I can write 1 m here, and then divided by L square u square, so L square and u square, and that is it, fu, and this minus sign here. Okay. So d2u d theta square plus u is equal to minus of fu, so minus of fu multiplied by m divided by L square u square. So this is the differential equation. This is that differential equation which we are looking for. This functional form of force whatever is given is here. L is a constant of motion for that entire path, entire motion, so it is here. Mass of the particle is known, and then you have u square, you have derivative of u. So this is that differential equation. If you think of that inverse square attractive force that we had been talking, then this f of r is minus k by r square, and therefore f of u I will be writing minus k u square, and if you put it there, your equation will be d2u d theta square plus u equal to, in place of this fu you write minus k u square. So what happens? This minus and this minus will become plus, and then you have to write k u square. So u square will cancel, k will be there, so it will be mk by L square. It will be mk by L square, and if you define u prime is equal to u minus mk by L square, if you define another quantity u prime, this is just a constant because angular momentum is constant in the entire motion. So it is u minus mk by L square. So d2 u prime and d theta square is equal to d2 u d theta square, and then this equation is d2 u prime d theta square and plus u prime equal to 0, and this equation is very well known to you. Simple harmonic motion, you do this similar kind of thing, d2x dx, d2x dt square and plus omega square times x is equal to 0. That is the simple harmonic motion equation. So you know the solution, and you can write the solution as u prime is equal to some constant a cos omega t, omega is 1 here, so it will be not t here, theta here, so cos of theta and minus some theta naught, two arbitrary constants, this and this. Okay, you can choose theta equal to 0 in such a way, you can choose the x axis in such a way that this theta naught turns out to be pi, and then you will have u prime is equal to a cos theta with a minus sign, and therefore u will be what is u prime plus this, so u prime plus that, so mk divided by L square and plus u prime, and this will be cos a plus a cos theta or minus a cos theta, we will just check minus a cos theta, right. U is equal to u prime plus mk by L square, so mk by L square is here plus u, right, plus this u prime, u is equal to this plus u prime, and what is u prime? U prime is minus a cos theta, so it is minus a cos theta, and if you take common, you can write this as mk over L square and 1 minus e cos theta, where e is another constant. This is just a constant which is coming in this integration. So this is another constant in terms of this and other quantities, and this is 1 by r, and this is 1 by r. Therefore, r is L square by mk divided by 1 minus e cos theta. That is what we had told, that by integrations of that r dot, theta dot, all those things, we can get this equation of path. So you can get it so easily from this equation. So this is another question. A particle is subjected to a force Fr is equal to minus k by r square. This is the usual inverse square attractive force. But then there is another term minus delta over r cube, with the second term being very small as compared to the first term. So this is a small perturbation in this inverse square attractive force. Show that the path of the particle is like an ellipse under proper initial conditions. That means the energy should be negative and all that. That proceeds slowly at a constant rate. So that's the question. So our equation of orbit in terms of u, we had just derived d2u d theta square plus u is equal to minus m over L square u square fu. Use this here. So this will be equal to minus m over L square u square, and then f of u will be minus k u square. So minus k u square and then minus delta u cube. This is fu. This you can simplify. This will be mk by L square. So this will be mk by L square here, and this will be plus delta by L square and u here. This delta, then u square and u cube gives you u, and then L square here by this minus is plus. Take this on the left hand side. So you have d2u d theta square and then plus u, and then you have 1 from here and minus delta by L square here, and I have missed m here, so m here, this, and is equal to mk over L square, right. So if you open this, you will have m times delta, and then u and divide by L square, and u taking common, this is 1 here, and minus m delta by L square here, and this quantity is here. And remember, this is a small number. So write 1 minus m delta over L square is equal to omega square. Define a new constant omega, which is 1 minus m delta by L square. Since delta is very small, close to 0, this quantity is close to 1. Omega is close to 1. If delta is 0, then it is just 1. And then this equation is d2u d theta square plus, this is omega square and theta, and is equal to mk by L square. This is u. Or d2u d theta square plus omega square u and minus mk by L square is equal to 0. Let us call this quantity omega square u. So let us call this quantity omega square u minus mk over L square as omega square u prime. So what I am defining is u prime is equal to u minus mk over omega square L square. So in that case, d2u d theta square, it's same as d2u prime d theta square. This is just a constant, and this bracket here is just omega square u prime. So my equation becomes d2u prime d theta square and plus this whole bracket, and that whole bracket is omega square u prime and is equal to 0. And this is again your very familiar equation, that simple harmonic motion equation, d2x dt square plus omega square x equal to 0, and you know the solution, x is equal to some a cos omega t, like that. Similarly here you will have u prime is equal to some constant, then cos of omega times theta. There it is omega t, here it is omega theta. So omega theta and omega theta minus theta naught, or theta plus theta naught, like this. So these are the two constants of integrations from here, and by properly choosing theta equal to 0, that means properly choosing the x-axis, you can make this quantity whatever you like, and I will be doing it like a minus a cos omega theta. So that is u prime. And what is u prime? U prime is this. I want to write u. So u is equal to this quantity plus u prime, and this quantity is m k over omega square L square and plus u prime. So it is minus a cos omega theta, and this is 1 by r, remember. This is m k over omega square L square, take this common, so here it is 1, and then minus omega square L square divided by m k here, and this a here, and then cos of omega theta. Okay, this is another constant. A is arbitrary constant, depends on the initial condition, what is the energy and what is angular momentum, etc., etc. So this whole thing is a constant depending on how you have started the motion, and we write it as small e. So this is mk over omega square L square 1 minus e cos omega theta, and this is u. So r will be inverse of this omega square L square by mk, and then in the denominator 1 minus e cos omega theta, right. So you can write this as omega square L square over mk and divided by 1 minus e cos omega theta, or r naught. You can call this whole constant. This is constant omega here that we had defined, and our omega is defined here, and that is a constant, mass delta L square. So this omega square is constant, L square is constant, m is constant, k is constant. This whole quantity is r naught divided by 1 minus e cos omega theta. This is the equation of the path under this slightly perturbed inverse square attractive force. Now how it looks like, and remember omega is very close to 1. Omega is very close to 1. We had defined omega here. If delta is very small, if delta is 0, omega is just 1. So here if delta is 0, what happens? If delta is 0, omega is 1. So it is 1 here, it is 1 here, it is 1 here, and you get back the original equation r naught divided by 1 minus e cos theta. But now omega has a value which is slightly different from 1. So what is the effect on the shape of this path? So let us see what is the maximum separation of this particle from the origin, and that maximum separation will be again r naught divided by 1 minus e, and that is when this quantity is 1. So r is maximum, and that is r naught divided by 1 minus e, and that is when cos omega theta is 1. And what are those values of theta? So omega theta can be, let us say, 0, can start from here, then it can be 2 pi, then it can be 4 pi, then it can be 6 pi, and so on. At these values of theta you have cos omega theta equal to 1, and then r is this. Similarly r minimum you can calculate. R minimum is r naught divided by 1 plus E, and when this cos of omega theta is minus 1, then this is r min, and cos omega theta minus 1 means omega theta should be pi or 3 pi or 5 pi and so on. What happens to theta? Let's start for this equation. Theta is equal to 0. Next, theta is 2 pi by omega. Next, 4 pi by omega. Next, 6 pi by omega. Next, 8 pi by omega. And omega, I've just erased that. Omega is slightly less than 1, right? Omega, you see the expression of that omega square that we have defined. It is slightly less than 1. So this quantity is slightly more than 2 pi. So this quantity is slightly more than 2 pi, and wherever at whatever theta this becomes maximum, once again you go slightly more than 2 pi, you will get this next maximum. It's a kind of ellipse. Remember, it's kind of ellipse. Omega is very close to 1. But then if your ellipse started like this is the maximum distance. Let's say this is the maximum distance of the particle, and then it goes. Normally it should have come back here to become maximum, but now it is becoming maximum here. So this major axis, similarly this minimum is not at pi, theta pi. This minimum is at pi divided by omega, slightly more. So minimum is not here, minimum is here. So this major axis has tilted, and your path will be something of this kind. Here it is turning, so this is that shift. So this is R max, and next R max is coming here. Very exaggerated figure. Once again R max is here, okay, and next time when it comes, and R min is somewhere here, and next time when it comes, the maximum will be somewhere here. So see, this was the major axis, then this is the major axis, and then this is the major axis. So the major axis is turning, so the whole ellipse is turning. That is the precession. So if the inverse square force is slightly disturbed, and that slight disturbance is of 1 by r cube type, then the path will be a precessing ellipse. In fact, it is related to the very famous observation of precession of orbit of Mercury around Sun, which was the first test of general theory of relativity. From Newtonian mechanics, we can do all this analysis. We can find the effect of other planets which are there, which is perturbing that inverse square attractive force due to Sun only. So that precession is explained by this Newtonian theory, but the amount of precession, and is very, very small. It is only, depending on which frame you are talking, it is only a few hundred arc seconds in 1 century, 100 years, and Newtonian mechanics, taking care of other planets and other disturbances, can account of most of it. But some 43 arc second was not explained by this, and that is very well explained by general theory of relativity of Einstein, which is a modification, or which is a totally different theory of gravitation. So we have almost completed the chapter on central force motion. We started with the definition that force on a particle is towards the origin or away from the origin along the radial direction, and depends only on the distance of the particle from the origin. Then we say that it is central force. Of course, we choose our origin in appropriate manner, okay. And then we saw that the motion will be in a plane, and then we talked of several kinds of energy diagrams, and when the motion will be bound, unbound, all those things. This inverse square attractive force, we talked at length about that, because that's very important. All the planetary motions and other things are governed by this kind of law. So all those things we have done. Last piece, because whenever in nature there is a force, the force is exerted not by the origin but by the object, by some object. That object may be placed at the origin, but nobody is holding it there. So if this object at the origin is exerting a force, central force, on my particle, the particle is also exerting force on this bigger object or the object at the origin, and therefore this will not stay there, and hence it's a two body problem. Small m is moving in because of the force by the capital M, but then the capital M will also move because of the force from this small m, and therefore keeping the body, this body at the origin, that is not the case. Of course, I can put the origin on the body even if it moves, but then that becomes non-inertial frame, and all our equations are for inertial frames. But it so happens that this two body problem can be reduced to one body problem, and that one body problem is exactly the same which we had been describing with a fixed center of the force in an inertial frame. Let us see how. So, suppose I have an inertial frame, this is our inertial frame S, and then I have some object here, let us say of mass m1, and another object somewhere, let us say at certain instant, this is at some other position, mass m2, and I call this position vector as r1 and this position vector at r2. These two objects, they are exerting forces on each other, and that force is directed, force on m2 by m1 is directed along this line joining, and so is the case when you consider force by m2 on m1, and the magnitude of this force or these forces is dependent only on this separation. So, if I put my origin here, okay, I am satisfying the conditions of the central force. The force on this m2 is always towards or away from the origin, and the magnitude of the force is dependent only on the separation. So, I am satisfying all those conditions. Only thing is that then if I put the origin here, then my frame becomes non-inertial. Okay. So, this is the situation. So, force on m2 by m1 is f of r and in r cap direction, but now what is r cap direction? Is the unit vector in the direction of r2 vector minus r1 vector. This is that vector, this vector is r2 vector minus r1 vector, this vector here, and the force is in this direction. It can be negative, it can be this way or that way. So, force is in this direction. If it is attractive, it is opposite. If it is repulsive, it is like this. Okay. So, this is that r cap vector, and the magnitude of the force is dependent only on this r. This r is separation between these two particles. So, this r here is r2 minus r1 vector, magnitude of this. So, this is the situation, and opposite force on m1 by m2, Newton's third law, is minus of Fr and r cap. So, how do we discuss motion of m2 and of m1, because it is a two body problem, both are moving, both are accelerating, and therefore to consider that motion we change variables, because we are interested in motion of m2 as seen from m1. So, we change our variables. We define r as the center of mass, m1 r1 plus m2 r2 divided by m1 plus m2, and the other one is this r, we define this r as r2 minus r1, as if my origin is here and I am writing the position vector of this with respect to this origin. So, this is r. So, we define these two. The motion of or change, rate of change of this r and the corresponding accelerations are trivial, because if it is an isolated system, the center of mass either remains at rest or moves with constant velocity. So, from the initial conditions I know what is the situation, and so where the center of mass will be at time t, simple. So, what we are really concerned with, this particular thing. Now, let us see if this is r, what is r double dot? What is r double dot? R double dot is, that means the second time derivative acceleration. R double dot will be r2 double dot and then minus r1 double dot. And what is R2 double dot? R2 double dot, this is R2 in an inertial frame, this is R2, and double dot the acceleration of this particle as seen from the inertial frame, that will be force divided by mass. So m times R2, m2 times R2 double dot is equal to the force and yeah, so mass I have written here. So mass m2 and into acceleration of this second particle in an inertial frame of reference, because R1 and R2 are measured from this inertial frame of reference, should be equal to force on this, and force on this is only because of this m1, and that is Fr r cap. So this is Fr r cap. So R2 double dot is Fr r cap divided by m2, and similarly m1 r1 double dot, acceleration of the first particle as seen from the inertial frame of reference and multiplied by mass should be Fr r cap with a minus sign. Newton's third law. Force on m2 because of m1 and force on m1 because of m2, they are equal in magnitude and opposite in direction. Our r cap vector is already defined. This is the unit vector in the direction of r2 minus r1. So on m2 it is r cap, and on m1 it is minus r cap. Of course, this Fr can be positive or negative, that will depend on whether it is attractive or it is repulsive. Okay, so r1 double dot is equal to Fr r cap minus sign and divided by m1. Put it here. What do you get? You get r vector double dot is equal to r2 double dot is Fr r cap divided by m2, and then minus, and then you have r1 double dot which is here, so another minus, and Fr r cap divided by m1, right? Now this is equal to 1 by m2 plus 1 by m1 times Fr r cap. This is m1 m2 here, m1 plus m2 here, and then Fr here and r cap here. So you can take this on the left hand side, write this as some number mu, write this as mu, and you have, or m, let us write it m. Let us write, we have not used m as such, we have used m1, we have used m2, so let us write this as 1 by m. Okay, let us write this as 1 by m. Dimensions, here it is m1 plus m2, here it is m1 into m2, so it is 1 divided by mass. So let us write this quantity as 1 by m and take this m on the left hand side. M times r double dot, m times r double dot is equal to Fr r cap, where m is equal to m1 m2 divided by m1 plus m2. And what is this equation? This is the equation that we have solved in the previous lectures. You have an inertial frame, this inertial frame, and here is the origin, and just one single particle here of mass m, and somehow this origin is exerting force on that m, and that force is dependent only on this distance from the origin, and it is in the radial direction. It is Fr r cap. This is what we had done. What will be equation of this particle in this inertial frame of reference? That will be mass into its position double dot, mass into acceleration is equal to Fr r cap. So if I know how to solve this equation, I know how to get the motion of m2 as seen from m1. So we fix up our coordinate system on m1, and then wherever this m1 goes, my coordinate system goes. We are not rotating this axis system, but the origin is shifting from here to here, here to here. As m1 moves in influence of the force from m2, this origin keeps shifting. So it is an accelerated frame, but we don't have to go for the techniques of non-inertial frames. Our next chapter will be on non-inertial frames, and I'll be discussing what are those techniques. But we don't have to go into those techniques. We can still use our techniques of inertial frame of reference. Consider a particle m, just one single particle, and it is acted upon by a force Fr r cap, which depends only on the separation of the particle from the origin, somehow we have fixed this object which is exerting force at the origin of this inertial frame of reference, okay, and then solve what will happen to this particle, and that will be the motion of this particle in this non-inertial frame. The only thing I have to do is, in place of its mass m2, I have to use another mass m, which is given by this equation, which depends on both the particles, the one which is exerting the force and one which is experiencing the force, okay. So this is given the name reduced mass of the system of two particles of the system. It's reduced mass of the system. So if you want to get the motion of m2 with respect to m1, use this, and of course m1 m2 you can interchange. You can get the motion of m1 as seen from the frame which is fixed at m2, that also you can do, and similar thing with a negative sign. So this is how the whatever we had done is very practical. And if suppose m1 is very large, suppose this m1 is very large as compared to m2, what happens here? If m1 is very large as compared to m2, in that case here m1 plus m2, you can neglect this m2, okay. Of course you cannot neglect it here. You cannot say that, okay, let's say m2 is close to 0 and therefore we neglect it. You cannot do it here, but here you can do m1 plus m2. So if you neglect this m1 cancels out, and then this m is almost same as m2. So if one of the particles is very heavy as compared to the second one, then you can still use the same equations, and you can use the mass of this particle as such, m2. This reduced mass is almost same as m2. So in the sun planet system, for example, sun is very heavy as compared to earth. So if you are not doing very sophisticated calculations like that precision of perihelion of Mercury and so on and so forth, for usual kind of astronomy, you can treat the sun as an inertial frame of reference, not being influenced by the presence of earth, or proton electron system. If you are doing Bohr model, you can do all those kind of things. But even if they are not too different in the masses, even if there are comparable masses, even then we can use this reduced mass and use all the equations that we had developed for this particle motion under a central force. So that finishes our chapter on central force, and now I will be going for next chapter, which is non-inertial frames. So I had already talked about inertial and non-inertial frames. The Newton's first law is kind of a definition of an inertial and non-inertial frame. If F is 0, that implies that the acceleration of the particle is 0, and if acceleration is 0, that implies that force is 0. So this is cryptic statement of Newton's first law, and if this law is followed in some frame, that frame is called inertial frame of reference. Right? So all those things we know very well, and if it is not, then it is non-inertial frames. So in non-inertial frames, the second law is also not valid. The second law, Newton's second law, is not valid. F, resultant force F on the particle, is not equal to mass of the particle times acceleration of the particle in such a frame. There are frames, we know there are frames in which this doesn't, it is not valid, and if it is not valid in those frames, this is also not valid. And then we can say that F and minus ma is not 0, is something else. What is that something else? That something else is written as something. So let me write it Fp, okay, or minus Fp. So mass of particle into acceleration of the particle is equal to F and plus Fp. If it is an inertial frame, mass into acceleration is force, but if it is not an inertial frame, it is a non-inertial frame, then mass into acceleration is not F, and what is left is written as Fp, and that we called pseudo force. Why do we call it pseudo force? Because if you bring it here, it's not there. Okay, this is the resultant force. This is the resultant force. All the forces which are acting on the particle are included in this. There is nothing left. When we say F equal to ma, when we write Newton's second law, F equal to ma, this F includes all the forces which are acting on the particle. So it contains all those forces, it is resultant force. Still it is not equal to m times a, and that is why we have to add something else to make it equal. And why are we so interested in making it equal? This is because we have learned all the techniques of how to solve this F equal to ma. Okay, we have done hard work to understand that in a given situation how do I apply this F equal to ma, and from there how do I get the path of the particle, position of the particle, velocity of the particle, acceleration of the particle at any given time. We have learned all those techniques that are governed by this equation, and we do not want to lose that advantage. So we bring in from our side some extra terms, make the right hand side equal to mass times acceleration, and then use all these techniques of inertial frames of reference, and we can get motion of the particle in that non-inertial frame. So this is how the pseudo forces are operating. Now acceleration of the frame, you have two broad kinds of varieties, two broad kinds of non-inertiality. So one is when you have translational acceleration of the frame with respect to some inertial frame. Okay, so we assume that okay, we know at least one inertial frame. Our laboratory, our room, our earth, our roads, they provide us a reasonably good inertial frame of reference. So I will be talking in this course the non-inertiality of earth because of its rotation, but if I am driving, if I am running, if I am swimming, if air is blowing, many of the things can be reasonably well understood, calculated, predicted using earth as an inertial frame of reference. So anyway, suppose we do have an inertial frame of reference and then there is some non-inertial frame, that non-inertial frame will be accelerated with respect to this inertial frame, because any frame which is moving with uniform velocity with respect to an inertial frame is also an inertial frame. So if it is non-inertial, it has to have an acceleration with respect to some inertial frame. Translational acceleration, that means if this is the inertial frame, let us say this is the inertial frame, and then I have yet another frame, it is translating with respect to this. That means the origin is here, and if it is moving, all the particles fixed in this frame, axis, everything, anything which is fixed in the frame has same velocity at that instant. If this is having this velocity, 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 right? If the velocity is upward, then everything is going upward. So axes are not rotating, they are only translating. So that we say translational acceleration. So first let us see, if my non-inertial frame is translating with respect to the inertial frame, and then there is an acceleration, because now I can talk of acceleration of the frame. All the particles of the frame, all the points of the frame which are fixed in that frame, they will be having the same velocity at any given instant, and therefore the same acceleration at any given instant, and therefore I can talk of acceleration of the frame as such. So in that case, what kind of pseudo forces we need? So I will show you a small video clip. It is taken from my course on special theory of relativity, and you see the video. I will be describing it here. So let us see what happens if you have a non-inertial frame which has translational acceleration. So I am trying to show non-inertial frame which is on this box, and on the lid itself I have drawn x-axis, y-axis, and z-axis is upwards, and in this box this is x-axis, y-axis, and z-axis upward, and then in this box you can see a ball hanging in water. So the thread is fixed at the lid. So at this time the ball is at rest and x, y, z, nothing is changing. What I will do, I will be giving this box acceleration towards left, my left, and you have to see what happens to this ball, in which direction this ball moves with respect to these axes, whether it goes to the right or to the left. Here it is. You have seen, I took the box towards left, but the ball moved towards right as seen from this origin, this xy axis goes towards the right wall. So what has exerted force on the ball in the positive x direction? No one. We had taken this box towards left, but the ball is going towards right. So this is a non-inertial frame, no one to exert force on the positive x direction. Water can exert a force in horizontal, but that will be in the negative x direction. There is no one to exert force on the x direction, but the ball is going in the x direction. But we want to use Newton's laws. If the ball has gone towards right, there has to be a force towards left. So we accelerate the ball towards left, and we say that that time there is a force on the ball towards right, and that assumed force which is not there in the box frame, box goes towards left, there is an assumed force towards right, and that force is the pseudo force. Only to use Newton's law in the non-inertial frame, we have to take some extra force which is not there. If this box is going towards left, then we have to take the force towards right, opposite to the acceleration of the frame with respect to inertial frame. That is our pseudo force. So you had seen that I had accelerated my frame, I had given a translational acceleration in the negative x direction, and it created an acceleration of the ball as seen from that translating frame in positive x direction. So we will do more algebra on it in the next lecture. So in the previous lecture I showed you an activity where I took a plastic container with water in it, and then there was a kind of pendulum which was hanging from here, a ball here, and water was filled in this. Okay. And then we accelerated this box in this direction with some acceleration. In fact, this was of course varying acceleration. We first accelerated and then we decelerated and then brought it to rest. But what we will discuss is only that initial part of the motion in which it has an acceleration in this direction. And then we had put some our x-axis and y-axis on the box itself, and from this frame what happens, that was the focus point. And what we saw is, if I call this lap frame as S0 and this box frame as S, then what we saw is in S the ball starts moving. It was initially here, and the box, when it started moving, this was at rest, this was at rest, so it starts moving in positive x direction. Okay, it starts moving, that means it has an acceleration in positive x direction. All this is description from this S frame. What happens in S prime frame, in S0 frame? In S0, the box is going, the whole box is going left. So after a very short time, also if you see, your box will be displaced in this direction and it will be like this. The ball has gone towards positive x-axis in this frame, and the thread is making some vertical angle here, and it becomes like this. So this is the situation. So our ball has in fact gone towards left. Okay, it was here and now it is here. So as seen from the S frame, the ball was at rest to start with, and then it started moving towards left. So in S0, the ball starts moving in negative x direction, that is towards left. Okay, in this frame also we can put up x this way, in this frame also we can put up this way. So the ball starts moving in negative x direction, and therefore its acceleration is in negative x direction. So first let us talk why in the inertial frame, why in the lab frame the ball is having acceleration towards left. So what are the forces in S0? We are using the frame S0. Forces, of course forces are same in this frame or that frame, forces are same, the accelerations are different. Forces, what are the forces? mg downward, then this tension upward. I am looking at the forces on this ball. So mg, mass of this is m, mg downward, tension upward, and then buoyancy in vertical direction, and that is upward. Okay, as you know, Archimedes principle, if this ball is dipped into this water, then this water will exert an upward force which is called buoyancy, and it is in vertical direction. But we are missing something, and what is that? If this is the case, if these are the only forces, then there cannot be an acceleration in x direction, positive or negative, because all these are vertical forces and I am using inertial frame of reference. So there has to be a real force which should be towards left in the negative x direction, because the acceleration of the particle, acceleration of the ball is in negative x direction. From where that is coming? That is coming again from the water only, because there is nothing else which can exert force on this. It is in contact with water, it is in contact with this thread, and of course the gravity. So that means the water is also exerting a horizontal buoyancy force, and that is in the left direction, that is in the negative x direction. And that means the pressure here, say P2, and pressure here P1 is different. P2 must be greater than P1, so that the force from this side is more and force from this side is less, and you have a resultant force towards left. Because inertial frame there is absolutely no problem, we know that net force and net acceleration are in the same direction. So acceleration we have seen that it is towards left, and therefore the net force should be towards left. These forces are all vertical, so you need a horizontal force in the left direction, and that will come from this pressure difference. The buoyancy comes from the pressure difference here, top and bottom, or up and down. And here the pressure is also different in the horizontal direction. In fact, that pressure difference is creating acceleration not only in the ball, but in the entire this mass of water, that is also accelerated towards left. So any part of water you take, the pressure here should be more, the pressure here should be less when it is accelerating towards left. So these are the real forces, and because of the resultant force which is in the left direction, you have an acceleration in the left direction. Now come to this frame S. Come to this frame S. In S what happens? All the real forces are same. All the real forces are same. So the real forces, all the real forces, in fact all the forces are always real. The resultant is this horizontal buoyancy force, like this. This is the resultant force. But the acceleration is in positive x direction. Okay, acceleration is in positive x direction. So how do we account for that? We say that fine, it's perfectly all right, because you are using non-inertial frame. So resultant force is towards left and acceleration is towards right. Newton's law is not valid. What is the problem? Absolutely no problem. If you are using non-inertial frame, you do not expect that the resultant force will be mass times acceleration. Force is in left direction, acceleration is in right direction. Possible. Newton's law is not valid. So if you write mass times acceleration, this is in positive x direction. If you write forces, these are the forces, the resultant force is this, which is BH, that is in left direction. And these are not equal. But you want to make it equal by adding something else, and that something else is your pseudo force. You call it pseudo force. You want to make it this equation look like Newton's second law, so that you can use all the techniques of solving Newton's law in inertial frames that you have learned in so many years. So if you do that, if this is in left direction and this plus this is in right direction towards right, positive x direction, this is negative x direction. So this Fp must be in positive x direction. and its magnitude should be more than the magnitude of this resultant real force. Only then the sum will be in positive x direction. So this is a general rule. If the frame has translational acceleration and you are using that frame and you want to use Newton's second law together with the real forces, you have to apply a pseudo force which is in direction opposite to the acceleration of the frame. What particle is doing, that will be decided later, but the moment I know that my frame is accelerating in this direction, I know that I have to use a pseudo force which is in opposite direction. How much is the magnitude? How much should be the magnitude? That also we can work out. We can make some drawing. Say this is our lap frame or inertial frame. This is inertial frame, and then I have some other frame, call it S frame, and here's the origin, and then I have a particle. At certain instant, this is the picture. This particle will have some velocity which will be different as seen from here, as seen from here. This particle will have some acceleration which will be different as seen from here, as seen from here. This is picture at a certain instant. Now at this instant, if I join this P to this origin of S naught, this is a position vector. This is position vector of the particle as seen in this S naught, and then I can also join this particle to the origin of this S frame, and this will be the position vector. I can call it position vector of the particle in S frame, and then I can join the two origins, and this position vector I can call position vector of this S, origin of S, with respect to this frame S naught. Okay. So if this be the case, then from this triangle you can immediately write that R of Ps naught is equal to this vector, is equal to R S naught, this vector plus this vector, R of P, particle in frame S. Now double differentiate and get the acceleration. Differentiate it once with respect to time, you get the velocities, and then do one more differentiation and you get acceleration. So acceleration of particle in S naught is equal to acceleration of S, frame S, with respect to frame S naught, and then plus acceleration of the particle in frame S. I am interested in this quantity. I want to use non-inertial frame and get the acceleration of the particle. So let us separate out this. APS is equal to APS naught, APS naught, and minus ASS naught. So minus ASS naught. Okay, multiply by the mass of the particle. So m times APS is equal to m times APS naught and minus m times ASS naught. This is the quantity which I am interested in. But what is this? Mass of the particle multiplied by acceleration of the particle as measured in inertial frame of reference. This is acceleration of particle P in frame S naught, which is inertial, and therefore this has to be equal to net resultant force. F equal to ma can be applied in S naught. It's an inertial frame of reference. So this is equal to the net resultant force, and then you have minus MASS naught. If you are using frame S and trying to write mass times acceleration, that is not equal to the net resultant force, because Newton's law is not operating there, and therefore this extra term is coming, and that is what you call FP. This is what you call pseudo force. So the pseudo force in this case is minus MASS naught. So we have already seen the direction of the pseudo force. It is opposite to the acceleration of the non-inertial frame that you are using, and then here is the magnitude. To get the magnitude of that pseudo force, you multiply mass of the particle and acceleration of the frame s with respect to frame s naught. So, acceleration of the non-inertial frame with respect to the inertial frame, that you have to write multiply by the mass of the particle, opposite direction, inverted direction, this minus is here, and you get the pseudo force. Now, why I am insisting on translational acceleration? This is because this vector that I had drawn here is the origin of this frame. This is only the origin of this frame. If it is not rotating and only translating, then any other point of this frame, fixed in this frame, will have the same acceleration as that of the origin. Okay. So, if I have this frame here and is translating in some direction, and I have a point which is fixed here, So, in that case, this acceleration of this particle, this point, is same as the acceleration of this point, because this vector is not changing. Its magnitude is fixed, its direction is fixed. But if this frame is also rotating, then even if this point is fixed in the frame, as seen from the inertial frame, the particle is or the point is also rotating, and therefore this vector will also give you some acceleration. So, you can't talk of acceleration of this frame, because point by point the accelerations are different. Now, what if the frame is rotating? So, let us go for another video clip again from the same course, Special Theory of Relativity, and first we see the path or the forces qualitatively in the video clip, and then we will discuss it here. So, here is a disk which can be rotated. We have already drawn x axis here and y axis here, and z axis is upward, and this whole disk can be rotated, and this x y z will also rotate together with the disk. So, this is our rotating frame of reference. We will measure everything with reference to these axes, and then we will see what happens. So, what I am doing now, this is the wheat flour, atta, and I will sprinkle this wheat flour on this disk. So, I am doing that. All right. So, I am sprinkling this wheat flour on the x axis, on the y axis, on this disk. You can still make out the x axis and y axis in those dark black lines. Okay. Now, I have this small object, ring type object, and this black small ring type object I will be keeping on the x axis close to the origin. So, I have kept this ring here, and then I will rotate this disk, okay, this way clockwise as seen from the top, and you see that ring. What is the path of the ring? What is the motion of the ring? How does it go in this frame? So, I am rotating, and okay. So, now the ring has gone to the periphery of that disk, but interestingly it has left its path. You can see this path. We started at x axis close to the origin, and now it is going in this path. The wheat flour has been displaced by the ring, and it is showing you the path, right. So, what you see is the distance from the origin. Originally we placed it close to the origin, and it is increasing. The distance from the origin is increasing, that r is increasing. Okay. So, something is if I use that terminology of Newton's second law, something is taking the ring away from the z axis, but it is also turning. It is not only going away, it is also turning. See the path carefully on this disk, it is very much visible here, and you can see that as it goes away, it is also turning. So, velocity is perpendicular to that outward radial direction. Okay, it is deflecting, tries to go in the radial direction, but then there is also something which is taking it, which is deflecting it from the path. It is not only the radial motion, you also have an acceleration in that perpendicular to the velocity direction. So, it is deflecting continuously towards left, and that is how this path is showing up. So, in the rotating frame of reference, that means my x-axis, y-axis, z-axis are rotating. We will do that rotational dynamics later, axis of rotation and all those things, but you know a little bit of it. So, in this particular example, this frame was rotating about the z-axis. This frame was rotating about the z-axis. This is how the whole frame was rotating, and in that frame we placed a particle somewhere here. We placed a particle somewhere here. It was rotating anti-clockwise, right? And then the particle that was increasing, this distance was increasing, but at the same time it was getting deflected. Every time it was getting deflected, every time it was getting deflected, every time it was like this. Okay. So, what are the forces which are taking it in this direction? If you see the real forces, you have mg, you have normal force, and you have friction. And friction is always opposite to the velocity. As such, friction does not change the direction of the velocity. The friction will be opposite to the velocity. It will keep that speed under control. It will decrease the speed, and it will not increase the speed in general. With respect to the disk, this frictional force will try to reduce the relative velocity, the slipping off of that object on the disk. It will not start the motion on the disk. All right. So, you must have forces, number one, which is taking it away from the z-axis, the distance from the z-axis, which was initially very small. Initially the ring was somewhere here, initially very small, but then this radial distance was going. So, if I use Newton's law of terminology, if I say that okay, I see there is an acceleration, there is acceleration outward, and also I see an acceleration which is perpendicular to the velocity, velocity dependent. The acceleration is velocity dependent. Okay. Then we will say okay, that means I have to use pseudo forces, two pseudo forces at least, one in outward direction and another which is perpendicular to velocity, and it turns out that yes, that is the case. So, we will talk more on these two kinds of pseudo forces coming in if you are using rotating frame of reference. So, you saw this video clip where I had a disk which was rotating, and then a small particle or small object, ring type object, was placed on that disk. We had x-axis, y-axis drawn, and then we saw what is the path of the particle with respect to the disk, because the path was traced out on the disk, so we could very easily see it leisurely. So, this was the disk, and then the disk was rotating, but then we will work from this disk frame. Okay. So, I have an x-axis here, I have a y-axis here fixed in the disk, and we are talking from the disk frame. For discussing the path of that object. The disk is rotating. When I say that disk is rotating about the z-axis, I am using the lap frame. But then when I am saying this is the path of the object, I am using the disk frame. So, that which frame I am using when I am telling some statement or some sentence, that is very, very important. So, from the disk frame, when I am talking in the disk frame, from the disk frame, x-axis and y-axis do not rotate, they are fixed. They are fixed. In this frame they are fixed. So, I do not have to turn the axis like that. Now, I put the particle here, that small black ring type object, I put it here, and then I gave it a rotation. When I say I gave it a rotation, I am talking from the lap frame. Okay. But the path of the particle is still seen in this disk frame. So, in the disk frame, this was going like this. You saw it. It went like this, and then it reached the periphery. So if I look from the z axis, which is the axis of rotation of the disc from the lap frame, then the distance from this z axis is increasing. Initially I had kept this much of distance, but as time passes the distance becomes larger, 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 larger. So something is, if I am using the language of Newton's second law, though I am not entitled to do that, but I know how to get the license to do that. I will be using proper pseudo forces, and then I can always use the language of inertial frames. So we are actually looking for those pseudo forces which will allow me to use the language of Newton's first law, second law, third law, and therefore if I am using that, there is some force which is pushing it away from the z axis. The distance from the z axis is increasing. It's not always to remember that if distance is increasing, then you have a force in the radial direction, you can have radial acceleration 0, but at least in this case it seems that yes. So you have to use pseudo forces, and then one force seems to be away from the axis, away from the z axis, which is the axis of rotation of this disc frame with respect to the lap. So this is one. And then it is not only going away from the z axis, it is also turning. So when it is here, it turns this way, when it is here, it turns this way, when it is here, it turns this way, and the direction of velocity is turned, is rotated only when you have a force, component of force perpendicular to the velocity. If you don't have that component, speed will increase or decrease. So if you have a component which is perpendicular to the velocity, then that component will turn the path, turn the direction of the velocity, and here it is turning. So there should be a force which is perpendicular to the velocity. So this is one, and then the other is a pseudo force which is perpendicular to the velocity. At least a component should be there, perpendicular to the velocity. So in the rotating frame you do have two pseudo forces, or you have to assume two pseudo forces if you want to use Newton's laws. Then together with the real forces you have to use at least these two forces. Now this one is called centrifugal. It's an example of, it's not definition, it is an example of what we call centrifugal force, and this is an example of what we call Coriolis force. Okay, so this was some kind of a feel. I tried to give you a feel that in a rotating frame of reference you need two kinds of pseudo forces. Now let me take one more example. Same story. Let's use the same figure here. Let us use the same figure. There is a disc, and there is an x-axis, there is y-axis, and in the lap frame the disc is rotating about the z-axis. So it is rotating about the z-axis with some angular velocity omega. And we will be using this axis, this y-axis, x-axis and z-axis, which are fixed in the disc frame, to observe the motion of a particle or an object which is placed at rest in the lap frame. Okay, so suppose I have a particle somewhere here, and this particle or this object is at rest. Where do I write? Let me write it here. Okay. This is the particle P at rest. P is at rest in the lap frame, and I am looking at this particle from the disc frame, and the disc frame is rotating with angular velocity omega about the z axis in the lap frame. So that is the situation. What is the path of the particle? Is the particle at rest? Is the x coordinate, y coordinate, z coordinate, or are constant? So if this is the particle now and it has some x component, this is x coordinate, and then it has some y coordinate and z coordinate is say 0 at this moment. Now in the lap frame the disc rotates and the x axis becomes like this. So the particle has come to on the x axis. Particle was not on the x axis to start with, and now the particle is on the x axis. So the particle is not at rest. Particle is moving. So that means the particle is coming down. It is from the disc frame. I will say that from the disc frame my frame is not rotating. In the disc frame x axis is fixed, y axis is fixed, and therefore the particle is here, and then the particle comes here. So if you work out, it is going in a circle. if in the lap frame, if the disk is rotating this way, this particle is going in a circular path, like this. If it is going in a circular path, it is in acceleration. Okay. So in the disk frame, if I want to use Newton's second law, there is an acceleration, so I have to assume some pseudo forces. The real forces is 0. F total, F net. Net means the real force, sum of all real forces. This particle, this object may be placed on a table. So the gravity, mg, the normal force, everything add to 0. Sum of all real forces is 0. But then I have to supply pseudo forces. So that you have this acceleration using Newton's second law. All right. So the centrifugal force will be there, and what will be that centrifugal force? That will be that you can obtain from other examples also, and you know it very well, that the centrifugal force, I am using disk frame, so there is a centrifugal force, and that centrifugal force will be away from the axis, and its value will be m times omega square times distance from the axis. All right, distance from the axis r. What is distance from the axis? Here is the axis. This one, this, let's call it capital X, and let's call this radius as r. This will not be needed. So centrifugal force will be this m into omega square into that capital X. Which direction? Outward. But the acceleration is inward. This particle is going in a circle, and when the particle goes in a circle, the acceleration is inward. And how much is that acceleration? If it is going in a circle of this radius x, if the particle is going in a circle with this radius x, and the angular velocity of this particle is also omega, the magnitude, because there is the same time period after which in the lab frame the x-axis will return at the same place, and the particle will have the same coordinate. So the angular velocities of the disk in the lab and of the particle in the disk, they are going to be equal. Okay, so the centrifugal force is this much outward, but the acceleration is omega square x inward. Okay, in terms of speed, it will be omega square x. So the centrifugal force is outward, but the acceleration is inward. That means I have yet another force, yet another pseudo force, and that is inward, and that is more than this, and more than this, and that gives me this acceleration. So I have Coriolis force. I must have Coriolis force. I must have another pseudo force, and this depends on the velocity, and that should be equal to 2 times m omega square x, and that should be inward. And then this is the pseudo force number 1, and this is pseudo force number 2. One is outward, one is inward. Inward is double of the outward, so this resultant of these two will be inward, and the magnitude will be m omega square x, and then yes, mass times acceleration will be equal to the total force. Total means the real and the pseudo. So these are some examples where you can work out what this pseudo force is, what the Coriolis force is. Now, but remember, they may look very similar. Apart from the factor 2 and the direction, they look very similar, m omega square x. But this one is like m omega times v, right? Omega into x is v. Okay. So I would like to write it as 2 m omega v, because it is dependent on the velocity. If the velocity is not there, Coriolis force is not there. If you consider that Bohr's model, you have a plus q charge here and minus q charge here going in a circle with some uniform speed. So if I put up a frame which is rotating at that same angular velocity as this charge is not moving in that rotating frame. If it is not rotating this frame, then the actual force, real force is you know, E minus q square, or q square by 4 pi epsilon naught, and this radius square inward. Force of attraction. Okay, inward. This much is the force, but this particle is at rest. this particle is not going in a circle. I am talking from that rotating frame. My frame is rotating, and from that frame I am analyzing the motion of this particle. And in that frame, in this particular case, the particle is not moving. It is at rest. And therefore, what pseudo force I require? The total force should be 0. The particle is at rest. So in the disk frame or in the rotating frame, I set up a frame which is rotating. I set up a frame, this is x-axis, this is y-axis, and then this whole thing is rotating in the lab. And when I go to that frame, I find that my particle has same x coordinate, same y coordinate, same z coordinate all the time. It is at rest, and therefore, if I want to use Newton's laws, the total force should be 0. But I know that there is an attraction that cannot be done away, and therefore, the pseudo force that I have to use, is just q square by 4 pi epsilon naught r square outward, and that is a centrifugal force. That is centrifugal. I don't need Coriolis force. Coriolis force depends on the velocity. If there is no velocity of the particle in my rotating frame, I don't need Coriolis force. So here I will be writing this as, I will not write this as omega times v. Centrifugal force depends on the position, and the Coriolis force depends on the speed, on the velocity, direction and magnitude of the velocity. So this difference one should take care. Let me now derive a formal expression for centrifugal force and Coriolis force if a particle is in motion with respect to the rotating frame. So let us have a rotating frame. So let me draw axis system, some axis system which is rotating in the lab, and the angular velocity is omega. Let's take this z axis as the axis of rotation, okay, and then x axis and y axis are rotating. And in this frame, in this rotating frame, there is a point A or point P which is fixed in this frame. There is a point P which is fixed in this frame, and I am looking at this vector OP. It can be a particle, and this OP can be the position vector of the particle or any vector, this vector OP. I am talking of the vector OP. Point P is fixed in the rotating frame. All right. Therefore, from the rotating frame, so OP is constant, fixed, not changing in the rotating frame. But OP is changing. OP is changing in the lab frame, which is supposed to be inertial in the lab frame. I am interested in at what rate this OP is changing in the lab frame. Okay, so what I do? This particle P, since the entire frame is rotating about z axis, and the P point is fixed in that frame, so P is also rotating about the z axis, and it is going in a circular path. It is going in a circular path. Okay, so it is going in this circular path with angular velocity omega, and therefore OP is here. After some time OP will be here. I am now talking from the lab frame. I need ddt of OP in the lab frame. After some time the frame will be here, this OP will be here, P point will be here, and so on. So it is rotating. So if I just look for this point P, so let me draw this diagram again. This is the path of that point P, of that particle P. So let's say particle P is here at some instant, and this is the z axis, and this is OP vector, this is OP vector, this is OP vector. Let me call this A. Let's name it OP vector. I will call it A vector. So this is A vector at this time. After dt time, what will happen? After dt time, this particle will reach here, and this angle will be omega t. This angle will be omega delta t. After delta t time, the particle will be here. So this was vector A at time t, and this is the vector A at time t plus dt. And this is a change. This is that change. This is that change. This you can say this is delta A, which is A at t plus dt and minus A at t. This is that vector. and divide by time, you will get this ddt of OP in the lap frame. Okay. Now, and this is our origin is here, remember our origin is here. So, this is not actually the A vector, this is the A vector OP. This is that A vector, and this is that A at time t plus dt. This is it. But nevertheless, things will not change much. Okay, this is your A at t plus dt, and this is A at t. But still this remains this much. So ddt of OP is same as, let me call this point C, the center of the circle. This is ddt of OC and plus CP. This vector OP can always be written as OC plus CP, and OC is fixed. OC does not change with time. This particle goes in a circle, and this is the center of the circle, and that will remain always there as time passes. So this is essentially ddt of CP. Okay, so that's why this original diagram is also valid. Now, how much is this? What do I write for this? This is CP. This is CP, and the ddt of is this one. And how much is this? The magnitude. This magnitude will be this length here, CP, which is fixed, and then into omega into delta t. Okay, so this is the length of this, and the direction of this delta A vector is along the tangent, along the velocity. Okay, so how much is this now? ddt of that, if you do this delta A by delta t, that is, or it's already written there, that is equal to Cp into omega. This is the magnitude, and along the tangent. And how much is Cp? Cp is this OP, and then if this angle is some theta which is fixed, once again this will be OP times sine theta, and then omega, and the direction is along the tangent. And you work out that this is nothing but cross product of O vector, this omega vector, and this OP vector. See the magnitude. Magnitude of this vector is here. Magnitude of this vector is here. Sine of angle between these two is here. Omega, this is omega vector, and you know what is omega vector? When I am talking omega vector, if the axis of rotation is there, that is the direction of omega vector, and if you are looking from top, then it should go anti-clockwise. So that is the direction of omega vector. So it is omega cross OP, and therefore what you can write is ddt of vector A in lap is equal to omega cross A. This is an important relation. We will take it from here. Now this is an important relation, and you can go through this derivation again and convince yourself that the direction of omega cross OP is also along that tangent. How? This omega cross OP, once again you write this OP as OC plus CP, and OC is in the same direction as omega, so this cross product is 0, and this will be omega cross CP. Now it is easy to see the direction. This is a circle, and then you have omega is perpendicular to the circle, and this CP is radius. So if you have a circle, this is C here, this is P here, CP, and omega is perpendicular to the disk coming out, and since it is going this way, so omega is in the positive direction of omega is coming out of the board. Now you see what is omega cross CP. So this is omega, and this is CP, and omega cross CP, you can work out what is omega cross CP. It has to be perpendicular to omega, therefore it should be in this plane. It is perpendicular to the CP, therefore in this plane it is perpendicular to the CP. And then you do this omega cross CP, and you see that it is in the direction of velocity. So you can very easily verify that this whole thing can be written as omega cross OP, and therefore ddt of this vector A in the lap frame is equal to omega cross A. You don't have to actually differentiate. We will be using this relation very extensively in our rigid body dynamics. You don't have to actually differentiate, you just take the cross product with this angular velocity vector, and you get the differentiation itself, provided this A vector is fixed in the rotating frame. This whole derivation is based on that this A vector is fixed in the rotating frame. In the rotating frame it is not changing, then this is true. But if the particle also moves in the rotating frame, this A vector is not a constant vector, this A vector is changing with time even in the rotating frame, then what will happen? You will have to add that term, that's all. ddt of A vector in the lap frame is equal to omega cross A if A is constant in the lap frame, in the rotating frame. If not, the only thing I have to do is I have to add one more term, dA dt is equal to, this is in the lap frame, this is equal to dA dt in the rotating frame, plus omega cross A. So if A is fixed in the rotating frame, you don't have any dA dt in the rotating frame, then it is just omega cross A. So because of the frame rotation, you are getting this omega cross A, and because of the particle moving in the, or the vector changing in this rotating frame, you are getting this term. So this is the relation which is general, more general than this. This is true when A is fixed in the rotating frame, and this is true if this A vector changes in the rotating frame. So we will start from here. So we related the time derivative of a vector in an inertial frame of reference and a frame which is rotating with respect to this inertial frame. So what we had, some inertial frame of reference, origin, call it S0, and then there is some other frame which rotates with respect to this with an angular velocity omega, and angular velocity we wrote as a vector, and the meaning is that this vector is along the axis of rotation of the frame, and then the direction on that axis, whether this way or that way, depends on how you are looking. So if you are looking and you find that the frame is rotating anti-clockwise, then the omega is towards you, and you find that the frame is rotating clockwise, then omega vector is away from you. So that is how we define this omega vector, very important. In fact, we will be using it extensively now onwards in this chapter, and then in rotational dynamics also. So this has to be understood. So about this line, the frame is rotating, the other frame is rotating, which we are calling S, and this is the frame which we will be using. So this is very important, because we are using this particular frame which is S, and this S is rotating as seen from this inertial frame about this line with angular velocity omega. So this is the situation. And then we said that if a vector is fixed in this frame, suppose I take a point here and say that okay, this is the vector, suppose this is the vector. So wherever this x axis goes, as x axis of this S goes, this vector will go together with it. So that means it is fixed in S frame of reference. Or there is some other point you can take and say that okay, this is a vector, and not necessarily position vector alone, any vector which is fixed in this frame, so that one can consider. And if you call this vector A, then we saw that in S0 frame, this whole frame is rotating. So this vector A, which is fixed in this S, is also rotating, and that means as a function of time this vector is changing in S0. It is not changing in S, it is fixed in S, but it is changing as a function of time in S0, and therefore we said that ddt of A, we have two things, one is in frame S, another thing is in frame S0. dA dt is 0 in S frame, it does not change with time, it is fixed in S frame, and it is rotating about this omega as seen from S0, it is rotating about this line, and therefore S0, this is not 0, and what this is, that we found that it is nothing but omega vector cross A vector. And if it is not 0 here, if this A vector is also changing in S, then the expression for this is this plus dA dt in S. So, if this is 0, this drops out and you just have this, and if it is not 0, then you have to take care of this also. This is because of the rotation of this frame, and this is because A vector is changing in that rotating frame also. So, when added together, it gives you the time derivative of A in that inertial frame of reference. So, this is what we had done, and now we will apply this equation for position vector of a particle. So, suppose this is now a point P, and here is a particle of mass m, and this may be moving in S frame of reference also, this rotating frame of reference also. So, this is a position vector, and to this position vector let us apply this. So, what do we get? dr dt as seen in the S frame, S naught frame, as seen in the S naught frame is equal to dA dt in S frame. So, dr dt in S frame, rotating frame, and plus omega cross r, vector. This is what we get here. So, velocity of the particle in S naught is equal to velocity of the particle in S and plus omega cross r. So, now we will apply this equation on the velocity itself. That means for this vector A, I will be using this thing, and that means this thing. So, what we will get? ddt of this Vs naught in S naught frame is equal to. So, this is the whole quantity, this Vs naught. I want its ddt in S naught frame in the inertial frame. So, what do we have to do? We have to write this term. This whole quantity which I want to differentiate, I have to differentiate in S frame. So, ddt of Vs plus omega cross r in S frame, and then omega cross plus omega cross what? This whole vector. So, this vector Vs plus omega cross r. This is equal to ddt of Vs in S, this is 1, then ddt of omega cross r, and that is also in S, and then plus omega cross Vs, and then plus omega cross r. Check. ddt of Vs in S, this term we have written, then ddt of omega cross r in S, so that term we have written, then omega cross Vs that we have written, and omega cross r that we have written. Now, what is this? This is acceleration of the particle as measured in S naught frame. We have first found the velocity of the particle in S naught frame, and then we differentiated that again in S naught frame. So, very consistently we are trying to write the acceleration of the particle in S naught frame, inertial frame. So, this is A naught. A naught is, what is A naught? A naught is acceleration of the particle in S naught. And what is S naught? S naught is our inertial frame of reference. And this is equal to, here this quantity is velocity of the particle as seen in the S frame, and then we are also differentiating that in S frame. So, this is the acceleration of the particle in S frame. So, in S frame I am finding what is the velocity, how it changes with time, and that is the acceleration. So, for this we will write AS. This is acceleration of the particle in S frame. Now, come here. We will take the angular velocity of the frame with respect to inertial frame as constant. We can also write the ddt of that also. If the axis also changes or the speed also, angular speed also changes, we can always write that d omega by dt. That is not a big deal. But let us practical cases, most of the time we deal with situations in which this rotating frame rotates about a fixed axis at a fixed angular speed. In that case, this omega will be constant, and so we will say plus omega cross dr dt in s, dr dt in s. But what is dr dt in s? Dr dt in s is just v in s frame. Okay, we are differentiating the position vector in s frame, and therefore we get the velocity of the particle in s frame, this. And then I have this omega cross vs here, and we have omega cross r here. All right, this and this are same, so you can put a 2 here, multiplied by m everywhere, mass of the particle, 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 mass of the particle. Then what is this m and into a of s? Mass into acceleration. Okay, and now I will be dropping this s because now it is very clear that we are writing acceleration, velocity, everything in s frame, in the rotating frame, and here this is in the inertial frame. So this ma is equal to m into a naught, and a naught is acceleration of the particle in the inertial frame, and therefore it is equal to the net force applied on the particle at that instant. Okay, in inertial frame of reference I can use Newton's laws without any hesitation. Force, net force is equal to mass times acceleration. Here is mass times acceleration. So this is the net force. So this is total force, net force, real. All right, in inertial frame there are no pseudo forces. In inertial frame Newton's laws are valid. So F is equal to ma, the net resultant force, all the forces acting together, take the resultant of that, is equal to mass into acceleration. So this we write F net and then minus, because what we are writing, this quantity. So this minus everything. So minus this quantity is m omega cross r, this is it, and then minus 2 times m and then omega cross v, and all these quantities are in s frame. Okay, so that's it. So in s frame mass times acceleration is not equal to the net force as expected. S frame is rotating with respect to an inertial frame of reference. So S frame itself is non-inertial. Newton's law will not apply there. So mass into acceleration is not equal to F net. But then we say that okay, we will put from our side some terms which look like forces, and then we will say that mass time acceleration is this total force. So these are the pseudo forces that we have to supply from our side if we want to use Newton's second law in the non-inertial frame, in this case rotating frame. Once you add this, then you are allowed to use all the techniques, all the processes, all the results of inertial frames of reference. Now this quantity depends on the position of the particle. This quantity depends on the position of the particle, and this is known as centrifugal force. Now we are defining centrifugal force in the most general way. Centrifugal force, this quantity is called centrifugal force, and this quantity is called Coriolis force. So the forces which are actually acting on the particle, they are all here, and these are terms which are added to that force to get this equation that okay, mass times acceleration is this quantity which we can call total force, and then use all that inertial frame type results. The important thing to note is the centrifugal force depends on the position of the particle, not on the motion of the particle. A very common misconception is if a particle moves in a circle, then you have centrifugal force, m omega square r or mv square by r. Now the centrifugal force has no reference to the velocity of the particle. Whether the particle moves, whether the particle is at rest, whether it moves in a straight line, whether it moves in a circle, whether it moves in an ellipse, whether it moves in a parabola, whatever the particle does, centrifugal force does not depend on that. Centrifugal force depends only on the position of the particle. Where the particle is, that will decide what is this centrifugal force. We will talk just now. But here the Coriolis force depends on the velocity of the particle. It is not depending on the position of the particle, it is depending on the velocity of the particle. So this is the equation that we will be using Our earth is a rotating frame of reference, we know, and so we will be using this equation for further discussion and examples and problems. So keep this in your current memory. Mass times acceleration in the rotating frame is the real forces, then a centrifugal force, and then a Coriolis force. And centrifugal force is m omega cross r, and Coriolis force is minus 2 m omega cross v. This is also with a minus sign. Okay, so let's talk a little bit more on separately on centrifugal force first and then Coriolis force. So let us say I have a frame which is rotating about this line with an angular velocity omega, and let's call it z axis, and there's some origin here, and you have a particle somewhere here at certain instant. You have a particle here, and that is the position vector r, okay, which can move in this frame. Your x, y, z axis are there, and it can always move. So whatever x axis, y axis, z axis is already drawn. So you have x axis, you have y axis, and this whole frame is rotating about this z axis. Let us take this example, or I can always choose my z axis along the axis of rotation, and then x and y axis will be in perpendicular plane, and this r may be moving in any way. We do not mind, we are talking of centrifugal force. It only depends on the position. So at a certain instant the particle is here in my frame, and then there is the position vector, that is it, and we have to find what is this minus m omega cross r. This is the centrifugal force. So let me use cylindrical coordinate system. Okay, what is that? In cylindrical coordinate system, the position of the particle is defined. So if this is z, this is y, this is x, and here is the position. So that position is defined in three quantities. You drop a perpendicular from the particle to the z axis. Why I have drawn this inclined type of perpendicular? Because the particle may not be in this plane of the board, z, y, z plane. It can be outside the board or other side of the board, and then you have to drop a perpendicular like this on the z axis. Now this length is called s. So your first coordinate is this s. What is the other coordinate? Other coordinate is phi. If you drop a perpendicular on this plane, and then from the x axis how much is the angle, that is called phi. So if phi is more, that means it is more on the other side. Phi is 0, that means it is right here in this xz plane. So that is how the, and then this is z. So this phi is the second coordinate and z is the third coordinate. Okay, so if you have an axis, and then x axis, y axis, z axis, and particle is somewhere here. So on the z axis you drop a perpendicular, and that length of the perpendicular from the particle on the z axis, that length is called s, and in that direction if you use a unit vector, that will be written as s cap. And phi means if here is the z axis, the particle is here or here or here or here or here or here or here. So that we define using phi. Phi equal to 0 will be just above that x axis, and then phi changes means I am going this way, I am going this way, I am going this way. So that direction. So if I draw a circle, remember this particle is not going on the circle. If I draw a circle about this, then it will be, this is phi, this is phi changing, 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 and so on. So that direction is known as phi cap. Unit vector in that direction is known as phi cap. Okay, and z is of course z cap. Z is this. So this is called z cap or k cap. This is how we define cylindrical polar coordinates or cylindrical coordinates, and let us use that here. So if I drop a perpendicular on this, and this perpendicular length here is s, and this vector is s cap, phi vector will be going into the board, perpendicular to the board, going inside, and then we have okay, not going inside because I am taking this point not in the plane, but then you draw the circle and that, and of course this z cap is in this direction. Alright, so what is this r vector? This r vector can be written as, this length which is z. You drop a perpendicular from the particle on the z axis, and that origin to that point will be z coordinate. So this is z in z cap direction. This is equal to z in z cap direction and plus this s in s cap direction. So this vector is, this vector here plus this vector here. What is this vector? Z in z cap direction. What is this vector? S in s cap direction, and therefore you have r vector as this. And what is omega vector? Omega vector is omega in z cap direction. So what is this omega cross r? Omega cross r, this is equal to omega z cap cross z cap plus s cap. Now z cap cross z cap is 0, and therefore it is omega into s z cap cross s cap. And once again, just like ijk, you have the similar relation. You know I cap cross j cap is equal to k cap and all that. Similarly here, s cap cross phi cap is equal to z cap and similar things. So s phi z in that cyclic order. I want z cross s. So z cap cross s cap will be phi cap. Just like you have a k cap cross I cap. This is j cap. You have I, j and k. S phi z, I, j, k. K cross I is j. Z cap cross s cap will be phi cap. So this will be phi cap. So it is omega into s, and this is phi cap. And then omega cross r. Omega cross r. So this is omega and then cross this omega s phi cap. And this omega is omega z cap. So this will be omega square into s and into this z cap and cross phi cap. Once again, phi cap cross z cap will be s cap, and here I have z cap cross phi cap. So opposite, phi cap cross z cap is s cap, therefore z cap cross phi cap will be s cap, so minus s cap. So this is minus omega square s and s cap. So centrifugal force is minus m. So this minus becomes plus m omega square s and s cap. So what is the magnitude? Magnitude is m omega square s. And what is s? S is the perpendicular distance of the particle from the axis of rotation of the frame. Remember, axis of rotation of the frame, not axis of rotation of the particle. Particle is not going in circle, need not go in circle. Okay. So s, this s is the perpendicular distance of the current position of the particle from the axis of rotation of the frame which you are using to describe the motion. And then s cap, what is that s cap? In that perpendicular, on that perpendicular you draw a line which is going away. So that is the direction, that is the direction of centrifugal force. So we will take from here, we will take some examples of centrifugal force, and then we will move on Coriolis force, or the examples which are combining centrifugal and Coriolis forces. So we had derived the fictitious forces or pseudo forces in rotating frame of reference, and two pseudo forces we found. One was minus 2m omega cross v, which we called Coriolis force, and then the other was minus m omega cross r, that was centrifugal force. This omega is the angular velocity of the frame. This is important, of the frame, not of the particle, of the frame with respect to an inertial frame of reference. So that is this omega, and then there is a position vector of the particle. This is velocity of the particle. Everything measured from the rotating frame. This r, this v, acceleration, whatever, everything is measured from the rotating frame of reference. So these are the things. Now this centrifugal force, this depends only on the position and not on the velocity, and this depends on the velocity. So if the velocity of the particle is 0 in the rotating frame, then you don't need to consider this Coriolis force, and only centrifugal force you have to work. We have assumed that omega is not changing with time. If that changes with time, we will have yet another term involving that d omega dt. Okay. So, if velocity of the particle is 0 in the rotating frame, then I need not consider this Coriolis force, and the only pseudo force is the centrifugal force, and that is what we generally encounter in school physics. Like when we say sun earth system, I talked about it earlier, sun earth system, and we assume that the sun is very heavy and therefore it is always fixed at one point. Of course, sun is not a point, is a very big object, but whenever you have a spherical body, spherically symmetric in density, that can be replaced for this gravitational forces by a single particle at its center. Okay. So, our sun earth system, we have worked extensively with this in the previous chapter, central forces. Even if you consider the finite mass of the sun, this two body problem can be reduced to one body problem, and you can always assume that the center of force is fixed in inertial frame, and this orbit is almost circular. The eccentricity is very small, and so if you assume this circular orbit, often question is asked, if sun is attracting the earth, why the earth does not fall? Why does the earth not fall into the sun? Okay. So, why it is not falling on the earth in the sun if the sun is attracting it in this fashion? That is a very general question which is asked in interviews and other things. Now, if you want to answer from the rotating frame, that means you make a frame where the axes are rotating. The axes are rotating, you can put your earth on the x axis if you so like, and as time passes in the inertial frame, this earth is moving and this frame is also rotating. So, if I use that rotating frame, then the earth is not moving, the earth is not moving, earth is at rest. That sentence I would like to emphasize. So, if you are using rotating frame, if you are using this frame which is rotating, if you are using rotating frame, your grammar should be correct, and you say that the earth is at rest, the earth is at rest, not falling, not falling into the sun. Because the force of attraction or the gravitational force is balanced by the centrifugal force. Correct explanation. Since I am using rotating frame of reference, I have to use a pseudo force, and since the earth is not moving in that rotating frame, earth is at rest. Therefore, I do not have to consider Coriolis force, the only pseudo force is centrifugal force, and that centrifugal force m omega cross r, which turns out to be m omega square r, that and this g m by r square. These are two forces, one force is this way, another force is this way, and these two forces balance each other. The resultant force is 0, so resultant acceleration is 0, and if it is not moving, it will not move. So, it will just stay there. This is the correct sentence. But if you want to use this earth frame or inertial frame, if you want to use inertial frame, same origin, but now the axes are not rotating. So, in this frame, the earth is going in a circle, earth is going in a circle, it is not falling, and there your explanation is different. Your explanation is that the force of attraction creates an acceleration towards the center, towards the sun. So, your explanation is the force creates an acceleration, force does not create velocity, force creates acceleration, force brings out change in velocity, and that acceleration must be in the direction of the force. So, although force is towards the center, acceleration is towards the center, but velocity need not be towards the center. No one says that velocity should be parallel to the force, resultant force. No, acceleration should be parallel to the resultant force. So this creates an acceleration towards the sun, and that acceleration with initial velocity of the earth ensures that earth goes in a circle. So this explanation is also correct. If you are using that inertial frame where axes are not rotating together with earth, then you say that earth is going in a circle, and that means there is a radial acceleration, and that means okay, that's perfectly all right. This attraction force creates that acceleration, and since the acceleration is towards the center, and therefore it bends to create that acceleration, to have that acceleration, and it goes in a circle, does not fall. On the other hand, also you can think that you remember the radial acceleration is r double dot and minus r theta dot square. Okay, so r double dot is rate of change of r dot, and if initially r dot is 0, r has some value, r dot is 0, r double dot is also 0, so that r is maintained. Okay, if r is fixed, r is constant, that means r dot is 0 and r double dot is 0, but that does not mean that ar is 0. If the distance from the origin is not changing, if the radial distance is not changing, radial velocity is 0. Velocity, you remember, velocity, radial velocity is just r dot, because the velocity vector was r dot r cap plus r theta dot theta cap. So that radial velocity is just r dot. So if r is constant, r dot is 0, there is no radial velocity, there is no radial this r double dot, that does not mean that the radial acceleration is 0, because this term is also there. So if you have theta dot, if the theta is changing, then you can have acceleration without r double dot. So we had done some problems on this also. So these are the things that you must remember. The generally I hear the answers that since centrifugal force balances the centripetal force, therefore the earth continues in the circle and does not fall into the sun. That grammar is wrong. Okay, since I am writing this wrong statement, since the gravitational force is balanced by the centrifugal force, the particle continues in the circle and does not fall in the sun. This is not acceptable. If you are using the rotating frame, then only you are using centrifugal force. If you are using rotating frame, the earth is not going into circular path, the earth is stationary, and that is why this statement is wrong. If you are saying that earth goes in a circular path, that means you are using that non-rotating inertial frame. If you are using that, then don't talk of centrifugal force. If you are talking of centrifugal force, you are using rotating frame, then don't say that it is going in a circle. So these two things cannot go together. This statement is wrong. So these are some of the things which one should remember when using the centrifugal force. The centrifugal force you have to apply on the particle is the mass times acceleration of the particle, which contains that force aside contains that centrifugal force. So it is applied on the particle, but then it depends on the frame, which frame you are using, and from that axis of rotation of that frame, how much is the distance of the particle, whether the particle moves, does not move, goes in a circle or whatever. Okay, so let me do a problem, and we will have some practice on this rotating frame of reference and centrifugal force. So here is the question: a horizontal circular disc is made to rotate about its axis with a constant angular velocity omega in the vertically upward direction. So, the disk is horizontal and therefore, the axis is vertical and omega vector is in vertically upward direction. So, if I see from the top, it will go anti-clockwise. So, that is this figure drawn here. This is the disk and this is horizontal plane and it is going anti-clockwise if I am seeing from the top. A straight groove is made along a radius. This is a groove. There is a groove cut in this disk and a small block is placed gently in the groove at a distance b from the center. So, at a distance b from the center, rotating disk, remember, and we gently place a small block here. Find the relation between the distance moved in the groove and the time elapsed. So, that is the question. So, we are using this disk frame which is rotating and therefore, we are not given anything about friction and any other thing. Weight will be balanced by the vertical reaction force, contact force from the disk. So, the only force which is in the direction of motion is centrifugal force. So, we have centrifugal force and that centrifugal force, I can call it x axis, here, y axis here and z axis along the vertically upward direction, which is also the direction of omega. So, the centrifugal force which is minus m omega cross r, you can work out if the particle is somewhere here at a distance x from here, then this is minus m, omega is omega k cap, this is omega, cross this omega is omega k cap, cross this r is xi cap, right. At a time t, it has already covered a distance x and so the r vector is xi cap and this will be equal to minus m and then omega and omega. So, omega square and this x and then these cross products, cross k cross j. So, I j k, k cross I, k cross I, k cross I will be j. So, this will be j and then k cross j is minus I cap. So, it is minus r, this is minus I cap. So, it is m omega square x I cap, right. So, we have told it several times that in the distance from the origin m omega square times the distance from the axis, that is the magnitude of centrifugal force and it is away from the axis, right. So, that is the centrifugal force. You do have a velocity. This particle is not at rest with respect to this circle, this disk, this rotating disk. On the disk, it is going in the groove. We are using the disk frame and therefore, our x axis, y axis, z axis rotating about the z axis in the inertial frame, but in this disk frame also this particle is moving in the groove. So, velocity is not 0. So, we have to also look for the Coriolis force, right. Coriolis force is minus 2 m omega cross v, which is minus 2 m, omega is omega k cap and cross v is in x direction. So, it will be v I cap, which will be equal to k cross I is j. So, it is minus 2 m then omega v and then k cross I is j. So, it is j. So, you have Coriolis force is not 0 and that is in minus j cap direction, that means that is in the minus y direction, negative y direction. But in the negative y direction there is no motion because of the groove walls and hence you have yet another force by the wall. This Coriolis force, this is the centrifugal force, this is 1, this is the Coriolis force, this is 2. Remember, this is horizontal, I am drawing everything in the horizontal plane. So, this is your centrifugal force, this is centrifugal and this is Coriolis force. So, if this groove was not there, then it would have picked up velocity in y direction, okay. But now, since the groove is there, the wall will exert a force, a normal contact force N and that force will balance this Coriolis force. So, ultimately it is motion only under the centrifugal force, right. So, although the Coriolis force is there, but then this N, the normal force, that normal force is by the groove, balances the Coriolis force. And so your equation of motion is m omega square x. This is the force in x direction. Motion is also in this direction. This is equal to m d2x dt square. So d2x dt square is equal to omega square x. Okay. Had it been minus omega square x, the solution would have been that simple harmonic type, but it is plus. You can still make it of that type, minus here, I omega here, whole square here, and x. Call this quantity as some omega prime, which is complex, which is imaginary, and you have the equation d2x dt square is equal to minus omega prime square and x, and you know the solution. The solution is x is equal to a, and then I can write it this way, e to the power I x plus b e to the power minus I x, my t, I omega prime t here and I omega prime t here. This is x. If you write in cos sign, you can do that. This quantity is cos of omega prime t and plus I times sine of omega prime t, and similarly this quantity is cos of omega prime t and plus sine of omega prime t. So you can write it in the familiar cos omega prime t and sine omega prime t also. The constants will be correspondingly added. If you are writing cos omega prime t, you will have a and then plus b and so on and so on. So the constants can be adjusted, and you can do this. So this expression, cosine type or exponential type, both are equivalent, only these constants will change. They are anyway arbitrary and they will be decided by the initial conditions. So it is this, and here in our case it will be e to the power I, then omega prime is I omega, and this t here, and then plus b, this e here, then minus I here, and this omega prime is I omega here, and then t here, and this is e to the power minus omega t and plus b into e to the power plus omega t. So this is how x and t are related, and now a and b are two arbitrary constants to be decided by the initial condition. So what happens at t equal to 0? What happens at t equal to 0? At t equal to 0, the particle is at a distance b. So x is equal to b. So x is equal to b equal to a and plus b, because when you put t equal to 0, this quantity is 1 and this quantity is also 1. So it is a plus b. A plus b is equal to b. And the other initial condition is that we had put it gently. So although it is moving and we place it, we have not given any x velocity to start with. So x dot is 0, dx dt is 0, and from here if you write that x dot or dx dt or velocity of the particle, that will be omega b e power omega t. I am differentiating with respect to time. So omega and then b and then e to the power omega t, and from here it is minus and this omega minus omega and then this capital A and e to the power minus omega t. This is the velocity at time t, and at t equal to 0 the velocity should be 0, and therefore 0 should be equal to omega b, t is 0, so this quantity is 1, and minus omega a, this quantity is 1. So this is it. So b is equal to a, omega times b minus omega times a is 0. It tells me a and b are same, and here the sum of these two is b, and therefore I know that a is equal to b and is equal to b by 2. So place it here and you get that your answer. And x is equal to, what is a? A is b by 2, e to the power, and what is this? Yes, here, put it here. So a, this is b by 2, and then e to the power minus omega t plus capital B. Capital B is also small b by 2, and then e to the power omega t. So that's it. This is b by 2 and then e to the power omega t and plus e to the power minus omega t. This is called cos hyperbolic. E to the power omega t plus e to the power minus omega t divided by 2, that is called cos hyperbolic function of this omega t. So you can write this as b cos hyperbolic of omega t. So you can do a plot and see how that x changes with time and so on and so forth. So we will continue with more problems related to rotating disk. So to practice Coriolis force and centrifugal force, we will do some more problems, and the first problem of today is this: a horizontal circular disk of radius capital R is made to rotate about its axis with a constant angular velocity omega as shown in the figure. So it is going clockwise as seen by us, and you can work out that if this is x, this is y, z axis has to be coming out of the board, and therefore this will be omega in negative z direction. A straight groove is made on the disk at a distance x from the center. So this is a groove. In last lecture I had done a problem where the groove was passing through the center, and now the groove is at some distance from the center. That's the only difference. At a distance x from the center, a small block of mass m is kept in the groove at a distance b from the center and is released from there okay, in the disk frame. So we have to work in the disk frame, find the distance and the velocity of the block as a function of time at time t, and then find the normal force by the vertical surface of the groove at time t. So very close to the problem that we had solved earlier. So if at time t it is somewhere here, let us say, and this y coordinate is y here, y coordinate is here, and the x coordinate is fixed, the x coordinate is capital X, and then we can write the forces on this block that we have to take care. One is centrifugal force, and that is equal to minus m omega cross r, and omega is minus omega k cap, because it is going clockwise as seen from the positive z side. So this is omega. R vector at time t you can write as capital Xi and plus small y j. Okay, small y is variable, as a function of time this will increase, capital X will be fixed. So this is R. So you can write this as equal to minus m, and this omega vector is minus omega k cap, and then cross this omega is again minus omega k cap, cross r vector is capital X I cap and plus y j cap. And then you first evaluate this. This is m omega k cap cross. Now here this is minus omega x, so minus omega capital X, k cap cross I cap will be j cap, so it is j cap, I j k, so k cross I will be j, so it is this, then minus omega y, and k cap cross j cap, k cap cross j cap is minus I cap, so this is minus I cap. So you can make it plus here, I cap times I cap here. Okay, and then do this cross product. What is this? M omega square x, m omega square x, that is this, and then we have a minus sign here, and k cap cross j cap, I j k, k cap cross j cap is minus of I cap, so this will be I cap here, one minus here and one minus coming from there, and here it is plus m omega square y, and k cap cross I cap is j cap, so it is this. We could have written it directly also. The centrifugal force is m omega square and the distance from the rotation axis outward. So if in this figure the centrifugal force must be in this direction, and that is m times this omega square times this distance, and in this direction. So you can easily write this expression. So this is centrifugal force. Then you have Coriolis force. What is Coriolis force? It is minus 2m omega cross velocity. So that is minus 2m, then minus omega k cap, and cross velocity. Velocity is only in y direction, nothing in x direction, it can only move in the group, so it is just y dot. You can write that as y dot or dy dt. And in j cap direction, this rate of change of y gives you the speed, and then j cap direction, and once again this minus and this minus is plus, so 2m omega y dot, and then k cap cross j cap is minus I cap, so it is minus here and I cap here. So that is the Coriolis force. So you have Coriolis force in the x direction, velocity is in this direction, so Coriolis force is just this much, which is in x direction, and the centrifugal force has both components, x component and y component, and therefore if it is to go only in y direction, x direction there is no acceleration, so the force in x direction should be 0, right. So you have yet another force, and that is normal force, that will balance it. Okay, you have Coriolis force I component, you have centrifugal force I component, so there is an I component, and that I component has to be balanced, it has to be balanced, and therefore another force, the normal force is there n, and this n could be from this side or this side. The inner side will exert a normal force in the positive x direction, the outer side will exert force in the negative x direction. So what is the resultant, that we do not know, so we will just write n is equal to n I cap. It is either this n can be positive or negative, so it can be in positive I direction or it can be in negative I direction. Alright, so part 1, first part, find the distance and velocity of the block at time t. So I need y and I need y dot. Okay, so the force in y direction, let us see force in y direction, that comes from here. So this is m times omega square y, and therefore acceleration y double dot is equal to omega square y. We have already solved this equation in the previous lecture. Y is some a e to the power omega t and plus e to the power minus omega t. Okay, using the initial conditions. What are the initial conditions? At t equal to 0, y should be equal to b and y dot should be equal to 0, that is the condition. Our general solution would be a, and this a also I know, this a is b by 2, Our general solution is a omega t plus b e power minus omega t, but when you put these conditions you get this as y, and then y dot you can differentiate, so b by 2 and omega will be there, e power omega t and minus e power minus omega t. So that is the velocity in y direction. That is part A. Now come to part B. In x direction the total force has to be 0. So let us collect all the x components. So from centrifugal force I have m times omega square x, capital X, that is in I cap direction. From Coriolis force I have minus 2m omega, and then y dot that is in x direction, and plus n, that should be equal to 0, and therefore n should be equal to 2m omega y dot, and y dot is here, which is b omega by 2, and then e to the power omega t and minus e to the power minus omega t, this is y dot. So this comes from the Coriolis force, n is equal to, this goes on the other side and becomes plus 2m omega, this is 2m omega, and y dot is b omega by 2 and this much, so it is, and from here it is minus m and then omega square and times x. So that is the equation, you can cancel this 2 here, this omega can be put here, omega square, and you can make some decoration, some simplification looking, and this is the normal force. Now the thing is that this y dot is increasing continuously, to start with at t equal to 0, this y dot is 0, and therefore n will be just this much, and which is negative. The x, this normal contact force is in negative x direction, that means this outer wall is pushing it more than the inner wall. But then this y dot is increasing. It is increasing. Initially it was 0, but then it is increasing, and it may become equal to this, in which case the normal force will be 0, and after that this will be further increasing, and this may become positive. So that means to start with, you have this outer wall which is pushing it more than the inner wall, and the things can reverse after some time. So I have plotted this function as a function of time. I had taken some arbitrary m equal to 1, omega equal to 1, etc., b, some values I had taken, and then for various values of t, I have calculated this to see how it varies with time, and that is in the shape of a graph, and that graph I am showing you, and I am describing what this graph is. So I am showing you 3 graphs. In fact, the first graph which is on your screen is position as a function of time, that means y as a function of time. You have the expression on the board, and then if you plot that as a function of time for a specific choice of omega and b and all those things, this is the kind of a graph. This is the kind of graph. It is increasing. To start with, this is 2, b equal to 2 you can take, and then it increases, it increases, it increases, and it increases. This is the position as a function of time. Then we have another graph. This is another graph which is velocity as a function of time. Looks quite similar. E to the power omega t plus e to the power minus omega t, and e to the power omega t minus e to the power minus omega t. Qualitatively they look very similar, because that e to the power minus omega t, that becomes very small. So whether you add it or you subtract it doesn't make much of difference after some time. So that is velocity as a function of t. And more interesting is the normal force as a function of t. The normal force as a function of t. Look at it very carefully and see where is the 0 on this vertical scale. See where is the 0 on the vertical scale. So initially when t equal to 0, 1, 2, 3, 4, you can see from this graph is this normal force is negative. The outer wall is pushing more, but after some time, some 4.4 second or so, n becomes positive. So there is a point, there is a time when both sides are pushing equally. That means probably none of the two sides are pushing. The resultant is 0, and then after that this inner wall is pushing more than the outer wall, and so on. So that is the kind of variation you have in n. Here is another problem. It says a horizontal circular disk is rotating about its axis with a uniform angular velocity omega in vertical direction, vertically upward direction. A small coin is placed at a comma 0, these are xy coordinates, and is released from rest with reference to the coordinate axis shown in the figure. Find the position of the particle as a function of time and a sketch of the path. So here are the axes. You have the circular disk, and going about this vertical axis, the disk itself is horizontal, and you have x axis and y axis fixed on the disk, and we have to solve everything from the disk frame. We have to sketch the path of the particle with reference to these axes only. Everything is to be done in this axis. Now you remember, this was the live demo that I gave. We had a circular disk, and then it was rotating about a vertical axis, and then we put a small black ring there on the disk somewhere, released from rest, and then we saw the path. So that is what we are trying to do the theory. Okay. So in the disk frame, what are the forces? And the vertical normal reaction of the platform is balanced by the weight of that coin, and friction we are neglecting. So the only forces are pseudo forces in the horizontal plane. And what are those? The forces. So from the disk frame, so we are working with the disk frame only. So from the disk frame, the force, net force, is just the pseudo forces, and that we have m omega square, and then r. This is the centrifugal force, omega vector cross r, and you know, once it is axis is known, then distance from the origin m into omega square into that distance in the outward direction. So from the center is just this r vector, centrifugal force, and then you have Coriolis force, and Coriolis force is 2m omega cross v. Okay, so this we write as m omega square xi cap plus yj cap. I am writing at a general time t. So if the coordinates of the particle, position of the particle on the disk is x comma y with reference to the axis shown, then this position vector r is x I cap plus y j cap, and minus 2m omega is omega k cap. This omega vector is omega k cap, and cross velocity will be x dot I cap plus y dot j cap. The x component of velocity and y component of velocity. So this is m omega square x I cap plus y j cap, and then minus 2m omega into omega you can write here, and then okay, 2m omega x dot and k cross I is j, so j cap here. The first term I am writing minus 2m omega k cap cross x dot I cap, this I am writing, so minus 2m omega x dot, and then this is j cap. Second term is minus 2m omega and y dot, and then k cap cross j cap is minus I cap, so it is plus here and I cap here. So this is a total force. Remember, we are using the rotating frame. This force does not exist in reality, but if I use these forces, I can use Newton's second law. I can write this force is equal to mass times acceleration, right? So mass times acceleration is this. This is mass times acceleration, and which is m x double dot I cap plus m y double dot j cap. So this is m x double dot I cap and plus y double dot j cap, and let us write the x component from the both sides and y component from the both sides. So you will have two equations. What are those? M cancels out from everywhere, so m I am not writing. M cancels out from everywhere. X double dot is equal to I cap only, omega square x I cap, so omega square x here, and then I cap here, so plus 2 times omega y dot. So that is x double dot. Then y double dot, the y component of the acceleration as seen from the disk frame, j cap, so omega square y, and then j cap is here minus 2 omega x dot. These are the two equations. You have acceleration in x direction, d2x dt square, and here you have x, that's okay. But here you have this y dot, so this is d2x dt square, and here it is dy dt. So how will you integrate? And similar the situation here, this is d2y dt square, but then here you have dx dt. How will you integrate? But there is a beautiful technique for doing that, and that is you multiply this equation by I. What is this I? This I is square root of minus 1. It's not I cap, it is just I, which is square root of minus 1, and then add these two, x double dot plus y double dot, x double dot plus I times y double dot is equal to, here omega square x plus iy, and here 2 omega, let us take minus 2 omega common, we are adding, so x dot here, and then minus omega is taken, so y dot I times y dot here. Okay, so let's check. I have to multiply this whole equation by I, so this I have put I here, then this I have put I here, and here 2 omega y dot and minus x dot I. Alright, so this I comes here, correct? So we are adding minus 2 omega x dot I, minus 2 omega x dot I, then here it is plus 2 omega y dot, plus 2 omega y dot. Take one more I common here, take this I outside, what will happen? This will be omega square x plus iy minus 2 I omega. I have taken this I also outside, and this becomes x dot plus iy dot. Okay, I into I is minus 1, so that plus becomes minus, and I if goes here it will be I x dot. So this is it. Now define q, which is x plus iy. Let us define this quantity q, which is x plus iy, and then it is q double dot equal to omega square q here minus 2I omega here, and this is q here. So now I have an equation in q as a function of time. So I can bring this side, q double dot plus 2I omega cube and then minus omega square q equal to 0. And this is a very standard second order differential equation with constant coefficients. You have second derivative q double dot. Q double dot is what? Q double dot is dq, d2q dt square, and then plus 2I omega, and then q dot, this is q dot, this is q dot, where is q dot, x dot, y dot, so minus 2I omega q dot here, and this is q dot here, so dq dt, so dq dt here, and then minus omega square, so this is plus I omega square and q, and this is equal to 0. Okay, so it's a very standard equation. Though in textbooks of differential equations you will find this d2y dx square plus c1 times dy dx plus c2 times y equal to 0. This is a standard statement of the differential equations of second order differential equation with constant coefficients. That's the heading, and the rule is that you write y as e to the power alpha t and put it here. If you put it here, and then you get second derivative, so alpha square e to the power alpha t plus c1 into first derivative, so alpha times e power alpha t, then plus c2, and simply e to the power alpha t is equal to 0, and that gives you alpha square plus c1 alpha plus c2 equal to 0. Then this is a quadratic equation. You will get two values of alpha, say alpha 1 and alpha 2. Now if alpha 1 is not equal to alpha 2, then your solutions are y is equal to, this is all x, this I have written x here, so let's write x here. All right, so x here, x here. So your solutions are y is some constant, arbitrary constant, e to the power alpha x, that is alpha 1x, plus another constant e to the power alpha 2x. This is the final general solutions. You have second order equation, you have two arbitrary constants, done. But if alpha 1 is equal to alpha 2, that happens when your discriminant is 0 and all that, if that happens, then the rules are different. Then y is equal to a plus bx and then e power alpha x, whatever that, alpha 1 is equal to alpha 2, so both are equal, anyone you put here. So this is the rule, remember this is the rule, and according to this rule I have to solve this equation. So let me make some space here to work. So let us do this. What we will do, we will be putting q equal to e to the power t here, so alpha t, so d2q dt square, so alpha square e to the power alpha t. So this will be, let us say, let me do here, alpha square e to the power alpha t, this is this part, plus 2I omega and then dq dt will be alpha times e power alpha t, so alpha times e to the power alpha t, and then plus I omega whole square, so plus I omega whole square, and q is e power alpha t, and that is equal to 0, so this is equal to 0, and it gives me alpha square plus 2 times I omega times alpha plus I omega square equal to 0, and that means alpha is equal to alpha plus I omega whole square is equal to 0, so alpha is equal to I omega comma I omega. Okay, so the two roots of this quadratic equation are equal, and therefore I have to use this recipe. My general solution will be q is equal to some arbitrary constant capital A plus bx, so plus bt, and then e to the power alpha t I omega t minus I omega and minus I omega. Okay, so minus I omega t. What are these arbitrary what are these arbitrary constants capital A and capital B, and how do we get it? From the initial conditions. If this is q, dq dt will be you have t here, you have t here. So I put this thing here, I differentiate this, so I get to b, and I put just e power minus I omega t here, and then I keep this a plus bt intact and differentiate this minus I omega and then e power minus I omega t. Okay, q dot differentiation with respect to time. So two factors, one factor is here, another factor is here. So first I keep this factor intact and differentiate this factor, and then I keep this factor intact and differentiate this factor. So minus I omega e power minus I omega t, this is our q dot. So let us say what happens at t equal to 0. At t equal to 0, we have released the particle from a comma 0 on this xy plane. Okay, so x is equal to a, y is equal to 0, therefore x plus iy is equal to a, and therefore q is equal to a. At t equal to 0, q is equal to small a. So use this thing here. Small a is equal to t equal to 0. So t is equal to 0. So this factor is gone. Capital A into e power minus I omega t. T is equal to 0. So e to the power 0 is 1. So just a. Capital A is same as small a. We released this coin from this point a comma 0, and that tells me that this capital A is nothing but a. Then what is q dot at t equal to 0? At t equal to 0, x dot is 0, y dot is 0, and therefore q dot is 0. Released from there. So q dot is 0, and here is q dot, and at t equal to 0 this should be 0. So this tells me that 0 is equal to t is 0, so it is b plus a plus bt. This t is 0, so it is a plus a, and then here minus I omega, this minus I omega, t equal to 0, so this factor is 1, right. So once again, at t equal to 0, no speed, so x dot is 0, y dot is 0, so q dot, which is x dot plus I y dot, is 0, so that is why this is 0 here, and here t equal to 0, so t equal to 0, this is 1, so capital B, plus t equal to 0, so this is capital A, so this is capital A, this is 1, so it is minus I omega, and this tells me that B is equal to I omega A. So B is equal to I omega A. I know now what is A and what is B. This is I omega small a. Finally, Q is equal to A is small a plus B. B is I omega A. So I omega A, and into T. So this is T here, and then e to the power, then this whole thing e to the power minus I omega t. So this is Q. What next? We write this Q as x plus iy, and then compare the real part this side, imaginary part this side, and that will give me x as a function of t and y as a function of t. So we will continue from here. Next lecture we will complete it and go to the next topic. So we were discussing our disk and that small object experiment. We had seen the path, and now we are trying to do the physics of it and see what kind of path we get from our equations using Coriolis force and centrifugal force. So we reached up to here. We defined Q as x plus iy, and this was Q, and then for Q we solved this differential equation and we got some solution, and then we put these initial conditions to get those arbitrary constants a and b, and then we finally got the value of Q as a function of time, which is here, and from here we can get x and y because Q is x plus iy. So let us first separate the real part of it and imaginary part of it. So this is equal to a plus I omega a t, and this quantity here is cos of omega t minus I sine of omega t. This is called de Moivre's theorem. This quantity is equal to this quantity. Open the bracket, a multiplied by cos omega t. So, a multiplied by cos omega t. Then this I omega a t plus I omega a t multiplied by cos omega t. So, cos omega t here. So, I have done this part, now this part. So, minus a I sine omega t, and then this part I into minus I is plus 1. This I into I is minus 1, and with this minus it is plus 1. So, it is now plus omega a t from here, and then sine omega t from here. Okay, so let us check once again. A into cos omega t is here. Then let us say from this side, a into minus I sine omega t, a into minus I sine omega t is here. Then I omega t into cos omega t. So, I omega a t into cos omega t is here, and this is plus 1. So, omega a t sine omega t. Okay, and this q is nothing but x plus I y. And now you know, if you have two complex numbers with a real part plus I times imaginary part and both sides, then you can equate the real parts and the imaginary part separately. So, x is equal to a cos omega t, real part only, a cos omega t. This is imaginary part, this is imaginary part, this is real part, plus omega a t sine omega t. Okay, and y is equal to, so leave out this I, omega a t, this is omega a t and cos omega t, and then minus a sine omega t. These are the equations for position, x coordinate and y coordinate as at any subsequent time t. So, these are the solutions of our problem, and dimensionally we can check that everything is all right. A is length, this is length, so A is length, fine. Omega is 1 by time, and this time here, so once again same dimension as A, so fine, dimensionally also okay. So, these are the equations. Now, sketching. So, what I have done is I have made a graph on Excel. I have taken A equal to 1, omega equal to 1, and then for different values of t, I have plotted this x and y, calculated this x and y for different values of t, and then I have plotted the graph between x and y, which gives me the path, sketching the path. So, that I will show you now. So, this is that graph, and you can see the nature of the path. It starts somewhere on this x axis, horizontal x axis, 1 it starts, and see how it turns, how it goes away from the origin. The distance from the origin is increasing, and then it is curving, and then finally it goes towards the edge. So, that is the kind of path we obtain from our equations, and the kind of path on that disc on which I had sprinkled some wheat flour, and then my small ring was going showing the path. They are not very different qualitatively. Yes, so this was the kind of path that I got from on my disk also. So, now I will continue with this non-inertial frame little bit, and we will discuss the Earth's frame. Normally, when we use all kinds of this projectile motion and this and that, we use that lap frame or our road frame or our field frame as inertial. The Earth is taken as inertial frame of reference, but I had said that it is nearly inertial, it is not really inertial, because it rotates about its own axis and then it rotates about the sun. So, what we will be doing here, we will be taking account of rotation of Earth about its own axis. So, any frame which is fixed on the Earth's surface, our lap frame for example, the frame that we use to describe railway stations and roads and trees which are already there. So, we use this surface of the Earth as rest, okay, as at rest, and then we set up our xyz coordinates there, xyz axis there, and then we use it. So, now let us take into account that small non-inertiality that is inducted because of the rotation of Earth around its own axis. So, one problem that will arise using Earth's frame, that when we set up our coordinate axis, the coordinate axes are set up on the surface of the Earth. So, our origin is on the surface of the Earth. When I was deriving all those equations for equation of motion ma equal to some Coriolis force, centrifugal force, this that, I had taken the origin of this rotating frame on the axis of rotation. But this time the origin of our frame that we will set up in our laboratory, for example, that is not on the axis of rotation, that is 6,400 kilometers away. And if Earth is rotating, that origin is also rotating about that axis of rotation. So first let us handle that situation separately, and then we will go to the Earth's surface frame of reference. Now suppose I have a coordinate system, and these are the XYZ axis, and this is the origin, and then there is another frame of reference in which here is the origin, and then let us say we have these as this is an inertial frame of reference. Suppose this is an inertial frame of reference, and this frame, it goes around, the origin goes around this point, this origin goes around this point. So let me draw a circle which is like this. So this origin goes on this circle, but the axis remain fixed in this frame of reference. The direction of axis remain fixed in this frame of reference. That means as time passes, as seen from this frame, this is our inertial frame, this is origin, now the origin goes here, but the axis remain in the same direction. It's like this. It's like this. Okay. So it's something like this. Suppose I have something here, and then I am taking it on a circle. See, I am taking it. Suppose this is the origin. I am taking this whole thing. Go like this. Just go like this. What is this? Is it a rotational motion? It's a translational motion. It is a translational motion. At any instant, if I am taking it from here to here in this whole path, suppose I am taking it from here to here. See, all the points are displaced by the same amount and in the same direction. See, part by part. Here, yes. 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 So in any given small time interval, all the points of this are going in the same direction with the same speed, or in any given time interval they are displaced by the same amount in same direction. So velocities of all the particles, all the points of this frame is the same, and therefore acceleration is also the same. The acceleration of this origin is same as the acceleration of this point. Acceleration of this origin is same as the acceleration of this point. Acceleration of this origin is same as the acceleration of this point. Or you take any point which is fixed with respect to this frame, the acceleration of that point is also the same. Alright, and we very well know what is the acceleration of this if it is going with an angular velocity omega, and if this radius is r, and if this origin is going, it's not a rotation, so I will not write this kind of symbol. No, I will not write this. This is not a rotational motion, right? So this is origin that is going in a circular path of radius r, of radius capital R, with angular velocity or angular speed, angular velocity, fine, for one particle I can always define angular velocity omega. This is it, and hence the acceleration of O is omega square into r towards the center of the circle. Okay, so the acceleration of this origin is towards the center. When the origin here is here, the acceleration is in this direction. When the origin is here, the acceleration is in this direction, and the magnitude is omega square into this capital R. And all the points, not only this origin, this point also. This is also going in a circle of radius capital R, convince yourself. This point is also going in a circle of radius capital R, convince yourself. The center is not here. For this particle, center is at some different point. This particle or this point, the center is at some other place, but the whole circle is different, but just displaced. And hence the acceleration of all these particles will be same. Acceleration of all these particles or points which are fixed in this frame are same at every instant. As time passes, acceleration will change, but at any given instant, acceleration of this, everything is same, and that is this. So we will use the law or the rule that we had in the very beginning we had discussed. If a frame is translating with acceleration a naught with respect to an inertial frame, the pseudo force which is to be used in that frame is minus m a naught. So if a frame is accelerating, is having some acceleration with respect to some inertial frame, and this is our accelerating frame, and it is translation, it's translational motion only, then if this is a naught, then the pseudo force which is to be used on the particle of mass m is minus m a naught. M a is equal to force, resultant force, and minus m a naught. This is the total applied force. This is force, this is not force, this is pseudo force. So all the forces are here, and then this is the pseudo force that we are adding in our equation to enable us to use Newton's second law in this accelerating frame, that we will be using for this frame. For this frame also we will be having the same equation, So m a is equal to total force F and minus m into omega square into this r vector plus here, because you have another minus. This acceleration is inward and therefore this is outward. I am not calling it centrifugal force, although it looks like centrifugal force, okay, because this is same, this is r. If your particle is here going this way, particle is here going this way, particle is here going this way, particle is here. So if I am seeing from this frame, then the same force m omega square r is to be used. In centrifugal force, distance of the particle from the axis. For different particles it is different. So this will be added if the origin is translating. And then once again we come to the Earth frame of reference. If we have Earth and then we are somewhere here, so I can always reorient. So we are somewhere here. This is the axis of rotation, north south, geographical north south, and say this is the rotation. In that case our origin is here, and we fix up our axis system maybe this way, maybe this way. This is vertical, okay, this is vertical, this is horizontal, then perpendicular horizontal, two horizontal axes, one vertical axis. Now as time passes, the Earth rotates, this origin is going in a circle. This origin is going in this circle. This whole Earth is rotating, so this origin is going this way, this way, this way, this way, this way, this way, and here is the center. So one thing is that origin is rotating, is going on this circle. Another thing is the direction is also changing. The whole Earth is rotating with respect to this about this NS line, and this is fixed with the Earth. So this is also rotating. If the whole Earth is rotating, this is also rotating. So this is here, when it comes here, this will be going like this. This line will be here. This line will be here. Similarly, this line will be somewhere here, and that line will be somewhere else. So it is also rotating with respect to this axis. This is the axis of rotation of my frame, and the angular velocity is omega. So those Coriolis force and centrifugal force will be there. On top of this, this kind of force will also be there. So what we will write? We will write mass times acceleration. Now I am using this frame which is fixed on the Earth's surface, and I am seeing some particle m which is going with some velocity v, some acceleration a, as seen from this frame of reference. That a is here. Mass times acceleration is equal to total force. This is the total force applied, real forces, and then I have minus or plus this quantity, this is plus m into omega square r vector. What is this r vector? This r vector is from this origin, this origin is going on a circle, and then the center of the circle and the position of the origin, that is r vector, capital R vector here. So here it will be, if I am here, then this is the circle, this is the center of the circle, here is the origin, so this is r vector, this is r vector. And if I use this capital R for the radius of the Earth, Then this r vector is here, but let me not write it r, because r I will be using for the radius of the earth. So whatever, this particular vector, any vector you write here, so this vector and in this direction, that I have to write here. So this will be if I call it some say E cap, okay, it is perpendicular to this ns axis wherever this origin goes. So this will be m omega square. Now okay, little bit of geography. This is our equator here, and then if you are somewhere here on the earth, you are on the equator, and we say that the latitude is 0. Okay, the latitude is 0 if you are here, and if you are above the equator, then this angle, how much above you are going, is known as latitude. This is the latitude, and then 90 minus this, which I write lambda, is called co-latitude, and I will be using this co-latitude. This lambda is co-latitude, and what is that lambda? If you are somewhere on the surface of the earth, join that to the center and see what is the angle of that line with the axis of rotation of the earth. That is lambda, known as co-latitude. In geography, more commonly used angle is latitude, which is this angle here, and the relation is lambda and theta, they add to 90 degrees. So this is co-latitude. So sine of lambda, capital R into sine of lambda, and then in this direction, in this E cap direction. So that comes from the shift of the origin, rotation of the origin, and then rotation of the frame. Those things will be there, minus m omega cross r vector and minus 2m omega cross b. This r vector is the position of the particle. If the particle is here, then from the origin you join this as r vector from your origin. If I am setting my axis system here, then whatever origin I choose from there, what is that r vector, that is here, and what is the velocity as seen by my frame, that is here. This is our Coriolis force, this is our centrifugal force, and this is a constant as far as the particle is. Only mass of the particle is here. Otherwise the position of the particle, the velocity of the particle doesn't matter. And if I am writing acceleration, if I am dividing by the mass, this mass also goes, and then this quantity is just constant. So, and also if I am using this earth surface and I am looking at some particle which is moving under some forces, then the gravity is always there, so m times g will be always there, and then you have this and other forces, okay, other forces. If you are only looking at the motion under the gravity, then this will be 0, and then other things, all these things, m omega square r sine lambda E cap minus m omega cross r, all these things will be there, and minus 2m omega and then cross b, all these things will be there. What I am doing is this quantity and this quantity, this is independent of the position of the particle, velocity of the particle, acceleration of the particle, and therefore these can be combined. You can take m out. If you take m out, this will be m times g and plus m omega square r sine lambda in E cap, and this is just a constant, doesn't depend on anything if m is taken out, and this we will call g effective, So this will be absorbed in g, and these two terms taken together we will call g effective. So m times g effective, any other forces if present, and then the centrifugal and this Coriolis force. This will be our equation of motion, and we will be using this equation for some simple cases, a freely falling particle or maybe a projectile and so on. So we were discussing frames of references that we normally use at the surface of the earth, like our laboratory and so on. So we place our origin on the surface and then put up XYZ axis. Now this axis system rotates with respect to this NS line, which is the North Pole South Pole line about which this earth is rotating. At the same time the origin is going in a circle, because origin was also fixed on the earth, the entire earth is rotating, X, Y, Z, everything rotate about that same axis, and then we set up our equations. And we found finally that we have this equation, mass times acceleration as measured from our frame, is any applied force which is there, which we can write again the gravitational force mg and other forces, because most of the time that we will be working with this force alone. And then you have this m omega square capital R radius of the earth sine lambda. Lambda is the co-latitude. So from this equator, how much above we are, that angle is known as latitude, and 90 degrees minus that means angle from this rotation axis and this vertical angle between that is lambda, known as co-latitude. So that lambda is here, and then the direction of this term is towards the outward radial direction of this circle, like this. So that E cap I have written, and then we have usual centrifugal force term and Coriolis force term, and this small r is the position vector of the particle from the origin that we have chosen on the surface. So this is the equation, and these two terms if I consider, I can write this as m into this g effective, and g effective is the g which is the vertically downward direction passing through the center of the earth, that is this, and then together with this we have omega square capital R sine lambda and E cap, and this g effective is independent of your particle. The motion of the particle or anything, mass of the particle, velocity of the particle, it's all independent, it's fixed at a particular position of the origin, right, of your frame. So that lambda decides whether you are working in Kanpur or you are working in Shimla or you are working in Srinagar. So that will decide the lambda, but it's independent of particles. Once you have fixed the frame, this term is fixed. Okay, so this whole thing which is independent of your particle and its motion is known as g effective. And let's see what this g effective is, how much it differs from the real g. We have to just change this g to g effective if we want to work on this frame. So our first task is to look at this g effective. All right. So once again, let me draw this. Your g is towards the center. So let me draw another circle because that is too clumsy. Okay, and suppose I am here. This is the center of the earth. This is that rotation axis N and S. Okay, and then this point is going, this earth is going this way, so this point is also going in that circle. And then this is the direction in which I have to write that omega square capital R and sine lambda. This angle is lambda, and this is a right angle. This is a right angle triangle, and this is lambda. So if you see how much is this, omega square R and then sine lambda in this particular direction. So that is this term, and g is in this direction. 9.8 meter per second square. That g is in this direction, and resultant of these two will be the direction, and it will give me the direction and magnitude of this g effective. So this is our g effective. Okay. So because of the presence of this term in general, this resultant will not pass through the center of the earth. And for us, this is our vertical direction. This is the true vertical. This is vertically downward, and this is vertically upward. But for us, we will only have access to this direction. This is our vertically upward direction. What does this mean? This means that if I have, let us say, a pendulum just staying at rest, not oscillating. So I have just suspended a pendulum and it is at rest. That strain, we understand this is the vertical direction. That is how operatively we find our vertical. Plumb line, people call it plumb line. All these walls which are there in the room, they are made vertical by using the plumb lines. So they just suspend some heavy block here, heavy ball here, and then they make all the walls, vertical walls, parallel to that string. So this is our vertical, okay, which is in fact in the direction of this g effective, because since it is in equilibrium, since it is in equilibrium and there is no Coriolis force, and I can put up my origin right here, so that this term is also 0, and therefore this T here and this M times G effective here, they should balance each other, and therefore the direction of this string should be in the direction of this G effective opposite to that, and the magnitude should be equal to mass times G effective. So for us this is the vertical. For us sitting here, this is the vertical direction, this is the vertical direction which is not passing through the center. When we make things horizontal, normally when buildings are made, we need floor to be very horizontal, the beams, many of the beams are horizontal. So these people use water level, okay, because free surface of water is always horizontal. Now what is that horizontal? That is perpendicular to this G effective. That is perpendicular to this G effective. In the on the globe, what is the horizontal? It is a tangent plane to this surface. If I show you on the globe, suppose this is our earth, this is the axis of rotation, north pole of this earth, south pole of the earth, and then this earth is rotating about this, and suppose our laboratory is somewhere here, suppose somewhere here. So what is vertical? This is vertical, this direction is vertical, which is going through the center of the earth and the point where you are looking for that vertical, and perpendicular to this vertical, that will be the tangent plane on the earth's surface from this point, this tangent plane. This is the horizontal, perpendicular to the vertical, and then in this horizontal I have north, south, east, west, everything. And how do I define north? This is north pole. So if I am here, then you look for that shortest curve from that point to this north in this direction. In this direction, the tangent in this direction, this is north, all right, this is north, and then perpendicular to that on the right side, this is east, and opposite to that is west, and then opposite to north is south. So that is how our directions east, west, north, south are determined, all in the plane which is tangent to this earth surface from the point of your interest, from the origin of your frame of reference. So that is how north, south, east, west are defined. At different places these directions will be different, but wherever you are, accordingly you define north, south, east, west, horizontal. But in when we are determining the horizontal plane using water level or whatever, it's not the tangent, it is slightly different, it is perpendicular to G effective and not G, okay. So that is the situation. Now let us see how much is the effect, how much is this deviation angle, how much is the difference between this G and this G effect. So it's a simple parallelogram addition of two vectors, one is G here, another is omega square r sine lambda here, and there is an angle between these two, and how much is that angle? If this is lambda, this angle is 90 minus lambda, and therefore this angle is theta equal to, not this theta, it is 90 degrees plus lambda, this angle between these two vectors. So I have now two vectors, and this is the parallelogram law addition of these two, this is G effective. So you remember, if you have a vector A here and a vector B here, and the angle between them is theta, and this is how you complete the parallelogram, and then you say that this is that resultant of these two, this is that sum of these two resultant, and you can call it C, and then C square, magnitude of C square is equal to A square plus B square plus 2AB cos theta. This is the magnitude, and this resultant makes an angle alpha with this A vector, where tan of alpha is if this is alpha, tan alpha is this perpendicular divided by this base, and this perpendicular itself, this is theta, remember, and this is B, so this is B, so this perpendicular itself is B sin theta, and then divided by this whole thing, which is A plus B cos theta. So this is our class 10th vector addition rules. Accordingly, let us apply it here. So the magnitude of G effective square is equal to A square, first vector, let us say this vector G, then plus B square, that is omega square r sine lambda whole square, and then plus 2 times AB, that means G here, omega square r sine lambda here, and cos of the angle between the two vectors. So cos of 90 degrees plus lambda. The angle between the two vectors is 90 degrees plus lambda. So G effective is equal to square root of G square, or you can take that G here if you so wish. You can take this G here. So it is 1 here plus omega square r by G, and then sine lambda square of this, and minus cos of 90 degree plus lambda is minus sine lambda. So minus 2 times omega square r by G and sine square lambda to the power half. Okay, this G square we have taken out and power half, therefore it is G. So divide by G square. So 1 here, omega square r sine lambda whole square divided by G square. So that is here omega square r sine lambda by G square. Then this is minus of sine lambda. So it becomes sine square lambda here and a minus sign, and divide by G square. So 2 times omega square r sine square lambda by G to the power half. So this is the magnitude. And the direction? The direction, this how much is this angle alpha? From the true vertical, how much is our vertical deviated? So that angle is alpha. So tan alpha is, it is from the G. So if it is from A, then this formula is used. So tan alpha will be the other vector omega square r sine lambda, it is this B, and then multiplied by sine of theta. Sine of theta. Theta is the angle between A and B. So theta is the angle between these two vectors, which is 90 degree plus lambda. So sine of 90 degrees plus lambda, and divided by the first vector, which is G, and then plus the second vector, which is omega square r sine lambda, and then cos of theta. So cos of 90 degrees plus lambda, this will be omega square r sine lambda, omega square r sine lambda cos lambda divided by, and then this quantity G minus omega square r and then sine square lambda. Okay, so let us work with numbers. How much is omega, how much is capital R, and so on. So how much will be alpha and how much will be this G effective. So let's have some feel of numbers. Right, so start with this omega. What is this omega? This omega is the angular speed of rotation of Earth about its axis, and you know how much it is. This will be 2 pi. Earth rotates by 2 pi radians in 24 hours. So 24 into 3600 radian per second, and if you work out, this turns out to be around 7.29 into 10 to the power minus 5 radian per second. So it's a small number. If I am using everything in SI, then this omega is 7.29 into 10 power minus 5. It is a small number, and omega square r, because wherever this omega is coming, it is coming in this combination omega square r, omega square r. Okay, so omega square r, omega square r. So this is 7.29 square and into 10 power minus 10 multiplied by r, capital R, this is the radius of the Earth. So 6400 kilometers into 10 power 3 meters. So this is it. So this quantity is something like 53.0 into 64, and then 5 here and into 10 power minus 5. So that is omega square r, and this turns out to be 0.034 what meter per second square. Okay, so this is omega square r. If you compare with G, this omega square r by G is this divided by 10. G is 10, around 10. So this will be 0.0034. So in 10 meter per second square, the correction is of the order. We'll just work it out why I am saying this. is of the order 0.034 meter per second square. So, in 100 it will be 0.34. So, it is 0.34%. If you compare omega square r and g, then this omega square r is about 0.34% of g. Now, let us first look at the direction. Let us first look at the direction. How much is our vertical deviated from the true vertical? So, this is here, omega square r, and then sin lambda, cos lambda, g minus this. You can divide by g in numerator and denominator, and you can write this as tan alpha is equal to, or we can write it here, we have space, divided by g. So, omega square r by g, and then sin lambda and cos lambda, and then whole thing divided by 1 minus omega square r by g, and then sin square lambda. Now, see what happens to this if I make lambda equal to 0. If I make lambda equal to 0 on the globe, where am I? If this lambda is 0, where am I? I am at the North Pole. Or if this lambda is pi, I am on the South Pole. Okay, so this will be sin lambda into cos lambda. If lambda is 0, this is 0, and therefore alpha is 0, tan alpha is 0, and alpha is 0, no deviation, no deviation. I should be like this, because if you are here, how much is this omega square capital R sin lambda, right? This sin lambda is 0, this whole number is 0, this whole vector is 0. This r sin lambda is in fact this radius. R sin lambda is this radius. This whole thing is capital R, and this is lambda, and it is this radius for which we had written this omega square, this capital R into sin lambda. And if you are here on the poles, this radius is 0. If you are here, then this radius is this much. If you are here, this radius is this much. At the pole, this radius is 0. So, you do not have that term, you only have this mg, and therefore the g effective is in this direction. The magnitude is also not changed because this vector is itself 0. So, at the poles you have no deviation in this vertical, and also the magnitude of g effective is same as g. What happens if I am, so lambda equal to 0, alpha is equal to 0, no deviation. What if lambda is equal to pi by 2, and here g effective is same as g value? If lambda is pi by 2, where you are? If lambda is pi by 2, you are somewhere on the equator, you are here. And everywhere on the equator, lambda is 90 degrees, right? When you define this lambda, all these points on the globe, you have same lambda, because from anywhere you draw this radius, it will be like a cone, and this will be the perpendicular cross section. So, lambda equal to pi by 2, you have cos lambda sitting here. Cos of pi by 2 is 0, and therefore this quantity is again 0, alpha is again 0. What is the significance? If you are on the equator, g, the real vertical is in this direction, passing through the center of the earth. This is the real g. So, if you are somewhere on the equator of the earth, then this small g is passing through the center of the earth, and this circle is now here, and therefore this direction is here. So, it is the same direction, omega square r into sin lambda, and sin lambda is 1. So, this whole radius of the earth is here, omega square times r here, and g here. They are on the same line in opposite directions, and therefore the resultant is also in the same line, and the resultant magnitude is g minus omega square r, and omega square r, you know how much it is this. So, g effective is g and minus omega square r. So, this is around 10, and this is 0.034 meter per second square. The effective g is slightly less than the actual g at the equator. Okay. So, magnitude wise, here it is g effective is equal to g, and here it is somewhat less than g. Whether it gradually decreases, or there are some maxima and minima in between, that we can see from this expression that we will do. But first lambda, first this alpha, the deviation angle. The deviation angle, if you see this sin lambda cos lambda, then since this 1 is here and this quantity is very small, omega square by r by g 0.0034 unit less, and therefore this whole quantity is very small, whatever is lambda. If lambda is pi by 2, this is 1, otherwise it changes, and therefore the denominator will not make much of difference as lambda varies, but this thing you can say sin lambda and cos lambda, and you can find at which lambda this is maximum. It is 0 at lambda equal to 0, it is 0 at lambda equal to pi by 2. So, in between at some place it will have a maximum value, and that will be 45 degrees, very close to 45 degrees, very close to because of this term, but this is very small. So, it will be quite close to 45 degrees, and therefore, at 45 degrees you have maximum alpha. So, our vertical and the true vertical, that deviation we are talking of. So, maximum alpha will be omega square r by g into sin 45 and then cos 45, which is 1 by root 2 into 1 by root 2. So, that will be omega square r by 2g, which is 0.0034 divided by 2, that is 0.0017, very small number, and this is tan alpha. Since it is very small number, alpha is almost same as tan alpha you can write, and therefore this is 0.0017 radian. So, how many degrees? 1 radian is 57 degrees roughly. 1 radian is 57 degrees, 3.14 radian is 180 degrees. From there you can calculate how much is 1 radian. So, it is around 57 degrees. So, multiplied by 57, and that number will be something like 0.1 degree. So, this is the maximum deviation, okay, 0.1 degree, 1/10 of a degree. So, that is the maximum deviation which occurs where you have lambda equal to 45, almost 45 degrees. So, it is not a great difference that we are not using the true vertical or so, but nevertheless whatever we are using, that we are using G effective, we are using the vertical, which is our vertical is along G effective and not along G, although the deviation is very small, maximum deviation is only 0.1 degree. And similarly the value of G, that also changes from pole to equator, and that also you can see from here. Here you have omega square r by g, which is a small quantity, remember this is 0.0034 square of that. Here it is that small quantity, and here it is square of that. So, this is not going to make any effect, any significant effect, and then as your lambda is increasing, gradually this quantity will increase and gradually this quantity will decrease. So, G effective will continuously decrease from G to this value G minus omega square r, and remember omega square r is only this is 0.34 meter per second square. So, it gradually decreases and it reaches here. So, we will stop here, and with this these numbers in mind, we will just take that as a vertical, that G effective as G in direction and magnitude, and then we will use our equations to find the path of the particle if I release it from here and it is dropped. I know what happens to the plumb line. I know what happens to my pendulum if I am not oscillating, that just stays in the direction of that our vertical, that G effective direction, okay. But if I drop it, whether it goes along that vertical, our vertical, or even with respect to our vertical, there are some deviations because of these pseudo forces that we will see in the next lecture. So, we discussed the frames that we attach generally on the surface of the earth, our laboratory or anywhere that we work, and the equations are mass times acceleration is equal to m into G effective. We talked in detail what is this G effective, and it depends on where you are on the globe, but the differences are quite small. The direction differs at the most 0.1 degrees at latitude 45 degrees, and the magnitudes at equator is some 0.034 or so. Okay, so and then any other force that you apply apart from this gravity, any other force that you apply, others, let me write others, and then you have the Coriolis forces. So these are the actual forces, then you have Coriolis force and centrifugal force m times omega cross r and minus 2m times omega cross v. This is basically, this is the equation, okay. And then since now this r vector is position vector of the particle from your own origin, so this is not going to be very large like 6,400 kilometers or so, it will be in meters, 2 meter, 5 meter, 10 meter, 20 meter, 30 meters, like that, and therefore this omega square term will be very, very small. You remember omega is 7.29 into 10 to the power minus 5. So omega square will be very small, and you don't have that capital R which was there some 6,400 kilometer, that made some change, okay. So we will totally neglect this, and this we will keep, first power of omega we will keep to see the effect of non-inertiality. So this is it, and the kind of axis that we choose is also very important, otherwise the equations may look weird. So what I prefer is that if I am here, this is the axis of rotation of the earth, ns, and it is like this, and this co-latitude is lambda, then this is vertical. This is vertical. Vertical means this g effective, the direction of this g effective, that is our vertical. All right, even if it does not go through the center, and you know the differences are extremely small, we can always neglect that. This is our vertical. So that vertical is taken as the z axis. I will take vertical as the z axis, vertically upward as the positive z direction. Then x and y are to be chosen. So this plane, this axis of rotation and this vertical, and in this plane if you draw this tangent here, this is north. At this place this is north. Wherever you are, you draw a tangent in this plane, and that gives you the north, and the opposite is south. So this opposite is south, this is south, and we will take this south direction as the x direction. All right, south direction as the x direction. So x axis I will always take towards south, and z is of course vertical. And then you can see, if you do this cross product of this z and this x, k cap this direction, I cap this direction, and k cap cross I cap should be j cap. So if I take a unit vector here, take a unit vector here. So now let us come to this table. Suppose I have origin on the table, and vertical is the z axis is this, and south, okay. So south is here in this room, south is here. So this is x axis, my left is x axis, vertical is z axis, and then I am doing k cap cross I cap. So when I do this k cap cross I cap, that direction is coming towards the board, and that is east. So y axis will be towards east. So here if you do, you will show is going perpendicular to this board, so you will show some dotted line, and that will be y axis, and that is towards east. So this is how we will take our axis system. This is how we will take our axis system. Z axis will be vertical, x axis will be towards south, this is x axis, this is south, and then y axis will be towards east. So wherever you put the origin, see where it's a vertical, see where it's south direction, see where is east direction, and then set up x, y, z accordingly. So this is the system that we will be using. Now in this system, what is this omega? Okay, what is this omega? Omega vector is here. This is omega vector. This is omega vector. So this is omega vector. This omega vector, if you draw from the origin, this is omega vector, and this omega vector can be written as what in this plane? This angle is lambda, so this angle is lambda here, and towards north if you extend this, this will be 90 minus lambda. So this omega vector is omega cos lambda in z direction, omega cos lambda in z direction, and then omega sine lambda in negative x direction. So it is minus omega sine lambda I cap, right. This north south and this vertical and this axis of rotation, they are in one plane, and therefore we can do this resolution of vector omega vector in the z direction and in this x direction. So it is omega cos lambda in the z direction, omega sine lambda with a negative sign in the x direction. So this is omega, and so and g is in a negative z direction, g effective is the value of G effective whatever and then minus of k cap. So, this is D, and then we have V, V will be Vx I cap plus Vy j cap. This is it. So, let us write this equation. Let me take up a specific example, and that will be free fall. Suppose I release a particle. From some height h above the ground, and I want to see the path of the particle, time taken to fall to the ground, and so on. So, a particle released from rest. So, what I have initially, suppose this is okay, this is the x axis, y axis, z axis, and the particle is released from here, and this height is h. So, at t equal to 0, x is equal to 0, y is equal to 0, and z is equal to h. So, it is released from here, and the velocities are 0. Vx is equal to Vy equal to Vz equal to 0. This is the condition. And now I want to see what will be the path of this particle, how much time it will take, and all those things. So, how do I write equation? Mass times acceleration. Mass times acceleration is equal to m into g effective. So, m into g, let me write g because I will not be using both together, g and g effective. So, it is g effective, alright. So, m times g in a negative k direction, so minus here and k cap here, and then no other forces are there, it is free fall. So, this term is not there, this is minus 2m, then omega vector is omega cos lambda k cap and minus omega sin lambda and I cap, this is it, cross V is plus Vz k cap. So, V is Vx I cap plus Vy j cap plus Vz k cap. Let us do this cross product. So, this is m you can cancel from everywhere. So, A is equal to this, A is equal to minus g k cap, and then this minus, now this cross this. So, start from here, omega cos lambda k cap, and here it is Vx. So, Vx and k cap cross I cap is j cap. So, this much j cap, right, I j k, k cross I is j. So, k cross I is j, then this term plus omega cos lambda into Vy, omega cos lambda into Vy, k cross k cap cross j cap, k cap cross j cap will be minus I cap. So, this is minus I cap here, and then k cap cross k cap is 0. So, this is done. Now, come here, this one, minus omega sin lambda, and then I cap cross I cap is 0. So, come here, minus omega sin lambda, and then Vy, and I cap cross j cap, which will be k cap. So, this is k cap, and then this one minus omega sin lambda and Vz, and I cap cross k cap, is minus j cap. So, this becomes plus here, and this becomes j cap here. Okay. Now, write the x component, y component, z component. Ax, x component of the acceleration, Ax is equal to, so search for I cap, here it is minus omega cos lambda, then Vy. Okay, so minus omega cos lambda Vy, that is here, and no I cap here, so this is Ax. Then Ay, I have k cap, then k cap cross j cap is I cap, and then that's it, right. Then you have Ay. So, Ay is equal to, search for j cap, where is j cap? Here is j cap. So, minus I omega, Ax is equal to minus I omega, but I also have a minus here, so it is plus. Ay. So minus omega cos lambda Vx, minus omega cos lambda Vx, j cap, I am looking for j cap, here is j cap and then here is j cap, minus omega sine lambda, minus omega sine lambda, that is j cap, and k cap, k cap is minus g. So Az is equal to minus g, and then k cap I have to search minus here and minus here plus omega sine lambda and then Vy, that's it. So this is it. So let's compare once again. Here is acceleration, here is acceleration, and I am writing the three components, x component, y component and z component. This two is here, this 2 is here, and the 2 will be there. So everywhere this will be 2 here, this will be 2 here, so maybe I can put minus and 2 common, and then this, and where is the velocity, where is the velocity, ay, y component is v omega cos lambda Vx is there, and then y component is here omega sine lambda and Vz, so this Vz is there. All right, so 2 here, that's it. Y component is minus 2 omega cos lambda Vx there, then the y component is minus 2 omega sine lambda Vz is there, z component is minus g from here and then from here, so minus plus 2 omega sine lambda Vy, that's it, right. So these are the equations to be solved with this initial condition. Okay. So how do we go about it? Start with first integration. First integration, of course, you can do this ax, if when you integrate this dt and then integration, ax will give you Vx equal to, what is Vx? Vx is integration ax dt, dvx dt, ax is dvx dt, and therefore this is, so Vx, and this side is 2 omega cos lambda, that is constant, and Vy similarly when you integrate it gives you y, it gives you y, Vy when you integrate it gives you y plus some constant, and that constant you should get the value from the initial conditions. At t equal to 0, y is 0 and Vx is also 0, so y is 0 and Vx is also 0, that tells me that the c is 0, so I can remove this. Similarly Vy, here Vy is equal to, I am integrating, minus 2 omega cos lambda, that is constant, and Vx when you integrate you get x, and plus omega sine lambda, and Vz when you integrate you get z. So up to this point it is very simple. Then here it is, so this was ay, and from az you can get Vz is equal to minus gt and plus 2 omega sine lambda, and Vy dt will give you y, of course plus constant and plus constant here. We will just see what these constants are. First this constant, at t equal to 0, x is 0, z is h, and Vy is 0. So it gives me, this equation gives me 0 equal to, Vy is 0, minus 2 here, x is equal to 0, omega here, sine lambda here, and this z is h plus c. So c is equal to minus 2 omega sine lambda plus 2 omega sine lambda into h. So that is c, that you have to write here, plus 2 omega and sine lambda and then h. So this is that constant. Okay. So 2 omega sine lambda you can take common from these two terms, and what you can write here is this term and this term together. This you can write h minus z, 2 sine lambda h and minus z. So you can combine this and write 2 omega sine lambda and h minus z. So these two terms can be written as this, that is c. In this equation what is c? At t equal to 0, y equal to 0 and Vz is also equal to 0, so this c is 0, this c is 0. So these are the equations, these are the three equations. Let me write it more cleanly. Vx is equal to 2 omega cos lambda times y, this one. Then you have Vy, Vy is equal to minus 2 omega cos lambda minus 2 omega I can take common, minus 2 omega, then cos lambda times x, and then here it is minus or plus or minus z, h minus z here, and sine lambda here. Okay, what we have done for Vy, minus 2 omega I am taking global common, so it is cos lambda times x from here, and these two terms, if I take minus 2 omega common, then from here minus 2 omega when I am taking common, sine lambda into these two I am combining, this was this plus this was 2 omega h minus z, minus 2 omega I have taken, so sine lambda here and h minus z with negative sign here. So this is Vy, and Vz is equal to minus gt and plus 2 omega sine lambda times y. So up to here we can go. I know the velocities if I know the position x, y, x and y if I know, then z also I need, x, y, z if I know, time if I know, then I can write velocity. Is not a great thing to achieve. Okay, we have to go further and write x, y, z as a function of time, but then now if I want to integrate this, the y is here, I cannot integrate, or if I integrate this Vy, then x is there, I cannot integrate, z is there, I cannot integrate, so we have to do some approximations. So let me make some space. So now remember, we had neglected omega square term and retained omega term. So our results that we are driving are up to the order of omega, and anything which contains omega square, that we will neglect, because omega, remember, 7.29 into 10 to the power minus 5. Now if I see this equation Vz, it is minus gt plus 2 omega sine lambda into y. Now if there was no rotation, there was no question of any y, because when I drop, there is no force in y direction, initial velocity in y direction is 0, there is no acceleration in y direction, and therefore it does not go in y direction or in x direction, it just goes in negative z direction. If at all there is some y and if at all there is some x, that is only because of the presence of omega, and therefore this y and x, if at all they are there, they will be in the, they will contain that omega there. They cannot be without omega, because it is only because of omega. When you put omega equal to 0, that term should go away. If you put omega equal to 0, that term should go away, because then it will just fall vertically. So this y will have omega in it, and therefore this term will be of omega square type. One omega is here and one omega is coming from here, so this term will be of omega square order, and therefore we will neglect it. Okay, consistently from the very beginning we are neglecting omega square term and retaining omega term, and therefore let us rewrite Vz. What is Vz? Vz is just minus gt, and therefore z is equal to h and minus okay, this is minus half gt square, our usual equation, because if I am neglecting this, it is just simple fall. Vz is equal to minus gt, and if I calculate how much is z, remember we are dropping it from here, and this is z is equal to 0 and this is z is equal to h, so it moves a distance half gt square, and therefore z is equal to h minus half gt square. So this is there. Now let us look at this term here. It is h minus z, and h minus z is half gt square. This is that h minus z, half gt square. So look at this equation Vy. Vy is equal to minus 2 omega and x. Once again, x is in the direction of south. So if you are dropping, it should just go vertically. There should be no horizontal deflection, because there is no force in the horizontal direction, but because of omega, because of this Coriolis force, you can get something, but then it should be of the order omega. So this contains omega, here is omega, so we will neglect this term because it will be of omega square type, and then come here. So it is plus 2 times, so plus 2 times h minus z, which is half gt square, and times sine lambda, This is Vy. and if this is Vy, now I can integrate to get y. So y is equal to gt cube by 3 and then sine lambda. This is y. So there is a deflection in east direction. Y, remember y axis was taken towards east. So if you drop it, it doesn't go in the direction shown by my plumb line. My plumb line is showing that z direction. The z direction is taken along the vertical, our vertical. Okay. So if I just take a plumb line, just suspend a pendulum at rest with respect to me, that thread is vertical. And if I drop a particle from here, it will not go in that direction, it will be deflected towards east according to this equation. And more time it spends in air, or we are of course neglecting air resistance, etc. So more time it spends in air before reaching the ground, more is the deflection towards east. What happens to x? What happens to x? Vx is equal to 2 omega cos lambda times y. Once again, this y is coming only because of omega. Where is my omega? Where is my omega? Where is my omega? This omega I have not written here. This omega, 2 omega. Okay, Vy is 2 omega. This is 2 omega. So 2 omega times h minus z. So 2 omega times h minus z, and that 2 omega is here, and h minus z is half gt square. So this is omega, of course. This is omega. So y contains omega. Y is because of omega only. The deflection towards east is because of omega only, so omega has to be there, and therefore this contains omega. Here is omega. So any x deflection is of the order of omega square, and we neglect that, and therefore the deflection, the actual deflection will be in the east direction. How much? How much? Typically how much? So we can put some numbers. This you can write in terms of height also, because we know this equation, and therefore when your z is 0, when z is 0, when does it reach here? When does it reach here? When this z becomes 0. So 0 is equal to h minus half gt square, and therefore t is equal to 2h by g square root of that. So if you write this in terms of h, so in place of this t you will be writing this. So you have y is equal to omega g by 3 sine lambda, and then t cube, that means the square root of 2h by g cube. That is it. Or omega here by 3 here, sine lambda here, and then square root, this is 2h cube here, and then this is g cube here, 1 g cancels with this, and it will be g here. So this is your y, this is your deflection. If you drop a ball from height h and it falls on ground, it will also be deflected towards east with this much of amount. So let's try to put some numbers here. Okay, so let us take lambda is equal to 90 degrees. Where are we? Lambda equal to 90 degrees. Where are we? We are on the equator. So if we are doing the experiment on equator, then the sine lambda is 1, otherwise you will multiply by sine lambda. Omega by 3. Omega is 7.29 10 power minus 5, everything in SI units, by 3, and then square root of how much h I should take? Let us take 20 meters. Let us take 20 meters. So we have dropped our ball from 20 meters of height, and we neglect all that air resistance which is there in this 20 meters. So this is 40 cube. So 40 into 40 and into 40, and divided by g, which is 10. Okay, so it is 7.29 into 10 power minus 5 divided by 3 into 4 into 4 into 4. So 16 and then 64 and 00, 64 00, so 80 meters. If I write in millimeters, it will be 7.29 into 10 to the power minus 2 by 3 and 80 millimeters. So that will be 7.29 into 0.8, okay, and divided by 3. How much is this? How much is this? So 2 here, 4 here, 3 here, and into 0.8 millimeters. Millimeters. 4 here, 34, 4 here, 3, something like this. So something like 1.9 or 2 millimeter, okay, let us say 2 millimeter. So, that is the order, that is the order. If you drop something from 20 meters and it falls through those 20 meters, there will be 2 millimeter deflection towards east when it reaches ground. So, that is the kind of effect. So, for our normal daily life routine is extremely small, we can neglect, but for like say missiles going to hundreds of kilometers, we have not done projectile. Similarly, in a similar way you can do projectiles, project it, and the Coriolis force that show some sizable effect there. If you are targeting some ship, perhaps that ship will not be sunk because of your missile, because your thing is deflected because of this Coriolis force. Okay, so we will stop here and you do an exercise, throw the particle from z equal to 0 upwards, so that it reaches a height h, the same height h, and see that if I am throwing it vertically upward from z equal to 0 and it reaches a maximum height of h, how much is the sideways deflection, and whether it is towards east or towards west or south or north or any other direction in horizontal plane. So, that you in a very similar fashion, in a very simple way, we have done everything, only you have to rightly put the symbols and the signs and get how much is the deflection as it reaches the highest point and in which direction. So, we will stop our non-inertial frame discussion here, and from next lecture it will be rotational dynamics, rigid body dynamics. So, today we are starting rigid body dynamics, and you have done some rigid body dynamics in schools, and especially with a fixed axis of rotation. A rigid body, as you know, is rigid. Ideally we assume that it is rigid, although nothing is rigid in this world, but then the definition would be that separation between any two particles is fixed in that body. Now, a general motion of this body is a translation and a rotation. For example, if I have this piece of pen here, and if it goes from here to here, then it has been displaced, its center of mass has gone from here to here, that is translation, and then on top of that there is a rotation because it was in this orientation and here it is in some other orientation. So, this is rotation. So, this is rotation with one point fixed, whereas this is translation as if everything is translating. So, if you have any rigid body, and you can start with the center of mass here, and then let me draw, say it is like this, and then when it goes here, center of mass reaches here, and this whole thing gets rotated. So, it is of this type, copy it and rotate. Okay. So, it has rotated as well as it has translated. So, consider any point, any particular point of this, let us say this point, and this point reaches here. So, velocity of this point at any time can be written as velocity of the center of mass and plus some omega times position vector of this particle with respect to that center of mass frame. So, you fix up a frame with a center of mass at the origin, and in that frame this is rotating, it is a pure rotation, and pure rotation can be described by this, because if you have an axis here and then a pure rotation, every particle goes in a circle, and you can work out that if this is omega, rotation axis, and then you take origin here or anywhere, and then you can see that this r vector and this omega vector, the cross product is v. How can we see it there? Omega cross r, this will be omega is omega in z direction, suppose this is z direction, and we will use cylindrical coordinates. So, r, this r vector is, this is let us say z, so z in k cap direction, and plus this one is s in s cap direction. So, and this when you do k cross k cap is 0, and you have omega into s, and then it is phi cap, and this is s, and therefore this omega times s the velocity and phi cap is the direction. So, it correctly gives direction as well as the magnitude. So, this gives you the translation part, this gives you the rotation part about the center of mass. Now, very interestingly, if you do not use center of mass and fix up some other point, say some other point here, let us say some say x, this point is named as x, you can still write velocity of this arbitrary point A, velocity of A at any instant, remember going here to here is a lot of variations. So at any instant what I am doing is I am writing the velocity of this particle at some instant, and that will be equal to velocity of this point x and plus omega cross and then the position vector of this particle A with respect to that x. So it's not necessary to have the center of mass. You can have you can choose any point you like. You can choose any point of you like, and the translation can be seen with respect to that point going from one place to other place. The whole rigid body is going like that, and then the rotation about that chosen point x. So you can write this kind of relation not only for center of mass but for any point fixed in the body. And the most interesting part is that this omega and this omega are same. Omega is same irrespective of the choice of x. You take any point and then you write the velocity of a particle, any arbitrary particle of the rigid body, as velocity of that chosen point plus omega cross position vector of the particle from that chosen point, and this omega remains the same. So it is independent of choice of this. It can be proved, but I am not going to do that, but this is very, very interesting result. In this chapter we will be focusing only on this part, not on this part, or this part, not on this part. So we will have one point fixed about which the rotation will take place, and then we will do the dynamics of it. Now as in translational motion, the central equation is F is equal to ma, which you write more appropriately dp dt, where p is the linear momentum. Now for a rotation of a rigid body, the central equation will be torque is equal to dl dt. Here it was force is equal to dp dt, here torque is equal to dl dt. And what is torque? Torque will be summation over I mi ri vector cross fi external. This is our torque. You can write it external torque. Okay, and remember the linear momentum and the torque both are defined about a point which we can choose. We have done it during the central motion discussions, that this torque has to be r cross f. Now from where this r is taken? Our own chosen origin, and depending on where I choose the origin, this torque may be different. That is not the case with f. Okay, f. Similarly, the angular momentum. The angular momentum L is summation over I mi ri cross vi or ri cross pi. This also depends on the choice of the origin. That is not the case here. Linear momentum of a particle does not depend on the choice of the origin, but angular momentum, yes. So be very careful. The angular momentum has to be calculated about that point, and the torque has to be calculated about that same point, and then torque is dl dt. And this gives me the law of conservation of angular momentum. If external torque is 0, total external torque on the body is 0, then its angular momentum is constant, does not change with time. That is it. And you can show this because when you write L is summation over I, here it is mi and then ri cross vi, or you can write pi here, no problem. And if I differentiate it with respect to time, this will be equal to summation over I mi and then ri cross differentiation of this will be acceleration of ith particle, and then plus differentiate this, that will be vi and cross vi. Alright, so we are differentiating this expression summation over I mi, and now we have to differentiate this. So keep this ri as such and differentiate this vi, and you get ai, and then you keep this vi as such and differentiate this ri position vector, that gives me again vi. So this part is 0. So what I am left with is summation over I m, or let me write ri here and cross mass times acceleration, which is force on the ith particle. Okay, but that does not prove this relation that dl dt is torque external. This is external torque I have written. That means the torque by the forces by objects outside that rigid body, not part of the rigid body. So that is what I am calling external. So if you have a rigid body and then you have a particle here, there are various forces on this. Some are applied from outside and others are applied by these other particles. So this particle is maybe attracting, this particle is maybe attracting, this particle is attracting, this particle is attracting. So these are the internal forces on this particle. Okay, so our conservation law will be if torque external is 0, then L is constant. This Fi is the resultant force because I am writing it for Mi and Ai, Mi and Ai. So this is the resultant force on the ith particle. So this is Ri cross Fi external and then plus Fi internal. And this is summation over I, mass is LT here. So Ri cross Fi external, this is one part. This is the external torque. This is that external torque that I am writing here. But then there is another term, summation over I, Ri and cross Fi internal. Now it is true that if you add all these internal forces on ith particle, you may get some non-zero value. But then when you sum over this I and take this particle also into consideration, this particle also into consideration in this sum, then suppose this particle, now this particle is also attracting it by that same force. This is attracting here and this is attracting here, and that sum will be 0. So total summation on Fi internal over all the particles will be 0. That is fine. That is Newton's third law. These two particles are attracting or repelling or doing whatever, and the magnitudes are same, the directions are opposite. So if you divide this whole sum as pairwise, this pair, that pair, that pair, that pair, that pair, that pair, then the total will be 0. But that does not tell me that this is 0. If this sum is 0, that does not mean necessarily that this sum is 0, because every time you are making a cross product and then adding, right? But this happens to be 0 because if I look for this term, summation over I Ri cross Fi internal, what is this? This is force on the ith particle by all other particles of the rigid body. And so this itself is summation over j, which is not equal to I, and then Fij. Okay, what is this Fij? Is the force on the ith particle by the jth particle, and then we go for all the values of j, first, second, third, fourth, nth particle except this I, because I have to consider forces by the other particles. That is why this j is not equal to I. All other j I have to consider, and then this total, this quantity is this quantity. So this you can write here, this j can be taken here, summation over j. So I have to sum over j and sum over I, j going from 1 to capital N, I going from 1 to capital N, but make sure that you do not put j equal to I, and here it is Ri and then cross Fij. Now this quantity, now consider one particular pair I and j, ith particle and jth particle. This particular pair, ith particle and jth particle. Okay, so I put some value here and some. Let's be more specific. Suppose I am talking of second particle and fifth particle. Okay, so somewhere in this whole sum I will get j equal to 2 and I equal to 5, and somewhere in this I will get j equal to 5 and I equal to 2. So these kind of two terms, j equal to 2, I equal to 5, there is something. J equal to 5, I equal to 2, there is something. These two I am clubbing together. What will happen? This will be Ri and cross Fij and plus Rj and cross Fji. This is a kind of pair. So the same I and j are interchanged. So the whole sum can be written in terms of such pairs, and this pair is Ri cross Fij and minus Rj and cross Fij. Here I have used Here I have used third law, Newton's third law. What? Fji is equal to minus Fij. The force by the ith particle on the jth particle has the same magnitude as the force by this jth particle on the ith particle, but with a negative sign, opposite in direction. So that is Newton's third law I have used. Now this is equal to Ri minus Rj and then cross Fij. Okay, Ri vector minus Rj vector and cross this Fij is taken common. Now if this force on the ith particle by the jth particle is along the direction joining the two particles, another restriction. So I have a particle here, I have a particle here, and they are exerting forces on each other. They are equal in magnitude, they are opposite in direction. Somewhere origin is here. This is my Ri vector, this is my Rj vector, and then what is this vector? This vector is Rj minus Ri, or this vector is Ri minus Rj. If the force is along this direction, if the force is along the line joining the two particles, then this vector and this vector are parallel. If this force on the ith particle by the jth particle is along the direction joining ith particle and jth particle, then this and this will be parallel, and then this will be 0. And then I will be sure that this whole thing will be 0. So this is equal to 0 with the condition that the forces by particles on each other are equal in magnitude, opposite in direction, and act along the line joining the two particles. This is sometimes called strong form of Newton's third law. So that this form of Newton's third law is needed for this being 0. If this is 0, then it's fine. This whole thing is now torque external, and then you get dl dt is equal to torque external. Dl dt is equal to torque external. If the total torque by the external force is applied on the rigid body is 0, then the angular momentum is conserved. So this is important theorem, or this relation itself is very important. This is the central equation of this whole rigid body dynamics, and therefore let's see what is the relation between this L vector, the angular momentum vector, and this omega vector, because this omega describes the rotation of this rigid body at that instant itself. Okay, so let me make some space. So angular momentum vector L, I am talking now of some rigid body, there is some origin somewhere, okay, and then I am talking of some particle, ith particle, and this is position vector Ri, and then this particle at this instant had some velocity Vi, right. So angular momentum will be summation over I Mi Ri cross Vi, and Vi is omega cross Ri. Okay, velocity is omega cross r. We are talking of that rotation part only. So any general motion can be decomposed in two parts, translation and rotation, and rotation will have the same omega. Translation velocity will depend on which point you have chosen for that reference. So this is it. Now you must be knowing this, that A cross B cross C is equal to A dot C and then B vector, and then minus A dot B and here C vector. This you can work out standard result. Any three vectors you take, and in this fashion you do the cross products, and then this is equal to this. This we will be using for this part. So L is equal to summation over I Mi, then this has to go out, so this dot this Ri dot Ri and the omega here, and then minus, now this has to go out, so Ri and dot this omega, and then this Ri here. This is it. This is equal to summation over I Mi, and this is Ri square, and what is Ri? Is the distance of the particle from the origin, this, and then omega. So this is omega, and okay fine, omega, and here it is xi omega x plus yi omega y plus zi omega z. I am not taking the z axis along that omega. So omega will have components in x, y, z direction. So I am writing this Ri as xi I cap plus yi j cap plus zi k cap. So those xi, yi, zi are here, and omega I am writing as omega x I cap plus omega y j cap plus omega z k cap, and then taking the dot product, it is this, and then it is Ri. Let us see what is Lx, x component of this angular momentum vector. So x component, here is vector and here is vector, and I am taking x component, summation over I mi Ri square, and then omega x, I am only taking the x component, so omega x minus xi omega x, yi omega y. These are all scalar quantities, they are not going to change. The component only comes from here, x component, so that is xi, is equal to summation over I mi. Let us take that omega x part. Omega x is coming from here, so that is Ri square. Then omega x is coming from here, so minus xi into xi, and then omega x, so minus xi square and into omega x. So this is that omega x part I have taken, plus omega y. Where is omega y? Here is omega y, the only place. So it is minus yi and xi, minus yi and xi. Okay, just multiplication here. So I have taken omega y part, and the only term left is this, which is minus, and then zi, omega z I will be writing outside, so xi and this omega z, so minus omega z. That's it. All right. So Lx is equal to, so this is equal to summation over I mi, and then this is yi square plus zi square. This is one part into omega x, then plus omega y part. So summation over I minus mi minus I have written, and then yi xi. So let me write xi yi and then omega y, and plus summation over I, that other part, summation over I minus, so let me write it bracket here and minus here. All right, so it is mi, and then it is xi zi, so xi times zi, and that is omega z, that is omega z here. So that is Lx. So Lx will involve omega x, omega y and omega z. So for symbol I am writing this as, let us write this as Ixx, okay, omega x, plus let us write this as Ixy and omega y, plus this is Ixz and then omega z, where I am writing Ixx for summation over I mi yi square and plus zi square. And what is this quantity? This is essentially perpendicular distance square from the x axis. So if you take the usual moment of inertia of class 11 about the x axis, you will take mass of the particle into distance from the x axis square. So that is this part. So this is essentially your commonly known as moment of inertia about a line about the x axis. But what is this Ixy? This Ixy is something very different. This Ixy is minus summation I mi xi and yi, and Ixz is similarly minus I here mi and then xi and zi, right. So these are the three symbols, and then Lx is equal to Ixx omega x plus Ixy omega y plus Ixz omega z, and you can similarly work out the y component of L and z component of L. And what you find is that Ly is equal to, let me write that again, Lx is equal to Ixx omega x plus Ixy omega y plus Ixz omega z. Similarly, you will get Ly is equal to Iyx omega x plus Iyy omega y plus Yz and then omega z, and Lz you will get Izx omega x plus I zy omega y and plus I z z omega z, and the new symbols that I have written iyx, iyy etc. are the following: iyy will be summation over I m and then zi square plus xi square. Izz will be summation over I mi xi square plus yi square, and then iyx will be same as ixy and iyz will be same as izy. So everything goes over 1, 2, 3, 4 new symbols. Iyx I have written, iyy I have written, iyz I have written, and then okay, that was not written here. Okay, fine. So this is equal to minus summation I mi and then yi and zi. So this is written zx is equal to xz, zx is equal to ixz, and that will be minus summation I and mi and zi xi. So I have written everything. Izz I have written, Izy I have written, Izx I have written, Iyz I have written, Iyy I have written, Iyx I have written. So this is the relation between angular momentum components and this omega components. So remember, L is not necessarily in the direction of omega. Axis of rotation, angular momentum is necessarily in the direction of axis of rotation. This is wrong, it is not. Here is the relation, and in this relation you can write this relation in a matrix form. It is, you will write it as Lx, Ly, Lz, this column matrix, equal to Ixx, Ixy, Ixz and so on, Iyx here, Iyy here, Iyz here, Izx here, Izy here and Izz here, and then this side it is omega x, omega y and omega z. So this whole column matrix which gives you the three components of angular momentum vector, and here you have this column matrix giving the components of angular this omega angular velocity vector. The relation between this and this is like this. It's not L is equal to some constant times omega, right? It is this. This we write as L equal to, this whole thing is called moment of inertia tensor. Moment of inertia tensor. This is moment of inertia of the object, of the body, of the rigid body, about the origin, not about a line, about the origin. Okay, so moment of inertia about the point, about the origin is needed to get the relation between angular momentum and this angular velocity. This quantity, if you wish, not a very standard symbol, but people sometimes use this with a double arrow, saying that this is not a scalar quantity, it's not a vector quantity as such, it's a tensor of rank 2. It needs 9 components, 3 to the power 2 components, and it's known as tensor of rank 2. That is this moment of inertia, and then this is omega. So this is this relation you should know very well, that if you want the relation between omega and L, because omega is given to you, and then you have to connect this angular momentum with that omega and then torque with that angular momentum. That's the chain, and therefore this relation one must know that this L is related to omega in this particular fashion. So we had seen the relation between angular momentum of a rigid body about some point and the angular velocity of the rigid body if it is rotating about some axis. So and the relation was L is equal to I omega, but then this was a vector, this was a vector, and this was a tensor of rank 2. We call it tensor of rank 2. It has 9 components. It has 9 components with respect to some xyz axis chosen. This is a vector, this is a vector, and this multiplication here is like a matrix multiplication. We had this moment of inertia tensor, which is Ixx, Ixy, Ixz, Iyx, Iyy, and Iyz, and then you have Izx and Izy and Izz, with Ixx equal to summation over I mi yi square plus zi square, and similarly Iyy summation over I mi and then xi square plus zi square, Izz as summation over I mi xi square plus yi square. These moment of inertia are like moment of inertia as we studied in class 11, about x axis, about y axis, and about z axis. But then there are other terms which are known as products of inertia, Ixy, which is same as Iyx, and that is minus summation I mi and then xi yi. Take ith particle, see what is the x coordinate of that ith particle, see what is the y coordinate of that particle, see what is the mass of that particle, multiply. Do it for all the particles of that rigid body and add. That is this Ixy, which is same as Iyx, in the same spirit Iyz, which is same as Izy, and that will be minus summation I mi and yizi, and the last one is Izx, which is same as Ixz, and this will be minus summation I mi and zixi. These are called products of inertia. And this L vector is here Lx, Ly, Lz, this column, and here it is omega x, omega y, and omega z. And the meaning is that Lx is equal to matrix multiplication, this into this plus this into this plus this into this, that is Ixx omega x plus Ixy omega y and plus Ixz omega z. So Ixz omega z, and similarly Ly and Lx. Ly will be this will be Iyx omega x. So Iyx omega x plus this Iyy omega y. So Iyy omega y plus this Iyz omega z, and Lz will be this row. So Izx and omega x plus Izy omega y and plus Izz omega z. And in general, L is not parallel to omega. The angular momentum and angular velocity are not parallel in general. So let us take an example. And example is that I have a rectangular plate, say uniform rectangular plate, this plate, and then this is the origin. And let us say it rotates about this axis, and therefore this is omega vector. Omega vector is in this direction. So this whole thing is rotating about this line, and length is L here, width is B, the total mass of this is capital M, and here is the origin, and I take this as the x axis, this as the y axis, and then z axis is perpendicular to the plane. So what is the kind of situation? I have let's say this is that rectangular plate, and here is a corner, and I am taking x axis. So here is x axis, I am taking y axis in the plane of this plate. So in the plane of this plate, this is x axis and this is y axis, other edge, and z axis is perpendicular to this plane. So z axis is here, z axis is perpendicular, this is z axis, x axis, y axis, and z axis, origin. So this is the kind of thing, and it rotates about y axis. That means it rotates like this, with a uniform angular velocity omega. Okay, so that's the kind of situation, and what we need is angular momentum of this rigid body, and for that what I need this moment of inertia, this 3 by 3, 9 components, and then omega we will write, L we will write, and we'll calculate that. So let us first calculate moment of inertia. This is O, moment of inertia about O, about the origin. Now we are not saying about an axis, not about a line, it's about a point. And of course, to get those 9 components, we need some x, y, z axis. So here is x axis and y axis and z axis. So let's calculate. Ixx. What is Ixx? What is Ixx? x-axis, moment of inertia, usual moment of inertia about the x-axis. So here is the x-axis and here is the plate, and you know what it is, it will be m times b square by 3, correct. If you have a rod of length b and you need it about this line, it is mb square by 3, and same is the formula if you extend it around the axis. So this is mb square by 3, and similarly Iyy, which is moment of inertia about y-axis. Here is y-axis. So if this is a rod, it will be ml square by 3, and if you extend it this way, it remains ml square by 3. And Izz, you can use theorem of perpendicular axis, it is b square plus l square. Okay, so that is very simple, that you have done several times in your schools. Now comes the other factors, Ixy. What is Ixy? Here Ixy equal to y, Iyx equal to minus I mixi yi. So we define Ixy as minus summation over I mi xi yi, and for continuous bodies you don't have particles, separate particles, so you cannot do this summation. This is integration dm x into y. So you take an element here, some dx dy, small element, see what is the mass here, what is the x coordinate, what is the y coordinate, multiply. So mass here is dm, x coordinate is x, y coordinate is y, so multiply. And then this is x into y, x into y. What is dm? Dm is capital M divided by AB into dx dy. Right? This is dxy, this is dx, and this is dy, and this area is dx into dy. Total mass is m, total area is b into l, so this is m divided by b into l. So this is mass per unit area, and then area here is dx dy, so it is this. And what are the limits? Let me separate. So m by lb is constant, then you have x dx and y dy. X will go from 0 to L, so x will go from 0 to L. You have to take this element here, everywhere, and then add. And y will go from 0 to b, so y will go from 0 to b. Our integration is fairly simple. It is m divided by L into b, L square by 2, b square by 2. So m into LB and divided by 4. That is Ixy, as same as Iyx. Okay, this is same as Iyx. And what is Iyz? In Iyz, you will have mi, yi, zi, and zi is 0 for all particles. Z coordinate is 0. Okay, this whole thing is in xy plane. So this z is 0 for every particle of this plate, and so this is 0. Z is 0 for every particle of this plate, and therefore this is also 0. So the only product of inertia terms are Ixy and Iyx. So let me write the moment of inertia tensor. So that moment of inertia tensor is Ixx. Ixx is here, mb square by 3. Iyy I have to write here, ml square by 3, and Izz I have to write here, so m by 3 and then L square plus b square. Then Ixy, this Ixy, and Ixy is negative, yeah, negative. So minus mlb by 4 minus mlb by 4, and all others are 0. This is 0 here, this is 0 here, this is 0 here, and this is 0 here. This is the moment of inertia of this plate about this origin. These are the components of moment of inertia along or with respect to these directions x, y, and z. But remember, a vector has 3 components, but components can change if you rotate the axis. If you change the axis, if you are using some x, y, z axis, and then you rotate the whole axis system just by some angle alpha, say some angle alpha, z, or about any line, you rotate and say this is x prime, this is y prime. You write the component of the vector along or in the directions of this x prime, y prime, z prime, the components will be different. If you are using x, y, z axis, there are some components of a given vector. If you are using x prime, y prime, z prime, the components will be different, but vector is not different, it is the same vector, it is vector. Is the physical quantity. Similarly here, I have chosen one particular axis system x, y, z. Of course, I need moment of inertia about the origin, about this given point, this I cannot change, but I could have taken some other axis, the x prime here, y prime here, and z prime. Then these components will be different. but that does not mean that the moment of inertia of the plate is different. Moment of inertia of the plate about O is a physical quantity, and that physical quantity is expressed in components once you have chosen xyz axis. If you choose different xyz axis, the components could be different, but moment of inertia as a physical quantity will remain same. In fact, tensors and vectors, these are defined in terms of this transformation. If you rotate the axis by a certain angle, the relation between new components and the old components of the same physical quantity, there is a certain rule according to which these components and those components will be related, and if those transformation equations are obeyed, then only we say that this is a tensor of rank 2 or this is a vector which is also called tensor of rank 1. And as a matter of fact, scalar is also a tensor of rank 0. So you have tensor of rank 0 which is scalar, tensor of rank 1 which is vector, tensor of rank 2 which is like this, then tensor of rank 3, 4, 5, no special names are given. So that is it. So this is our moment of inertia tensor components, and we are interested in the angular momentum. So what is omega? Omega is along the y axis. So omega, this is our moment of inertia. So omega we will write omega x, omega y, omega z. X component of omega is 0, y component of omega is omega, and z component is 0. So this is our omega, angular momentum vector. This is moment of inertia tensor, and when you do this multiplication, matrix multiplication, what you get is your angular momentum vector, Lx, Ly, Lz. So what is Lx? Lx is equal to this into this 0, this into this, so minus mLb by 4 and then omega, and this is plus 0 into 0 is 0, so this much I cap. This is Lx, fine, this is Lx. And then Ly is, what is Ly? What is Ly? Ly is this row, Ly is here, therefore this row and this column. So this into this 0, this into this, yes, mL square by 3 omega, then this into this is 0. And what is Lz? This is Lx, this is Lx, this is Ly, and Lz is 0 into 0, 0 into omega, and this quantity into 0 is all 0. So this is 0, this is Lz. So that means L is minus mLb omega by 4 I cap plus mL square omega by 3 and this much omega, that is j cap. Okay, this is it. So this is L vector. Omega was omega j cap. You can see that L is not parallel to omega. L is not parallel to omega. L is not parallel to omega. Let us take another example. The same story, the same system, the same plate, but this time let us rotate it about the z axis. So that means if this is the plate and if this is x axis, this is y axis and this is z axis, it is rotated about this z axis. So it will rotate like this with some uniform omega. Okay, so this is z axis and it will rotate like this. Previously we had this as the axis of rotation, y axis, and it was rotating like this. So only change we are doing, same origin, but now the omega is along the z axis, so its plate is going like this. So let's do for that. So let me make some space. I think I can make the space this side. So let me have the same figure, and omega is not here. Omega is now about along the z axis. So this is z axis and omega is in this direction, it's going like this. I want angular momentum of the object about this point, and I'll use the same procedure. Now moment of inertia of this plate about this origin is a fixed quantity. Wherever is omega vector, that doesn't matter, right? Moment of inertia of this is given by all those ixx, ixy, ixz, and in that omega doesn't come. Omega comes later. Moment of inertia, as long as that point is fixed about O, is the same moment of inertia, and therefore the same moment of inertia will be there. In fact, I can work there itself. Or let me write. It's the same moment of inertia. It is mb square by 3 and then minus mbl by 4 and then 0 here, minus mlb by 4 here, ml square by 3 here, 0 here, then 0 here and 0 here, and ml square plus b square by 3. So it's the same moment of inertia, but omega Omega is different. Omega is now in z direction. So omega x is 0, omega y is 0, and omega z is z. So this is 0, 0, and then omega. So that's the difference. Here it was 0, omega 0. This angular velocity vector was in the y direction. Here this angular velocity vector is in z direction. So see how much is this Lx, Ly, Lz, Lx, Ly, Lz. What is x component? What is Lx? Lx is this into this 0, this into this 0, this into this 0. So no Lx. Lx is 0. So Lx is 0. Ly, so this into this 0, this into this 0, this into this 0. So Ly is also 0. Lz is this into this plus this into this plus this into this. So this is m, L, m, and then L square plus B square divided by 3 and then omega. So L is m, L square plus B square by 3 and omega vector, because your omega is only in z direction. So omega is omega and k cap, right? And this is also Lx is 0, Ly is 0, so Lz this k cap and omega k cap is omega vector. So you have this relation. Yes, L is parallel to omega, and the magnitude L is equal to I omega. That's simple class 11 moment of inertia. Okay, about this, what is the moment of inertia about the z axis? Use perpendicular axis theorem, and here it is. This is the moment of inertia about z axis. So L equal to I omega, torque is equal to I alpha, all those things can be applied in this case. The same plate, the same origin. But if the rotation is about this y axis, no, you need product of inertia, and L is not parallel to omega, and things are very complicated. But if the axis of rotation is z axis, very simple life. So what is so special about this z axis which is not there in the y axis? And there comes the concept of principal axis of the system. If you have any rigid body and you are given a point fixed in that rigid body or with respect to that rigid body, from that point you can definitely find 3 perpendicular directions, at least one set of 3 perpendicular directions in which the product of inertia terms are 0. So if you use those 3 axes, very special directions in the rigid body, once the rigid body is given and a point is given, origin is given, you can obtain at least one set of 3 perpendicular directions, so that if you choose those directions as x, y, z axis, the moment of inertia tensor, that matrix, will not have product of inertia terms 0, those will be 0. Only the diagonal terms will be there, ixx, iyy, izz will be there. Now it so happens that, I will talk more about these principal directions, but it happens that from this O, one of those 3 directions is the z axis. One of those 3 directions is z axis. X axis is not one of those 3, y axis is not one of those 3, but z axis is one of those 3. So where are the other 2? Z axis is a principal axis direction, it is a principal axis for this plate. Z direction is the direction of principal axis for this plate. Where are the other 2? They have to be in this xy plane, but these are not, because if I use these x, y, z, I do have this product of inertia terms. You can find that, and this will be your homework. It must be in this plane. So suppose it is at some angle alpha, this is say x prime and this is y prime in this plane. So if these are our principal axis, then the product of inertia term should be 0. So take this as x axis, take this as y axis, and z axis is here, and calculate these terms as I had calculated from the very basic definitions. Ixy is equal to minus summation I mixi yi. Calculate that product of inertia, put that equal to 0 and find what is alpha. Then you will get those 3 principal directions. But nevertheless, at this moment, if the axis of rotation is, what is the axis of rotation? Direction of omega, that is direction of omega. Remember, this need not be constant in time, it can change with time. I am talking of certain instant. The direction of omega is along one of the principal axes. Then you have L is equal to I omega, where I has the usual meaning moment of inertia about that omega direction, about that axis, instantaneous axis of rotation. So this will work provided this omega is along one of the three principal directions, and here it so happened that yes, the z axis was one of the three principal directions, and therefore this all worked, and here it was not, here it was not, and therefore you had all those complicated things. Now a question, if you look at this L, I am now rotating this plate about this y axis, x axis, y axis, and this is the direction of omega. I am rotating it this way. So all these calculations are valid. Angular momentum is given by minus mlb omega by 4 I cap plus ml square omega by 3 j cap. My question is torque 0 or it is not? Torque, remember torque we say is dl dt. So if this L is constant in time, as time passes this L remains the same, then the torque is 0. Alright. The question is, in this condition, what happens to that torque? Is it 0 or it is not? Lx, see this Lx, this is Lx, x component of L, and that is capital M, constant mass of the plate, small l, constant length of the plate, b, constant width of the plate, omega, say constant, it is rotating at uniform velocity. I give you, this plate is rotating about this y axis with a uniform velocity omega, so this omega is same, it does not change with time. Constant, so this Lx is constant. Come to Ly, m is constant, mass, L square constant, omega constant, 3 constant, Lx is constant, Ly is constant. So what is the conclusion? This L vector is constant, and so what can we derive? If L is constant, the torque is 0. For uniform angular velocity of the plate, you need not apply any torque, but this conclusion is wrong. This conclusion is wrong. Lx is constant, Ly is constant, Lz is constant, but the torque is still not 0. Why? Because this I cap, this j cap is not constant. As the plate rotates, the x axis was along the length. Alright, so if this is the plate, this is the x axis along the length, and y axis is here. This I cap is in this direction along the length, and j cap is in this direction along the width. And as this rotates, this j cap does not change, but I cap changes. This is I cap now, and this is I cap now, and this is I cap now. So as it rotates about the y axis, this j cap remains constant, but this I cap changes. So although Lx is constant, Ly is constant, but what we are using is a rotating frame of reference. K cap is also changing. Where is K cap? Perpendicular to the plate. This is z axis, and as it goes from this position to this position, z axis also tilts. So K cap is also changing. So we are using rotating frame of reference, non-inertial frame of reference. In this reference frame, yes. With these x, y, z axis, yes. In this rotating frame, L is constant. But if in the rotating frame L is constant, that does not mean that dl dt equal to tau will be 0. So we had this relation, very important relation, dl dt in the inertial frame is equal to dl dt in that rotating frame and plus omega cross L. So in our case this is 0. In the rotating frame this L is constant, but in the inertial frame, which is non-rotating, dl dt is equal to omega cross L. You have expression for L. You have expression for L. You have expression for omega. You can calculate from here what is the torque. So let us do that. Let us do that. Simple. Torque is equal to omega cross L. Right? Torque is equal to, this is torque, inertial frame of reference, dl dt is torque, is equal to omega cross L, is equal to omega cross L, is equal to omega j cap, and then cross L, this L here, minus m L b omega by 4 I cap, and then minus plus here m L square omega by 3 j cap. Cross product j cap cross j cap is 0. So, you have minus m L b omega square divided by 4 j cap cross I cap is minus k cap. So, plus here and k cap here. This is our torque. To maintain uniform angular velocity of this plate, you have to apply this much of torque. So, torque equal to I alpha will not work. Alpha is 0, no angular acceleration. The angular velocity does not change with time, neither the magnitude nor the direction. But torque is not 0, angular acceleration is 0, torque is not 0, torque equal to I alpha will not work. To maintain a uniform angular velocity, you have to apply this torque. You have to apply some forces in the xy plane perhaps, which will produce this kind of torque in z direction. So, those are the kind of things that are there. Now, how to find this principal axis of any rigid body given the origin? So, there are standard mathematical procedures. You have to solve certain equations, and those equations will definitely give you the 3 directions which are principal directions or principal axis direction or principal axis going through that particular origin. But there is if symmetry permits, if the object is of some good geometrical shape, you can just by inspection find where are those principal directions. So, there are 2 simple rules which works most of the time. I will tell about that. So, one is rotational symmetry axis. We call an axis as n-fold rotational symmetry axis if a rotation of 2 pi by n, of course n is an integer, positive integer. If a rotation of 2 pi by n about the axis does not change the mass distribution of the body, all right. So, this is called n-fold rotational symmetry axis. If you rotate the whole body by this angle about that particular axis, then the mass distribution does not change. So, we can take some simple examples. For example, suppose you have a square plate or this plate, this rectangular plate, and then I have a line which passes through the center of this rectangular plate and is going in perpendicular direction. Okay. So, now let me put it on the table. So, now see the mass distribution, where the masses are, where this rectangular plate is. Suppose I rotate it by an angle pi by 2, rotate pi by 2 about this z axis, about this chalk, the mass distribution has changed. But if I rotate it by an angle of pi, so I come here, and if it is a uniform plate, I get the same mass distribution again. Mass distribution now and then the mass distribution now is the same, identical if the plate is uniform. So, this axis is such that a rotation of 2 pi by 2, a rotation of 2 pi by 2 which is pi about this axis does not change the mass distribution. So, this axis is a 2-fold rotational symmetry axis. Similarly, suppose you have a triangular plate, equilateral triangular plate, and you are at the centroid, and then draw a line perpendicular to the plane, rotate by 2 pi by 3, 120 degrees. Now, look at this object. If I check for this axis of rotation, this line through the center, and see the mass distribution now, this blade is here, this blade is here, this blade is here. I rotate this fan by 120 degrees, 120 degrees, the same mass distribution I have obtained. Another 2 pi by 3 is this, the same mass distribution I have obtained. another 2 pi by 3, and I get the same mass distribution, and this time I have completed 2 pi rotation. So, the same particles have returned to the same positions. Okay. So, I am not worried about that. If the mass distribution is same, 2 pi by 3, rotate by 2 pi by 3, and you see that the same mass distribution results, this is a 3-fold rotational symmetry axis. Now, here is a square plate, this is a square plate, and suppose I put my axis here through the center perpendicular to the plane of the plate. Now, you can very well see, if I rotate this plate about this axis by 90 degrees, that is 2 pi by 4. So, 90 degrees, I rotate it by 90 degrees, and you see that you get back the same mass distribution. Rotate by 90 degrees and you get the same mass distribution. Rotate by 2 pi by 4 and you get the same mass distribution. So, this axis is a 4-fold symmetry axis, rotational symmetry axis for this plate. Of course, this 4-fold, if you rotate by 2 pi by 2, that is pi, right, then also you get the same mass distribution, but it is not called 2-fold symmetry axis, it is called 4-fold symmetry axis. Alright, so if a rotation of 2 pi by n with n greater than 1, it has to be positive integer and also greater than 1, because if it is 1, you rotate by 2 pi, so everything will get back to the same position. So, that is not a rotational symmetry axis. If a rotation of 2 pi by n with n greater than 1 about the axis, about the line, does not change the mass distribution, does not change the mass distribution of the body, this axis or this line or this direction is called n-fold rotational symmetry axis. And is, this is important for us, is a principal axis, is a principal axis of this object, of this body, through any origin on this line, on this axis. Okay. So, if I have an object and that object, and then there is a point, and I can find a line, I can find a line which is 2-fold symmetry axis or 3-fold symmetry axis or 6-fold symmetry axis, this line has to be a principal axis through this origin. And if I take my origin here, then also, if I take my origin here, then also. So, this line is a principal axis of this object. So, this is one way to guess the principal axis. If you recall our calculations, I said that this is not a principal axis, this is not a principal axis. If I am using this as x, this is y, then I rotate it along about this line, or if I rotate it about this line, my angular momentum is not parallel to the angular velocity, but if I rotate it about this vertical line, then it is, and I said that this is a principal axis. But is this a rotational symmetry axis? No. If you rotate about this line, you will have to rotate all the way 2 pi rotation, then only you will get back the same mass distribution. You have to rotate it all the way 2 pi, then only you will get the same mass distribution. So, it is a principal axis, we have seen that in the calculations, but not because of this. There is yet another beautiful way. If that symmetry also exists, you can get the principal axis, and that is when you have what you call plane of reflection symmetry. If you get a plane through the point of interest, and so that if you reflect the body in that plane, the mass distribution does not change, that plane is known as plane of reflection symmetry. So, if the object is reflected, okay, in the plane, and the mass distribution does not change, that plane is known as plane of reflection symmetry. Let us take examples and look at this brick here placed on the table, and let me take a plane. Suppose from the middle I am using this plane. What happens if I reflect this brick in this plane? This side will go to that side and that side will come to this side. Everywhere all particles have to be reflected. These particles will go that side, those particles will come this side. So the mass distribution will remain the same. Of course the brick is supposed to be uniform. So this is a plane of reflection symmetry. This is a plane of reflection symmetry, or this is a plane of reflection symmetry. This upper part goes to the lower part comes to the upper part. If it is right from the middle, these are planes of reflection symmetry. Similarly, if you consider this hemisphere, and then you draw a plane like this or this or this or this plane is plane of reflection symmetry. So if the object is reflected in the plane and the mass distribution does not change, that plane is known as plane of reflection symmetry. And for us the most important thing is all directions or all lines perpendicular to a plane of reflection symmetry are principal directions or principal axis. All such lines are principal axis. Okay, so come back to this hemisphere. And I have a plane of reflection symmetry. You can see this is a plane of reflection symmetry. Now any line perpendicular to this, that means if I draw a line from here perpendicular to this plane, this is a principal axis for this hemisphere. Okay, I am drawing tangent from this topmost point of this hemisphere, and this line is a principal direction, and in fact all tangents will be principal directions. So this is another rule. If you can find a plane of reflection symmetry, then all directions perpendicular to that plane will give you the principal axis. Now if I talk of my rectangular plate, the example with which I had done all the calculations, is a two-dimensional object. So this plane itself is a plane of reflection symmetry. Okay, here are the masses, these are the masses of the object. If I reflect this object in this plane, what happens? Nothing happens, everything remains at its own position. So this plane itself can be called plane of reflection symmetry. So all directions which are perpendicular to this are principal directions, and that is why this direction, that is why this z axis is a principal axis. So if you can find a n-fold rotational symmetry axis n greater than 1, that will be a principal axis. Through all the points, origin can be taken anywhere on that particular line, that will be principal axis. If you can find a plane of reflection symmetry, then also it is very simple. Any point you take on that plane and draw a perpendicular line, that will be principal axis. So you can identify the principal axis easily if such symmetries exist, and if you can, then you can write your equations which take very, very simple form. So this is a kind of supplement to our week 8 lecture 3, that is 24th lecture, in which we discussed principal axis or principal directions of a rigid body. And you know what this principal axis are. If you have xyz axis, then you have product of inertia terms and principal moment of inertia terms, ix, xy, etc., ixz, like that. So if all these product of inertia terms are 0, the axes are principal axis. So that is kind of a definition, principal axis. And we had two simple ways to identify if a particular line is principal axis or not, and one was rotational symmetry axis, rotational symmetry axis. If you have a rigid body and origin is given here and you are searching for 3 principal axes with this origin, and you find that okay, here is a line which is a rotational symmetry axis. If you rotate this body about this line by an angle 2 pi by n, n integer and greater than 1, then this line will be principal axis. So that we had given. Another was reflection symmetry plane. Reflection symmetry plane. So if you have a rigid body and you have a point origin and you are looking for principal axis of directions, and then you find that okay, there is a plane through this point which is reflection symmetry plane. If you reflect the whole rigid body in this, the mass distribution does not change, and then you say that okay, any line perpendicular to this plane is a principal direction or principal axis, can be taken as principal axis. Now the supplement I want to discuss today is that the choice of origin is not to be forgotten. You first choose the origin and then look for all these axes. Otherwise, if you shift the origin or you don't think of the origin, a particular line, whether it is principal axis or not, that cannot be guaranteed. So I give an example. Our example of this rectangular plate with some length L and some width B, uniform rectangular plate. So we had seen that if I take this as the origin, and then if I take this as y axis, this as x axis, and then we calculate, and the z axis is here, and then this is rotating about that y axis, that we had done in the lecture, that if it rotates this way with a uniform angular velocity, L is not parallel to angular velocity vector, angular momentum vector is not parallel to that, the torque is equal to I alpha does not work, because this is not a principal axis system. These 3 axes are not principal axis system, and you can see that I x y is not 0. X and y are always positive, and therefore that minus mi xi yi or integration dm xy, that will not be 0, and therefore all those things happen. But if the rotation is about z axis, if the rotation is about z axis, then everything works well, because this is a principal axis. From this point, this is a principal axis, and that reflection symmetry plane works. This whole plane itself is a reflection symmetry plane, and this is perpendicular to that. Okay. But now I give another example. So this is not principal axis direction, this is not principal axis direction, this is principal axis direction. Now I give another example, that same plate, the same plate, and I take the origin here. Suppose this is the origin, and then this is x axis, and this is y axis, and the z axis is like this. Now if you calculate that product of inertia term, z is 0 everywhere, so ixz and iyz, these will be 0, and ixy is also 0, because you take any element here, and then if I take a corresponding element here, then that minus mi xi yi, you can write in integration form also. So for this element here, it is x into y, and for this it is x into y. Y it's same, positive, but x is negative here, here, and positive here, and so pairwise this term will vanish, and that can be done everywhere. You can distribute these pairs here, 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 and so on. This entire thing can be thought of, made of such pairs, and ixy is also 0. So this is a principal axis system. So this line, think of this line. This is not a principal axis here. This is not a principal axis. This x-axis, the same edge is not a principal axis here, but it is a principal axis here. Okay. So this is important. If I, from this origin, if I take this as a plane, right, this as a plane, so in that plane if you reflect, that plane is a reflection symmetry plane, and lines perpendicular to that from any point, from here, from any point, will be a principal axis. If your origin is on this plane, if the origin is on this plane, then you can draw the perpendicular, and this is a principal axis. But here that is not the case. Here that is not the case. This plane is not reflection symmetry plane, this line is not perpendicular to that, and it is not the same line, is not a principal axis direction here, the same line is principal axis direction here. So don't forget to first choose origin and then look for the principal axis from that origin. So that you can add to our lecture 8 and week 8 and lecture 3. So by now we have developed several techniques and we have understood how to deal with rigid body motion if one point is fixed and it is rotation about that point. Our central equation is torque is equal to dl dt, where L is the angular momentum, and that is the true for inertial frame of reference. So we can use any axis system to describe the body. If it is inertial frame, it is good, fine, you can write your equations, but many times it is simpler to use axis system which are rotating with respect to the inertial frame of reference. So if you use the rotating frame of reference, then this dl dt inertial is equal to, in the inertial frame, is equal to dl dt in the rotating frame and plus omega cross L. Omega is the angular velocity at that instant. This equation works. And then this rotating system can also be of two types: fixed with the body is rotating, this frame is rotating, and this frame is fixed in the body. This is one possible choice. Another possible choice is, yes, it is a rotating frame, but the axes are not fixed in the body. They are not fixed in the inertial frame and they are also not fixed in the body. That is also possible, and sometimes that is more useful, so we will be using that. Sometimes this is easier, so we will be using this. So fixed with the body and not fixed with the body. So depending on the situation, we can use inertial frame or a rotating frame. In the rotating frame, we can either use a frame which is fixed with the body, which rotates with the body, and with respect to the body the frame is fixed, or we can have a rotating frame but the body is not fixed in that frame also. So that can also be used. If you are using this, if you are choosing the frame which is fixed with the body, or even in this case also, if the axes are, is another issue, if the axes are also principal axis, right? And what is principal axis? If you have x, y, z axis, and in those axis system the product of inertia terms are all 0. Okay, you have 9 components of moment of inertia, 3 on the diagonal which we write ixx, iyy and izzz, and then the off diagonals which we write ixy or iyyax or ixz and so on. So those are product of inertias. So if you are using the axes which are also principal axis of the rigid body through that origin, then the life is simple in many cases. Okay, so we will be talking of this. We will be choosing axis system which is fixed with the body and the axes themselves are principal axis. So then what happens to the equation of motion, this equation of motion? All right. So in this system, if you have this, we will write it as 1, 2, 3. Suppose this is the origin, and then there is some one direction, one axis, then there is some two axis, and there is some three axis. So this 1, 2, 3, and the unit vectors are E1 cap, E2 cap, E3 cap. These are principal axes of this this body, and for a given body and for a given this origin, you can always find at least one set of principal axes. Okay, you can find more also, then you will have a choice which one you want to use, and those unit vectors are E1 cap, E2 cap, E3 cap. All right, so this is our torque. This is our torque, inertial frame. Now what is this? What is this? What is this? In the rotating frame, what is dl dt? In the rotating frame, you will write L as L1 E1 cap, L2 E2 cap, and plus L3 E3 cap. And this omega you will write as omega 1 E1 cap plus omega 2 E2 cap plus omega 3 E3 cap. Because in general you will be said, okay, this body is rotating about it has this angular velocity at this instant, and this angular velocity is not, this direction is not a principal axis direction. So you cannot choose your axis here if you want to use this formulation. Then this omega will have some component in E1 direction, E2 direction, and E3 direction. So it is this. And then this this L1 will be I1 omega 1, L1 will be I1 omega 1, that is it. If you are using principal axis, it is very simple, L1 is just I1 omega 1 E cap here, E1 cap here, plus L2 is I2 omega 2 E2 cap, and plus L3 is I3 omega 3 E3 cap. Okay, because in principal axis system you do not have any this off diagonal terms. So, your matrix is like this, Ixx which I am writing I1, Iyy which I am writing I2, and I33 Izz which I am writing I3, and rest are all zeros, rest are all 0. So, if you want to write L which is I times omega, this is I and this is omega, omega 1, omega 2, omega 3, and then you can see L1 is I1 into omega 1 plus 0 into this plus 0 into that. So, there is just I1 omega 1, and similarly L2 is I2 omega 2 and L3 is I3 omega 3. So, what is this dl dt in the rotating frame? This dl dt in the rotating frame, dl dt in this rotating frame, in this body fixed principal axis frame, that will be I1 will not change. Now, you are fixed with the body, axes are fixed with the body, the x axis or one axis that you have chosen, it is fixed with the body. So, I1 which is Ixx, usual moment of inertia about the one axis, that is not going to change with time, but omega 1, yes, it can. So, it is omega 1 dot E1 cap plus here it is dl dt. So, this is L dl dt I1, and then omega 1 dot E1 cap plus I2, and then omega 2 dot E2 cap and plus I3, and omega 3 dot and IE3 cap. This is this first term. And what is omega cross L? Here is omega, here is L. So, what is omega cross L? So, omega cross L, you can write it E1 here, E2 here, E3 here, cap, 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 and then omega 1, omega 2, omega 3, and this L1, L2 which is I1 omega 1, I2 omega 2, and I3 omega 3. So, the x component, the one component omega cross L, one component will be E1 cap, and then omega 2 into this, that is I3 omega 2 omega 3, and minus this into this, minus this into this, I2 omega 2 omega 3. This is just a way to easily write this cross product, otherwise you can always do this omega cross L, that means omega 1 E1 cap cross this whole thing, and then E1 cap cross E1 cap is 0, E1 cap cross E2 cap is E3 cap, E1 cap cross E3 cap is minus E2 cap, and so on. Similarly, do with this term, and you can get the same expression. So, this is the x, this is the first component. So, this is the first component. So, I can remove this, and similarly the second component will be just cyclic permutation of this. You can take this omega 2 omega 3 common, and it is I3 and minus I2, and the second component will be omega 3, in place of 2 you write 3, in place of 3 you write 1, so omega 1 here, and then in place of 3 you write 1, in place of 2 you write 3, so it is this. And similarly the third component is omega 1 omega 2 cyclic permutation I2 and minus I1. This is it. Alright, so now let us write this equation, one component of this equation, one component, take one component, and I am writing 1, 2, 3, not x, y, z, because x, y, z we will be using for inertial frame, and this is the principal axis frame that we are writing. So, we have given different names, not I cap, j cap, k cap. Of course, you can do that, but in many cases you have to use both the frames, inertial frame and this rotating frame. So, that is why we are using these symbols. So, the one component in this direction, that will be tau 1, one component of the torque. So, now we are writing this equation, one component of the torque is equal to one component of dl dt, dl dt is here, one component of dl dt is I1 omega 1 dot. So, this is I1 and omega 1 dot plus, right, one component of omega cross L, and one component of omega cross L is here. So, it is plus omega 2 omega 3, and then I3 minus I2. Then two component along this direction, this principal axis. So, that component will be here, it will be tau 2, inertial frame of reference, dl dt is the torque. So, tau 2 is equal to, and then two component of this is here, I2 omega 2 dot. So I2 omega 2 dot, and then 2 component of this is here, omega 3 omega 1 and I1 minus I3. Then similarly tau 3, the 3 component of this is tau 3, 3 component of dl dt is I3 omega 3 dot, so this is I3 omega 3 dot, and then plus 3 component of this, which is omega 1 omega 2 and I2 and minus I1. In fact, if you have written 1, do a cyclic permutation of these indices and you get this, and do cyclic permutation of this, you get this. So these are the equations. They are named as Euler's equations. Euler's equation for this rigid body motion. So if it is easier to use this frame, you can use these equations to describe the motion. So let us take some examples of using this Euler's equations. So here is the problem. A uniform rectangular plate is rotated about its diagonal AC. Figure is given. So A, B, C, D is a uniform rectangular plate, and this AC is one diagonal with a constant angular velocity omega. So it rotates about this AC with a constant angular velocity omega. First question is, find the torque needed to maintain this constant angular velocity. You know, even for maintaining uniform constant angular velocity, sometimes you need torques. If the forces to produce this torque are applied at the support points at A and B in directions perpendicular to AC, find the magnitude of these forces. So if the forces are applied here and here, then you have to find the magnitude. So let's first do this. Since the axis of rotation is along the diagonal, or the diagonal is the axis of rotation, and that is fixed omega, so we can choose our origin at the center of this plate. So let us choose our origin at the center of the plate, and then the principal axis are very simple. This is one principal axis, this is another principal axis, and the third is perpendicular to this plate. So these are the axes. Let us call this as one axis, this as 2 axis, and this perpendicular to the plate as 3 axis. This is a principal axis, because if you take a plane here, plane of this type, then this is a reflection symmetry plane. If you reflect in this plate, or it is a twofold rotation symmetry axis also, so that also tells me that this is principal axis, and this is a reflection symmetry plane. So any line perpendicular to it will be principal axis. Similarly, this is principal axis, and the third one is also principal axis. Okay. So if I am using these 1, 2, 3 axes, and which are principal axes, so I can write what is I1. I1 is the usual moment of inertia about the first axis. Okay, let's take length as L and width as B. So moment of inertia about this, moment of inertia of this plate about this line, and that will be mb square by 12. Mass of this plate, let us take this as m. So I1 is mb square by 12, I2 will be ml square by 12, and I3 perpendicular axis theorem will be ml square plus b square by 12. So this is I1, I2 and I3. And omega, this is omega direction, and the magnitude is omega, and that is fixed. So omega is equal to omega 1, or omega 1 is equal to component in one direction, that is this omega into cos of this angle here, cos of this angle, let's call it theta, let's call this angle as theta. We know what theta is, tan theta is b by L, tan theta is b by L, so it's known. So this is cos theta, omega 2 is omega sine theta, because these are in the same plane, this axis and this line are in the same plane. So omega cos theta this side, omega sine theta that side, and omega 3 is 0. What are our Euler's equation? Tau 1 is equal to I1 omega 1 dot plus omega 2 omega 3 and I3 minus I2. Euler's equation, first equation is this. Then you have second equation. Second equation is just cyclic permutation. 1 becomes 2, 2 becomes 3, 3 becomes 1, 3 becomes 1, and 2 becomes 3. Then tau 3 is equal to I3 omega 3 dot and plus omega 1 omega 2 I2 here and minus I1 here. 1 becomes 2 and 3 becomes 1. So these are our Euler equation. Let's use these quantities here. What is tau 1? Let us see what is tau 1. So, tau 1 will be equal to omega 1 dot, omega 1 is omega cos theta, does not change with time, and therefore, this is 0, and omega 2 is also constant. So, this will be 0, omega 3 is constant. So, this will be 0, these terms are 0. Here omega 2 into omega 3, omega 2 into omega 3 is 0, omega 2 into omega 3 is 0. So, tau 1 is 0, we get tau 1 is 0, tau 2, this is anyway 0, and omega 3 is 0. So, this omega 3 is 0, and therefore, tau 2 is also 0, and we are only left with tau 3. This term is 0, omega 3 is constant, omega 3 dot is 0. Here it is omega 1 into omega 2, omega 1 into omega 2, and that is omega square sin theta into cos theta, and then I2 minus I1. So, I2 is here and I1 is here. So, m and then L square minus B square and divided by 12. Okay. You have I2 minus I1, here is I2, here is I1, and I2 minus I1. So, m L square minus B square divided by 12, this is the torque. So, our torque needed is, our torque is equal to omega square. What is sin theta and what is cos theta? So, cos sin theta is B divided by this. So, B divided by square root of L square plus B square, and then cos theta is L divided by the same. So, L divided by square root L square plus B square. So, that is the sin theta cos theta, and then m and L square minus B square by 12. So, this is the torque, this is the torque. You have m, then you have omega square, you have B, you have L, and then you have this quantity L square minus B square by 12, and then divided by L square plus B square, E3 cap, right. So, this is the torque which is needed, and the torque is in the direction of E3, and that direction is changing as it is rotating. Remember that E3 direction is perpendicular to the plane of the plate, and the plate is rotating about this diagonal. So, this plate is rotating, and the normal, the perpendicular is also rotating, this E3 direction is also rotating, E1, E2, everything is rotating. These are body fixed principal axes. So, your torque is not constant, the torque is changing. So, you have to do proper, you have to apply proper forces. Now, the second part is this torque is obtained by applying forces here and perpendicular to AC, and the torque is in A3 direction. So, E3 direction, so this direction, so it should go like that, and hence this force is here in this direction and here in this direction. They must have equal magnitudes, the center of mass is fixed. So, this is F and this is F, and the torque of these two about this line, this point is F multiplied by this and plus this, the whole length which is L square plus B square, square root of that. Okay, let us see once again the force of this F, the torque of this F about this, what is that? Since it is already perpendicular, it is F multiplied by this length and in this direction, and here the same thing, F multiplied by this length, same thing, and therefore, F multiplied by double of this length, that means this whole diagonal, and that is L square plus B square square root. So, it is this. So, this should be torque, this should be torque. If I apply F, this is the torque, but what I need this much. So, this is m omega square L B by 12 L square minus B square divided by L square plus B square, and from here you can get F. What is F? F will be m omega square L B by 12 L square minus B square divided by L square plus B square to the power 3 by 2. So, this much force you have to apply here, and this much force you have to apply here to get that torque, to maintain this uniform angular velocity of this rectangular plate about the diagonal. Let us take next question. So, here is another problem. A uniform circular disc of radius capital R and mass capital M rests on a support at its center. At time t equal to 0, it is given an angular velocity omega which makes an angle alpha with a normal to the disc. So, what is the situation? You have a circular disc. So, suppose you have the circular disc, and then at t equal to 0, this is let us say the normal, this is let us say the normal perpendicular, and then it is given an angular velocity omega, which is making an angle alpha with this normal, So that's the situation. At t equal to 0, this is given in angular velocity omega, which makes angle alpha with this normal to the disk. This is a circular disk, and it is supported at the center, and therefore there is no torque. Right? It's just supported at the center, so weight, etc. These things are not important for us, and no torque is applied, and just this angular velocity is given at t equal to 0 and then left. And then your question is find the angular velocity of the plate at a later time in an appropriate frame. So let's choose a principal axis frame which is fixed in the body, and we choose our 3 axes along this, because this is the principal axis. It's a circular disk, so any diameter, any radius gives you a principal axis direction, and perpendicular to the disk is also a principal axis direction. So this is 3, and at t equal to 0, you know what is omega and what is this 3, and in that same plane you draw the radius, and that we will take as our 2 axis, and perpendicular to this 2 axis we take another radius, and that will be our 1 axis. So this is the radius, this is the radius, so they are principal axis. This is normal, that this is also principal axis. So this is our principal axis system. And if I write Euler's equations, remember I1 tau 1 is equal to I1 omega 1 dot plus omega 2 omega 3, then I3 minus I2. This is tau 1, tau 2 is I2 omega 2 dot omega 3 omega 1 I1 minus I3, and tau 3 is equal to I3 omega 3 dot and then omega 2 omega 1 and omega 2, so omega 1 omega 2 and then I2 minus I1. So these are the Euler equations. In our case tau 1, tau 2, tau 3 all are 0, and then let us see what happens. Let's see what happens. What is this? This is 0, so I1 omega 1 dot is equal to minus omega 2 omega 3 and then I3 minus I2. We know what is I1, I2, I3. Okay, so let me put I1. What is I1? I1 is moment of inertia of this disk about this one axis, which is a diameter, and it should be mr square by 4. Correct? About this normal, it is mr square by 2, and then these two are equal and they add to this one, so this should be mr square by 4. So I1 is mr square by 4. I2 is also mr square by 4, and I3 is mr square by 2. So it gives me I1, which is mr square by 4 omega 1 dot equal to minus omega 2 omega 3 and I3 minus I2, this minus this, which is mr square by 4, and therefore omega 1 dot is equal to minus omega 2 omega 3. Okay. Similarly, write that second equation, this one. Tau 2 is 0. So 0 is equal to I2 is this one, mr square by 4, and omega 2 dot. So this is all right. So this is 0. So this is negative of that. So I2 omega 2 dot is equal to minus omega 3 omega 1, and then I1 minus I3. Here is I1 and minus I3 is here. So minus mr square by 4. So this is minus mr square by 4. See it once again. What I am doing? I am writing this equation, and tau 2 is 0. So 0 is equal to this. So I2 omega 2 dot is negative of omega 3 omega 1 and I1 minus I3, and that is what we are writing. I2 omega 2 dot, this is I2 omega 2 dot is equal to minus omega 3 omega 1. So minus omega 3 omega 1, and then I1 minus I3, I1 minus I3 is minus mr square by 4, and therefore if you cancel, you get omega 2 dot is equal to, this becomes plus omega 1 and omega 3. So omega 2 dot is equal to omega 1 and omega 3. And the third equation is tau 3 is equal to 0. So this is negative of that. So I3 and omega 3 dot, I3 omega 3 dot is equal to negative of omega 1 omega 2 into I2 minus I1, and I2 and I1 are equal, and therefore this is 0. So this is 0, and hence omega 3 dot is 0 and omega 3 is constant. And what is that constant? What is that constant? That is constant, so the value does not change with time. At t equal to 0, we know omega 3 is omega cos alpha. So, this constant is omega 3 cos alpha. So, this is it. So, omega 3 is fixed, omega 3 we have gotten, this is omega 3. Look at omega 1 and omega 2, and let me use that same technique I had done earlier, multiply it by I, and this I is square root of minus 1, and add. You get omega 1 dot plus I times omega 2 dot is equal to minus omega 2 omega 3 plus omega 1 omega 3 and I, which is equal to, let us take omega 3 into I as constant, I omega 3 as common. Let us take this as common. From here I get omega 1, and from here I get plus I omega 2, right? You can check. When I multiply this, I get I omega 3 omega 1, which is here, I omega 3 omega 1. When I multiply this, I into I is I square, that is minus 1, and then omega 3 into omega 2. So, here is minus 1 and here is omega 2 into omega 3. So, it is this. So, if I say Q, if I name it Q, omega 1 plus I omega 2, if I name it Q, this is Q dot. This is Q dot, and is equal to I omega 3, I omega 3, and this is Q. So, a quite simple equation, Q dot is equal to I omega 3 Q, and hence dq divided by Q is equal to I omega 3 and dt. Q dot is dq dt, that dt goes this side, I omega 3 dt, this Q comes here, dq by Q. What I have? I have Q dot is equal to I omega 3 and Q. So, I am integrating dq divided by this Q is equal to I omega 3 dt. So, integrate ln of Q, ln of Q is equal to initial final omega I omega 3, and then t here 0 to t, this is also from t equal to 0 to t, Q ln of Q at time t, which I write Q, divided by Q at time t equal to 0, this is it, and that is equal to I omega 3 t, and hence Q is equal to Q at the initial time and e to the power I omega 3 t. What is this? What is this Q0? At t equal to 0. At t equal to 0, what is Q? Q is defined here. At t equal to 0, I had taken my 2 axes in the plane of omega and this 3 axis. So, these are in one plane and this is perpendicular to that plane, and therefore, this omega has no component in one direction. So, omega 1 is 0. So, at t equal to 0, omega 1 is 0, and omega 2 is omega sine alpha. So, it is omega sine alpha. All right. So, Q is equal to omega 1 plus I omega 2 is equal to I omega sine alpha. This is Q at t equal to 0. Hence, Q at time t is equal to Q at time 0, which is I omega sine alpha, and that multiplied by e power I omega 3, and that omega 3, in fact we know omega 3 is omega cos alpha. So, this is omega cos alpha, right. So, this is equal to I omega sine alpha multiplied by cos of omega cos alpha and plus I times sine of omega cos alpha, and that is equal to first let us write this one, this multiplied by this, right. This e to the power I omega cos alpha is cos of omega cos alpha plus I times sine of omega cos alpha. So, this multiplied by this will be minus I is minus, then I have omega here, then I have sine alpha here, and then I have sine of omega cos alpha here. So, it is dimensionally not correct. So, I have left something. So, Q is equal to, this is Q at time 0 e to the power I omega 3 times t. So, it is omega t here, omega t cos alpha and omega t cos alpha, right, good. So, omega t cos alpha is this minus then omega, then sin alpha, then sin of omega t cos alpha, right, and then this multiplied by this is plus I omega sin alpha and multiplied by cos of that same thing omega t cos alpha. Okay. But what is this q? This q is omega 1 plus I omega 2, and the real part should be equal, the imaginary part should be equal. So, omega 1 should be equal to the real part, and where is the real part? This is the real part. So, omega 1 is minus omega sin alpha and then sin omega t cos alpha or omega cos alpha times t. And omega 2 is equal to, what is omega 2? Is that imaginary part, and that is here, this is omega sin alpha times cos of omega t cos alpha. Alright, so we have gotten omega 1 as a function of time, omega 2 as a function of time, and omega 3 as a function of time in the particular principal axis frame we have chosen. So, that completes our question. We have gotten omega as a function of time in this frame. However, what is the, how does the disk look like in the lab frame? Because this tells me that this omega 3 is constant. So, the component of omega about this 3 axis is constant, that is fine, and omega 1 and omega 2 are rotating. Omega 1 and omega 2, they are rotating with this angular frequency omega cos alpha. So, if I look at in this frame, in this principal axis frame, this omega is rotating, is going in a cone, this omega vector is going in a cone. The tip of this is going in a cone, because in our frame we consider 1, 2, 3, these are the axes, and the entire motion is described in that frame. So, this is 3 axis fixed in our body, and in that frame this omega has to move this way, this has to change, the axis of rotation has to change this way. It is body is rotating about this, then about this, then about this, then about this. So, these vectors are changing with time, and that rotation is this, and this cone is known as body cone. But if you go in the lab frame and there you see what happens. So, even this 3 axis is not fixed, even this is going in a rotating frame, rotating fashion. And how to get that? So, I will just give you some hints. You calculate what is the angular momentum. Okay, you calculate what is the angular momentum, and that angular momentum is fixed in the inertial frame because there is no torque. So, that will have a direction, this L will have a direction, and that is fixed direction, and then this 3 axis will go around that this L vector, and that yet another cone which will be made. So, these are the body cone and the space cone, those are somewhat more advanced topic that I will be not taking up. So, in the next lecture we will take some more problems on rigid body dynamics and see how we solve it. So, we are close to the end of this course on classical mechanics. I had done some problems on rigid body rotation about a point using Euler's equations of motion, and I will do some more problems before finishing the course. Now, today first of all I will show you some demonstration. I have this notebook. So, it is essentially a rectangular plate, it is like a rectangular plate with some thickness, and if I use the center of mass as the point origin, then very easy, 3 principal axes, one along the length, one along the width, and one vertical perpendicular to this plane. So, these are the principal axes. Now, what I will do is I will rotate it about a principal axis, one of those 3 axes, and then let it fall. So, it falls under gravity, so that mg is acting, but that mg does not have any torque about the center of this plate of this notebook, and so no torque is exerted by that mg, and hence as far as the rotations are concerned, we will have as a 0 torque situation. The center of mass will fall, x is equal to half gt square and all those things, but then the rotation is still guided by our equations of rotation. So, first look at this. I will be rotating about this axis perpendicular to this bigger face, flatter face. So, this axis I will be rotating, and you notice how it falls on the table. Okay. Once it falls on the table, that means once it has travelled this much of distance, what has happened to the angular velocity? Initial angular velocity will be along this say one direction, and other omega 2, omega 3 I will try not to give, okay. And if finally when it reaches the table, whether it is still in this plane or it has tilted. So that's the thing to see. So watch. All the time its face, this face, the lower face hits the table, okay. It goes like this, it rotates and then it hits like this. Natural, this is the principal axis, and if you rotate about the principal axis, then class 11 mechanics is fine. So it keeps rotating about that axis and then it just reaches the table and falls. Now I will be rotating about this principal axis. This is also a principal axis. About this principal axis I will be rotating, and then carefully watch what portion of this notebook hits the table first, whether it is this part or it is this part or it is this part. Which part? This edge hits the table, or this edge hits the table, or this area hits the table. Careful. Okay. So all the time you are seeing that this edge is hitting the table, this edge. This whole thing may not hit, it may go like this or it may go like this, but this edge is hitting once again. And now this is the part for which I am doing the demonstration. This is the other axis. So say one axis, then two axis and three axis. So about this I will be rotating, and carefully watch what portion of this plate or this notebook hits the table. Okay. So when I am rotating, it is not this edge which is hitting the table. Alright, most of the time this surface hits the table. I start with this orientation. The angular velocity is given in this direction. So it should go like this, but somewhere it has gone like this. Somewhere during the path it has rotated and the flat part hits the table. So that means this rotation means this is picking angular velocity about this, then it will rotate like this. So although I am giving initial angular velocity along a principal axis as best as I can, of course this is a very crude method of giving initial angular velocity, but there's something special about this, that it picks up the other rotations very fast. So let us do this problem. Let's analyze this problem. So I have this plate. And then there is some thickness. And the three axes are, one is here, call it I1, one is here, call it I2, E1 direction, well, one axis. This is one axis, this is two axis, and then perpendicular is the three axis. What are the equations? Using these as the axis system, this is fixed in the body, and then they are principal axis also. So I can write the Euler's equation I1 omega 1 dot plus omega 2 omega 3 and then omega 3 I3 minus I2 is equal to tau 1, and which is 0. We don't have any torque. So this is the equation. So I1 omega 1 dot is equal to omega 2 omega 3 and then I2 minus I3. Similarly, I2 omega 2 dot will be omega 3 omega 1 and then I3 minus I1, and I3 omega 3 dot will be equal to omega 1 omega 2 and then I1 minus I2. Suppose I start with giving omega 1. So our initial angular velocity is largely, omega is largely say omega 1 E1, and omega 2, omega 3 may be there, small, very small. All right, because I try to give it a pure rotation about one principal axis. Of course, I cannot do it so crudely. So, some omega 2, omega 3 may enter, but suppose it is very, very small. So, what do I see from here? This omega 2, this omega 3 is very, very small, and therefore, omega 1 dot is very small, and hence omega 1 is nearly constant. Okay. So, if I say this is 1, this is 2, this is 3, then what we will say is from 1, since omega 2 into omega 3 is very small, this omega 1 dot is also very small, and hence omega 1 is nearly constant, and whatever angular velocity I had given initially, it will largely, that component will largely remain there. This first component omega 1 will be nearly constant, equal to what I had given initially. Now look at these two equations. This is I1 omega 1 to, okay, right, this is 1, this is 2, this is 3. So look at these two equations, these ones. What does it say? Omega 2 dot. Omega 2 dot, initially I have given a very small omega 2, but then omega 2 dot is equal to omega 3 and then omega 1 here, I3 minus I1 here, and divided by I2 here. Okay, omega 2 dot is omega 3, omega 1, I3 minus I1, and then divided by I2, and from here you have omega 3 dot equal to omega 1 omega 2. So it is omega 2 and then omega 1. So I have written omega 1 omega 2, I1 minus I2, so I1 and minus I2, and divided by this I3 by I3. So these are the equations, and omega 1 is nearly constant, so that's why I have written it here and I have written it here in this bracket. Let's differentiate this one. What is omega 2 double dot? Omega 2 double dot is equal to omega 3 dot, and this is nearly constant, so it is omega 1 I3 minus I1 by I2. Okay, omega 2 double dot is omega 3 dot and then this quantity, and omega 3 dot is here, this omega 3 dot is here, so let's put it there. So this is equal to omega 2 here, I am trying to write this from here, I am writing this from here, and this is omega 2 omega 1 I1 minus I2 divided by I3. So I have written this part and now this part, omega 1 I3 minus I1 divided by I2, this part. So omega 2 double dot is equal to omega 2 into some this whole thing, let's write something. Okay, omega 1 square I1 minus I2 into I3 minus I1, and then divided by I3 into I2. Okay, so omega 2 double dot is equal to omega 2 into omega 1 square I1 minus I2, I3 minus I1, and I3 I2 here. Now this quantity, let us look at this quantity. It's like constant. Omega 1 is almost constant, so it's like a constant. Now if I1 is maximum of the 3, if I1 is maximum of the 3, then I1 minus I2 will be positive and I3 minus I1 will be negative. So this whole quantity will be negative, and I can write that as omega 2 double dot equal to this omega 2 double dot equal to omega 2 into this negative quantity, which I can write as say minus alpha square omega 2. And you know what this equation means. This means omega 2 is oscillating with some amplitude. This is simple harmonic motion type equation for omega 2. So this means that omega 2 is oscillating with frequency or angular frequency alpha. And since initially omega 2, omega 3 were small, I did not want to give any omega 2 or omega 3, but it did crept in there. Or from disturbances of air or some other thing in the path also, it can pick up some small omega 2, omega 3. So, the amplitude will also be small. So, with a small amplitude. And same will be the case with omega 3, same with omega 3. Okay. So, largely it will continue with angular velocity omega 1. Some small omega 2, omega 3 will be there, but that will be oscillating, the amplitudes will be small, and finally, when my notebook falls on this table, it falls with that initial, whatever was initially below this surface, it falls there, if I1 is maximum. In fact, if I take this as the axis, the moment of inertia will be maximum as compared to this axis and this axis, because this is perpendicular axis theorem, this will be sum of this and this. So, if I am giving it this rotation, that means I am in this, I am satisfying this condition, I1 is maximum. What if I1 is minimum? Okay. If I1 is minimum, then what happens? This is minimum. So, I1 minus I2 is negative because I1 is minimum. But I3 minus I1 is positive because I1 is minimum. So, this is again negative. So, the same story is the same story. Again omega 2, omega 3 will oscillate with small amplitude. That means motion is stable. Okay, I had given angular velocity about omega 1, even if it picks up some omega 2, some omega 3 little bit, that is not going to disturb the motion too much. Largely it is still rotating about that one axis. Now finally, if I1 is intermediate between I2 and I3, it is intermediate between I2 and I3, then if one is positive, other will be also positive. If one is negative, other is also negative. Okay. If I1 is in between and I2 is the largest, suppose I2 is largest and this is in between, this is the story, then you can see I1 minus I2. So, this is smaller, this is larger, so this is negative, and I3 minus I1. I3 minus I1, this is smaller, this is bigger, again negative. So, this will be positive. Same will be the story if it's the other way. So, if I1 is intermediate between I2 and I3, then this factor here is positive, and if this factor is positive, you can write your equation as omega 2 double dot is equal to alpha square times omega 2, and you know the solution. You know the solution of this equation also, it will be like e to the power alpha t, and the other term will be e to the power minus alpha t, but this will not dominate, this will dominate. So, it will keep increasing. Okay, omega 2 will keep increasing, because omega 2 will be some constant, although this is a small constant, initially it is very small, say e to the power alpha t, and some b e to the power minus alpha t, ultimately this dominates. So, initially the value is small, but this is continuously increasing as time passes. Okay, and therefore omega 2, even if what's initially small, it will keep increasing, it will keep increasing. Same will be the story with omega 3. So, this is not stable. So, when I am rotating it this way to start the motion, I am using this intermediate. My this moment of inertia of this plate about this is intermediate between about this and about this. This is the smallest. This is the smallest. Masses are close to the axis. Then this is a little bit larger. Okay, that ml square by 12, mb square by 12, and then this is sum of these two. So, that is what you have seen. If I am doing this rotation and then letting it fall, as time passes, it is picking up the other rotations, and finally in some situations when it is rotating about this axis, then it becomes stable and it falls on the table that way. So, this is about stability. So, before taking up the next problem, let me give the demonstration of the situation which will be there in that problem. And that is, I have this wheel and I have an axle here, this is an axle, and then a rope is tied to this end and I am holding it here, okay. And then this wheel will be spun, I will be giving a spin angular velocity, it will spin like this. So, let us do that and see what happens. So, this plane is vertical and then I am giving a large velocity, and you see the wheel is spinning and is also rotating about this about the vertical line through this support here, okay. Once again, so the wheel will keep spinning, that is one, at the same time it will rotate like this, it will rotate like this, right. And if this speed is high, it will remain vertical, almost remain vertical. See once again. So, there is a precision. So, now the problem is the same situation which is written here. A wheel of mass m has moment of inertia I naught about its symmetry axis. So, I have a wheel and this is the symmetry axis, and the moment of inertia about this axis, which we will call, let us say 3 axis, is I naught. A light axle is attached to the center. So, I have an axle here, light, okay. This is axle, this line is our geometrical line, right, to show the axis. This is the actual physical axle there, and then the other end length being L. So, this length is L. The other end of the axle is tied to a light rope fixed at some support. So, this is a rope, and that I was holding here. So, this is that fixed support, this point is fixed. Initially the rope is nearly vertical. So, initially the rope is nearly vertical. So, this angle is beta, let us say small, nearly vertical. The axle horizontal, this is horizontal, and the wheel is spinning with large angular velocity omega naught, okay. So, it is spinning with large angular velocity omega naught, that is given. The wheel axle system moves under the gravity and of course this tension, right, gravity you can write, and the tension from the rope. So, these are the forces on this wheel axle system. Assume that it precesses with a uniform angular velocity about the vertical line through the support. You had seen that this is called precision, this motion is called precision, this is called spin. So, it is precessing with a uniform angular velocity, and that the spin velocity remains constant. So, you assume that the spin velocity omega naught, that remains constant. Now, you have to find that angular velocity of precession and find the angle between the rope and the vertical, assuming it to be small. So, this is our question. So, let us choose axis system. So, this I will be using as 3 axis, and vertical from here I will be using as 1 axis, and then horizontal in this plane of the disc, that I will be using as 2 axis. These are principal axis because this is perpendicular to the wheel, it is a symmetrical system. So, this is a principal axis, then this is a diameter, okay. So, you assume that it is all symmetrical, and this is principal axis, and then this is also a diameter. So, this is also principal axis system. So, this 1, 2, 3 is principal axis system, principal axis, 1, 2, 3 are principal axis, but they are not fixed in the body. It is not body fixed frame. Why? 3 is all right, all the time it is normal to this disc, plane of the disc. So, this is all right, this is fixed, but this I am saying it is vertical, and at different times different radii will come here. This time this particular radius is vertical, but now the disc is rotating. If the disc is rotating, let me rotate it this way. If the disc is rotating, then this radius, which was not vertical, will become vertical after some time, and therefore this 1 axis is not fixed with the body, 2 axis is not fixed with the body. So, it is not fixed in the body. So, if I use these axes, I cannot use Euler's equation of motion, because Euler's equation of motion are based on the assumption that our principal axis 1, 2, 3 are fixed in the body, okay. That is why that dl dt in body, so that those things are calculated with that assumption. So, we will not be using that. Torque is equal to dl dt in inertial frame, and then this is equal to dl dt in a rotating frame which may not be fixed with the body, and then omega cross L. And what omega is this? What omega is this? This is very important. What omega is this? I should not use this symbol. So let me use another symbol, capital omega. This is angular velocity of the frame, of this rotating frame. With respect to the inertial frame. Alright, so we have done that. So we have chosen the 1, 2, 3 axis rotating frame of reference. This frame is rotating, and if I look from the lab, from the inertial frame, this origin is also going on a circular path. Okay, so this equation, when we derived that time, our origins were same. Now this origin is also going on circular path, so that also we should take into account. So what I do is I use another frame, say XYZ frame. Let me use another frame, XYZ frame. And what is the description? XYZ axis coincide with 1, 2, 3 axis, 1, 2, 3 axis, coincide with 1, 2, 3 axis at t equal to 0. Okay. After that, the directions of XYZ remain fixed in the lap frame, which is inertial. So carefully see what this XYZ frame. At t equal to 0, this is x, this is y, this is z. Fine. But after some time, the wheel goes somewhere else, this goes somewhere else, and the axis 1 axis, 2 axis, 3 axis, they are all rotating. If the wheel is going from here to here, this 3 axis, for example, this 3 axis is also going, it is normal to the disk. But our XYZ axis, the origin will go. The origin is here. Okay, origin of this XYZ frame is at the center of the wheel, same origin as for 1, 2, 3. Origin will change, but the direction will not change. If this is axis, the origin has gone here, this is the x axis. It comes here, this is still the x axis. X axis, y axis, z axis will not change orientation. 1, 2, 3 axis can. Right? So that is how we have defined. We are defining XYZ frame. Now, can I use this XYZ frame as an inertial frame of reference? No, because ultimately the origin is going in a circle. Each point of the frame is going in a circle, right? Different circle, but same with the same radius. And therefore, it is a translation of the frame. We had discussed it earlier when we were doing non-inertial frames, rotating frames. It's a translation of the frame, and we only have to use pseudo forces. If I want to use this XYZ axis as inertial frame, I only have to use pseudo forces, which are mass of the particle into acceleration of this frame, and that acceleration is same for all points of the frame. It's just that whatever origin is going with some angular velocity, capital omega, omega square times this radius of that circle, and in opposite direction, and so on and so on. Important thing is, for all particles of mass m, wherever they are situated, for all those particles, if the mass is m, the pseudo force is same, mass into that acceleration of the frame, and therefore the torque of all those pseudo forces about the center of mass will be 0. That is how the center of mass is defined. mg, all particles, mg, and if you take torque of all those things about the center of mass, 0. Similarly, here the pseudo force, m into a naught, m into a naught, m into a naught, m into a naught. If you take the torque about the center of mass, it is 0. So although it is not an inertial frame of reference, but as far as the torques are concerned, I have taken care of pseudo forces, so I can treat it as inertial frame of reference, and those pseudo forces have no torque, and so I can directly use this I can directly use this. This can also be written as dl dt in xyz frame. Okay, dl dt in xyz frame is equal to dl dt in 1 2 3 frame. This is our 1 2 3 frame, and then plus this. So let's write our equations. This omega with which this frame is rotating is omega times E1 cap. This vertical is E1 direction, and this whole frame, 1 2 3 frame, is rotating with an angular velocity of capital omega, which is the precession velocity. So with this velocity it is rotating. I am putting the origin here, so it is rotating at its own place like that, but the angular velocity will still remain that omega. And for particle, for any particle, and that means for this whole object, this whole wheel axle system, omega will be equal to omega 3 or omega naught in E3 direction, correct? This is that spin, omega naught in E3 direction, that remains constant, we have assumed, and plus this omega E1. So this is our omega for this body, and therefore when we write L, this L is written as, in 1 2 3 system we will express this L, but remember it's L is L, vector is vector. In any system you can write the components. So this L is equal to I1 omega 1 E1 cap plus I2 omega 2 E2 cap plus I3 omega 3 E3 cap. So this is how we can write, because 1 2 3 are principal axis, therefore we can write that. And then omega has 3 component, omega has 1 component and no 2 components. So this is equal to I1 and omega 1, yes, omega 1 is there, capital omega, E1 cap. This is not there, omega 2 is 0 and this is there, plus I3 is that I naught, and omega 3 is omega 3 is omega naught, E3 cap, correct. So this is L, this is our L vector, and then we write this dl dt torque, and torque is equal to dl dt in inertial frame of reference, which is same as dl dt in xyz frame of reference. So that, and this is equal to, so this is inertial and this is equal to, in 1 2 3 frame you can see that no component is changing. Okay, so when you write dl dt in this 1 2 3 frame, this part is 0 and therefore it is this part, and this part is equal to omega E1 cap cross L, and here is L. So let me make some space and then we write it. So our equation was torque was equal to that omega cross L, so this is omega and then cross L, and L is, the first component was I1 omega 1 E1 cap, second component was 0, and the third component was I3 omega 3, which is I naught and omega naught, E3 cap. This is what we had derived so far. Now we work on this. This is equal to, this part is 0, so it is omega here, I naught here, omega naught here, E1 cap cross E3 cap, which is minus E2 cap. Now the torque is coming from where? The forces. And what are the forces on this wheel axle system? The forces are gravity mg and then this tension T. These are the forces which are acting on this wheel axle system, for which we are writing all the equations, and we can write torque about the center, about the origin, and therefore torque of this mg will be 0, and you only need torque of this T about this origin. So it will be R cross F. Remember torque, R cross F. What is R here? R is this vector. This is R. Here is the origin and here is the force. So this is R. You write it as L and minus E3 cap. Correct? It is in this direction, minus E3 cap. And then the cross product with this tension. It has 2 components. One is in this direction, one is in this direction. And this component is T cos beta. So T cos beta. What direction? E1 direction. That's the one direction. So E1 cap. And T sin theta will be 0 because it will, that is passing through the center. It is this, and this is equal to, you see, this E3 cross E1 is E2. So, it is minus and L here, and then this tension cos beta here, and then E2 cap, right. This minus is here, E3 cap, cross E1 cap is E2 cap, T cos beta here, this L is here. So, this is the torque, and from this equation torque is this capital omega I naught omega naught minus E2 cap. So, see the directions are good, minus E2 cap and minus E2 cap, and therefore, the magnitudes are also good. L into this L is length okay, this L is length. So, let me write a small l, let me write it a small l here. So, it is L, and so this is L here. So, small l into length into this T cos beta is equal to omega and I naught and then omega naught. So, this is one thing. Then there is a equilibrium in vertical direction. Okay, this whole wheel axle system, the center of mass is going on a horizontal circle. So, in vertical direction there is an equilibrium, and therefore, this T cos beta should be equal to mg, right. So, T cos beta should be equal to mg because of the vertical equilibrium, and therefore, this equation now becomes L into m into g is equal to capital omega I naught omega naught, and therefore, capital omega is equal to m g L divided by this I naught omega naught, I naught omega naught. So, this is the answer of part A. This is the part A answer. What is the, find the angular velocity of precession. So, the angular velocity of precession is mgl divided by I naught omega naught. More is omega naught, higher you spin it, and then you will have lower angular velocity, it will go slowly. If you spin it fast, it will go slowly, it will precess slowly. If you don't give that much of spin, then it will go faster. So, that is this from here. Now, the second part is find the angle between the rope and the vertical, that means find this beta. So, now this component, this horizontal component is T sin beta. This is T cos beta this side and T sin beta this side. What is this sin beta doing? This is providing the centripetal acceleration, because the center of mass is going in a circular path, and therefore, the net force on the object must be mass of the object into acceleration of the center of mass, and therefore, this provides you the centripetal acceleration. So, T sin theta should be equal to, and that you know how much it is, T sin theta is a force, and that is mass into omega square into radius, and radius is L plus, this is the center of this circle. So, L and plus, if this distance is d, okay, if this distance is also needed, if this distance is d, it is d sin beta, d sin beta, okay, and t you can again write from here what is t, and then things can be written there, but let me do this is beta. But let me use this approximation. Sin beta is beta and cos beta is 1. Remember 1 minus beta square by 2, that is why we can take it 1 if beta is small, sin beta is beta. Then this becomes T times beta is equal to m omega square and then L plus beta times d. And this equation here, T cos beta equal to mg, under that approximation T is equal to mg. So, T equal to mg, and therefore, mg beta is equal to m omega square L plus beta d, and from here you can write, you can collect these two beta terms together and then solve it and get beta value of beta. So, we will stop here, and next class we will take maybe one more problem, and then we will finish the course. So, today is our final lecture on this course, classical mechanics, and I will be doing one or two problems before we finally close this course. Our first problem is on this symmetric top, and you know top which children play with it. There is some thread, they wrap that thread on that top, and then there is a pointed iron nail, and then they throw it on the ground, and that it spins and it processes. So, that is the situation. A symmetric top of mass m is set spinning with an angular velocity omega s. so that fast velocity, and its pointed end fixed on the ground. The distance of the center of mass from the pointed end is small l. The top precesses about vertical line through the pointed end with a constant angular velocity omega. So, when children play like that, it spins very fast, and then if it is at some angle to the vertical, then it precesses like this, keep spinning and then it precesses. So, that kind of situation is there. Find the conditions on these parameters, various parameters which are there in the problem, so that the top continues precession with this constant angular velocity at that theta. This is also known as steady precession. Okay, steady. This is also known as steady precession. So, here the situation, this is the top. Symmetric means you have this axis and all directions perpendicular to the axis, they have same mass distribution. So, that is symmetric top, and then this is that pointed end on the ground. It is spinning fast, and then it is precessing about this vertical line. This is going in a circular path, this whole top is going like this. So, that is the situation. You have to find the conditions on this mass and then theta, this omega, capital omega, small omega, and other things, so that it continues precession with a constant angular velocity. So, what is our strategy? We first choose a principal axis system, and naturally this symmetry axis will be taken as the 3 axis E3. Then in this plane, this vertical plane containing this vertical line through the pointed end and this 3 axis. In this plane, you draw perpendicular to this 3 axis, and that will be the 1 axis. So, this is our 3 axis. When it precesses, it goes somewhere else behind the board, let us say, then this comes out of the board, and perpendicular to these two will be our 2 axis. So, this will be 2 axis. Now, these are principal axis. Why? This 3 is a rotational symmetry axis, 3-fold, 4-fold, 5-fold, infinite fold, because the whole thing is symmetric. You rotate it by, it's a solid top, so you rotate by any angle and you get the same mass distribution. So, this is a rotational symmetry axis, therefore, it has to be the principal axis, and this plane here, this plane is a reflection symmetry plane, and any line perpendicular to that has to be a principal axis. So, this is a principal axis, and if 2 of them are principal axis, then the third has to be. So, this is our principal axis system, principal axis 1, 2, 3, but not fixed with the body, Okay, it is not fixed with the body in the sense that this is spinning. So, when this is spinning, these axes do not spin with that. Okay. Although this remains the same, but these 2 axes, they will not spin at that velocity with it. So, it is not fixed in the body. So, we will not use Euler's equations. Okay. Fine. So, this is our system, and then the angular velocity, and this is our origin, right? Naturally, this is our origin. So, angular velocity will be this omega, and then this is, let us say, z axis, omega k cap. This is because of that precession, and then because of this is omega s, and in E3 direction. And this k also you can write in E1, E2, E3. This is omega. This k vector will be cos theta times 3 vector, cos theta times E3 vector, and plus this is the unit vector k, cos theta in this direction and sin theta in this direction. So, sin theta times E1 cap. This is this thing k cap, and then plus omega s and E3 cap. So, you can write this as omega sin theta E1 cap plus omega s plus omega cos theta E3 cap. So, that is what this omega is, and you write what is L vector, angular momentum vector. It is I1 omega 1 E1 cap plus I2 omega 2 E2 cap and plus I3 omega 3 E3 cap. Since these are principal axes, therefore, I can write that, otherwise that 9 component matrix will be needed. Okay, so, this is it, and the torque tau, which is dl dt, that is our lap frame. This is equal to dl dt in the rotating frame 1 2 3 frame, and then 1 2 3 frame is rotating about that lab axis with omega, capital omega, and therefore it is capital omega cross L. Okay, if this is the z axis, if I make an x axis and y axis fixed in the lab, then with respect to that lab frame, this 1 2 3 axis, they are just going around this vertical, which will be this omega. So our frame is rotating at omega, and therefore that omega comes here cross L. This is our lap frame or inertial frame. So this is our relation, that is what we will be using. What is dl dt in 1 2 3 frame? Here is L. This is equal to I1. What is omega 1? Omega 1 is this. So omega sine theta, and this is omega 1 E1 cap plus I2 into omega 2. What is omega 2? Omega 2 is 0. Omega 2 is 0. There is no omega 2 here, and so I don't have to write this. Then I3 omega 3. And what is omega 3? Omega 3 is this, and we will write that as omega 3. Let me keep it omega 3, where omega 3 is omega s and plus omega cos theta, capital omega cos theta. Okay. So what is this dl dt? This dl dt is, this is constant, this is constant, this is constant, so this component does not change with time. This is constant, this is constant, so this component does not change with time. So in this 1 2 3 frame, dl dt is 0, and so this is just, it is just omega cross L, and that means omega vector is here. This is omega vector, omega cos theta E3 cap and plus omega sine theta E1 cap. Okay, this omega is just omega in k cap direction, and omega in k cap direction we have already written omega cos theta E3 cap plus omega sine theta E1 cap cross with what? Cross with L, that is I1 capital omega sine theta, I1 capital omega sine theta, and then E1 cap, and plus I3 omega 3, and that is in E3 cap. So let's do this with this omega cos theta I1 omega sine theta. It is I1, it is omega square, capital omega square, then I have cos theta and sine theta, so sine theta and cos theta, and then we have E3 cross E1, which is E2 cap. This is this term. Now come with this. This is plus E1 cross E1 cross is 0, and therefore it is this cross this. So it is I3 omega 3 capital omega sine theta E1 cross E3 cap is minus E2 cap, so it is minus here and E2 cap here. Okay, when you cross product with this term, E3 cap cross E3 E1 cap gives you E2 cap, E3 cap cross E3 cap is 0. When you cross with this term, E1 cap cross E1 cap is 0, and then E1 cap cross E3 cap gives you minus E2. So it is in E2 direction. Okay, so this is the torque. But from where this torque is coming? Where is the force? Torque of which force? So if this torque is the system, the forces are mg here, this is mg, and then some normal reaction and some friction perhaps. So normal is this way and friction is this way, the total reaction is at some angle. But then our origin is here. So this friction or this normal force will not have a torque about the origin. Remember, everything is about the origin, angular momentum about the origin, torque about the origin. So these forces which are there from the ground, they do not produce any torque. The torque is produced from this mg only. And how much is that? If this is mg and this is the point, so and this angle is theta, so this angle is theta, so it is mg and then L sine theta, mg L sine theta. So torque is equal to mg L sine theta. And you can see from this diagram, this torque is in this diagram it is clockwise from our side. I am finding clockwise, so it's away from me, so it is minus E2 cap. Good, it is in E2 cap direction, and from here I am also getting E2 cap direction. So compare these two, this is the same torque and the same torque here. So you have I1, then omega square sine theta cos theta, and minus I3 omega 3 omega sine theta is equal to mgl sine theta, and here it is minus mgl sine theta and E2 cap. So this is equal to this. Now sine theta you can cancel, sine theta here, and sine theta here. So that can be cancelled. What you have now is I1 cos theta capital omega square, and then minus I3 omega 3, and then capital omega, and plus mgl is equal to 0. This is equal to 0. So from here you can try to write what this omega is, what this capital omega is, and what this capital omega will be. It's a quadratic equation. It's a quadratic equation. So the first observation is that not all omegas are allowed. You need only real omegas. To get a real root of this quadratic equation, the discriminant should be positive or at best 0. So that will put some restriction on this omega 3. So let us see what it is. The discriminant is b square minus 4ac, and I am working on this omega. So this is our b, minus I3 omega 3, that is our b. So to get a real capital omega, I should have I3 square and omega 3 square, b square, and minus 4ac. So minus 4 times, and this is I1 cos theta, and multiplied by that mgl. This should be greater than or equal to 0. So omega 3, I3 omega 3 square should be greater than or equal to 4 I1 cos theta, 4 I1 mgl and cos theta. So I3 omega 3 should be greater than square root of this, and therefore omega 3 should be greater than or equal to 4 I1 mgl cos theta, and then divided by this I3, or you can write here I3 square, like that. And remember, this omega 3 is omega s and plus omega cos theta, right? This was our omega 3. This capital omega is going to be small. We will just see this omega s is to be fast enough to make this omega 3 greater than equal to this. So this is the first condition for steady precision. Okay, and if this steady precision is there, we can find the value of this omega, capital omega, from this quadratic equation. So omega will be equal to minus b, which is I3 omega 3, and then plus minus the square root of this b square minus 4ac, that is I3 square omega 3 square, and minus 4 I1 mgl cos theta divided by 2a, that is 2 I1 cos theta, and then omega, a minus b plus minus b square minus 4ac divided by 2a. So these are the two values of this capital omega. You can simplify it little bit. If you can take this I3 omega 3 common out of it, 2 I1 cos theta here, you get 1 plus or minus, then square root of 1 minus 4 I1 mg L cos theta divided by I3 square omega 3 square half power. Right, so I am taking this out, and when it comes out, it is I3 omega 3, and that goes here. So 1 plus minus, and then 1 here, and divided by 4 I1 mgl cos theta divided by I3 square and omega 3 square. Now since omega 3 is large, to get a precision, omega 3 is large, and therefore you can do a binomial expansion and keep only the first term. This whole thing is small. So now it is equal to I3 omega 3 divided by 2 I1 cos theta. You know that 1 minus x or 1 plus x to the power n, when you expand, your first term is nx, and then you have more terms. So if x is small, you can stop here. So this half will come here, and I can do it here itself. So this half comes here, and this becomes 2. So, if you take the positive value, it is 2 plus, and then this whole thing 2 I1 mgl cos theta divided by I3 square omega 3 square. So, this, and if you take the negative value, or so this, or I3 omega 3 divided by I1 cos theta, and if you take the negative value, this negative value, 1 minus 1 and plus this. So, it is just 2 I1 mgl cos theta and divided by I3 square omega 3 square. So, you have two values of this omega. Omega is this or it is this, and since this quantity is small and this 2 is sitting here, therefore, we can neglect this, and this number will be just this 2 cancels with this, and it is I3 omega 3 and then divided by I1 cos theta. This is one relation. This is one relation between those parameters. This capital omega is equal to I3 omega 3 I1 and then this cos theta. So, this I1 is the moment of inertia of this top. Okay, I have to erase the top. So, if this is the top and this was 3 axis, this was vertical, and this is 1 axis. So, I1 is moment of inertia of this torque about this line. So, be careful about this line, this is I1, and I3 is the moment of inertia on the top about this line I3. So, you put those things and you get here. The other choice is this, and then this choice you have I1 cancels out, this cos theta cancels out, and then I3 omega 3 will cancel one power of this. So, what you have is now mgl only in the numerator, mgl in the numerator, and divided by I3 omega 3. So, this is another possible relation. So, either omega is equal to this or omega is equal to this. You have to start the motion in this particular fashion, that this is the relation between them or this is the relation between them, then it will continue to process with uniform angular velocity. This is known as slow precession, and this is known as fast precession. Both are possible depending on how you start, but you have to either start this way or start that way. In general, in practice, this is the way the tops are started, with large omega 3 and small precession velocity. So, the question is, a thin hoop of mass m, hoop means you have a mass which is on the periphery, it is a kind of a ring, and the mass is at the periphery only, although there will be spokes from the center, but those things will be treated as light. So, a thin hoop of mass capital M and radius r is fixed to a rod of length capital R as shown in the figure. So, the radius here is capital R, the radius here is capital R, this is capital R, and this rod is also having the length capital R as shown in the figure. The hoop rests on the ground, so it rests on the ground and in a vertical plane. So, you have a hoop here, suppose you have a hoop here and it is placed on the ground and the hoop is vertical, okay, and then this rod is there, from the center you have a rod, and the other end of the rod is attached to a vertical rod through a bracket that can rotate freely. So, here is that vertical rod, here is the bracket, and the other end of this rod is attached to this bracket, and this rod can rotate here in this bracket. This whole bracket can rotate, and therefore, this whole thing can rotate about this line. The hoop rolls on the ground without slipping. So, it rolls on the ground and without slipping here. So, if you have a hoop here, rod here attached to this vertical rod, and then this hoop is rolling. So, it is rolling, but as it rolls, it cannot go straight because of this rod here, and the rod can rotate here. So, this whole hoop will go like this while rolling. So, that is the situation. The hoop rolls on the ground without slipping. The center of mass thus rotating about the vertical rod, thus rotates about the vertical rod. Let this angular velocity be omega. So, this is omega. The center of mass goes in a circular path about this line with this angular velocity. Now, the question, find A, the angular velocity of the hoop. This hoop as a whole, what is the angular velocity? It is spinning, at the same time it is rotating. And then the angular momentum of the hoop about the position of the bracket. So, this is the point at which we need angular momentum. So, these are the two questions. So, let us take this point as A, this point of B. I can directly write omega, not a big problem. Because of this I can write the velocity, angular velocity. Because of this I can write the angular velocity, then no slipping condition I can put. But let us see one more small technique that you can use in other problems also. So we have to find omega, small omega, the angular velocity of this hoop. Now for any object which is rotating, velocity can be written as omega cross r. Velocity of any particle is velocity, general relation is v equal to some point, you pick up some point and then r of that point with respect to this. So velocity of say point q is r of this q with respect to p, that is the general one. But if you pick up the right point, and here we are picking the right point which is 0, this point is 0, this will be our system, hoop plus that horizontal rod. We will consider this as the system, and this will be our reference point, which is at rest, and therefore we have this just v equal to omega cross r if I use this point as the reference. Now for point B, it's rolling without slipping, so v of B should be equal to, according to this, omega cross r of this point B, this, and that is equal to omega cross AB vector, and this is equal to omega cross, and this is 0, okay, this is 0, because at point B there is no velocity, it is rolling without slipping, so this is 0, and therefore this omega must be parallel to AB. The cross product is 0, therefore it has to be parallel to AB, and therefore I can write omega as some k. And what is AB vector? What is this AB vector? This AB vector is this AC vector and plus CB vector. So this is AC vector and CB vector. Now let me take axis. This will be our 3 axis, as usual, symmetry axis we take as 3 axis. Then this vertical will be our 1 axis, this will be 1 axis, this will be 1 axis, and then the perpendicular will be 2 axis, like this. So 1, 2, 3, origin here. This is principal axis system. This 3 is a principal axis, rotational symmetry axis. Then there's a reflection plane, this is a reflection plane, this side and this side, they can reflect on each other, and perpendicular to that will be will be principal axis. So this is principal axis, this is principal axis, and therefore this is principal axis. So in this principal axis system, let me write this, this is K, and AC is R E3 cap, plus CB is R and then minus E1 cap. So R and minus E1 cap. So I can put minus here and E1 cap here. So that is omega. Omega is K R E3 cap and minus R E1 cap. Now once this K is unknown yet. Now once I have written the expression for omega, with this omega I can also write the velocity of this point C. So what is the velocity of point C? Velocity of point C is equal to omega cross position vector of C, and omega is K times R, you can write here, and E3 cap and minus E1 cap, this is omega, and cross R of C, position vector of C, which is R E3 cap, and that you can write now KR square, E3 cap is 0, and minus E1 cap cross E3 cap will be E2 cap. KR square 0 here, and E1 cap cross E3 cap is minus E2 cap, and therefore with this minus it is positive, so it is this. But then we also know that this center is going on this circle with this omega, and therefore the speed is omega times r. It's just going on a circle with a constant angular velocity capital omega, and therefore the velocity, linear velocity, will be this capital omega into r. And what will be the direction in terms of our axis system? Since it is going that way, so it has to roll, and if I am looking from this side clockwise, and therefore it is on the other side, so minus E2 cap. So VC is also equal to omega r in minus E2 cap direction. Okay, that we know from the rolling. If it is rolling this way, the particle, this is going in this direction this way, and therefore we can write the speed of this. The speed of this will be in minus E2 cap direction, in that direction, and 2 is in this direction. So it is this. Now you can compare these two VCs. I got it in 2 different ways, but the same velocity V, and therefore this K R square E2 cap, or E2 cap you can leave from here, K R square is equal to minus omega r, and so K is equal to minus omega and by r, and hence omega is equal to, come from here, omega is equal to k. K is minus capital omega by r. So it is capital r will cancel. So capital omega here and minus is there. So E1 cap minus E3 cap. So that is the answer of the first part. So this is all answer of the first part. Find the angular velocity of the hoop. So that's the angular velocity of the hoop. The angular momentum of the hoop about the position of the bracket. So I need angular momentum here. So you know what it is? Angular momentum is I1 omega 1 E1 cap plus I2 omega 2 E2 cap plus I3 omega 3 E3 cap. You have to make sure that your axes are principal axis system, then only you can write this, otherwise that 9 components matrix will come. So this is L, in our case it is I1. So if it is a hoop, whole mass is concentrated on the periphery and the radius is capital R, mass is m, and therefore I1, what is I1? I1 is moment of inertia of this with respect to one axis, and the axis is here, this is one axis. So about this diameter, the moment of inertia will be mr square by 2. Okay, it's a hoop, ring. So about this diameter it is this, then parallel axis theorem to get the moment of inertia about this, and that will be I1 will be mr square plus mr square by 2 and omega 1. What is omega 1? This is omega. So omega 1 is this capital omega. So capital omega and then this E1 cap. Right? I1 is here, omega 1 is here, and E1 cap is here. Omega 2, I don't have any omega 2, there is no 2 component of omega, so this term I need not write, and then this term I3. What is I3? Moment of inertia about 3 axis, and that's the axis of the hoop, and so it is mr square, it is mr square. Omega 3, what is omega 3? Omega 3 is minus capital omega, so minus capital omega and E3 cap. That's it, that's it. 3 by 2 mr square omega E1 cap minus mr square omega and E3 cap. So that's the angular momentum. Now you can go further to write if there is a torque, if this L is changing with time, and if there is a torque, from where that torque is coming, what are the forces which are creating that torque, and so on and so forth. What is the force that is taking the center of mass in the circle, and all those things you can further do exercises with this situation. Okay, so with that I close this classical mechanics course. Had been a good experience, revised many things that I used to teach at IIT Kanpur a few years ago, and learnt many things. I hope you also enjoyed it. So keep enjoying physics. Thank you very much.